It is 9 o'clock, so I'm going to go ahead and kick us off. Welcome, everybody. Thank you so much for making it out today. It's good to see you all. I'm Shira Francis, and y'all probably know me. I'm the UFS Secretariat, so I've been on calls with plenty of you, but we don't have a lot of time for my introduction, so I'm just going to quickly hand it over to John Tenhove.
All right, thanks, Shira. That was very quick. Today the first session is going to discuss NOAA modeling priorities, and we have three senior leaders here from Weather Service, Ocean Service, and also NOAA Research. Speaking first will be Steve Smith, the Office of Science, Technology, and Integration Director. Next will be Mark Osler, the Senior Advisor for Coastal Inundation and Resilience, and then Gina Esco, the Director of the Weather Program Office. So I'll turn it over to Steve.
Oh, I gotta hold it on. Yeah. Thanks, John. Really great meeting so far. I really enjoyed the conversations and presentations yesterday. Thinking about community and what it means in the context of UFS, for example, I think if we do no better than having a commitment to coming together periodically as a group like this and having open discussions where debate is had and people don't necessarily agree, but we do it in a civil, respectful way to advance the nature of our community. To me, that's community. That is coming forward in a purposeful way. So I'll take that to the bank every day, and I really appreciate everybody approaching this meeting in that sense. I did want to. These are some of my takeaways before I get to sort of where Weather Service is at. It's really interesting to hear the conversations in a really big strategic picture. So, the year I was born, the Berlin Wall went up. So I'm dating myself here, but that was the beginning of the Cold War, and so I feel like we've been living through Cold War modeling, since that time, and this has been in tremendous benefit to society to be able to predict the future of weather and atmosphere. And our modeling has generated tremendous benefit across that time. But it feels like we're coming up to maybe like a sea change. I feel it. I feel like and part of this is driven by the conversation on AI, so it feels like we're still, because of the momentum behind, I'll call it Cold War modeling, we're focused on the best prediction of state variables of the atmosphere as the foundation and bedrock of all our services, which they are. But when AI enters into the picture, is the application of AI to that mission still, is that the best use of that new technology? I'm not so sure, right? And I think I put this out there for people to think in the UFS community. Is our vision of UFS sort of still anchored in that, legacy modeling enterprise across, and do we need to think about that? Think about what might be a perhaps different approach to what UFS look like and what the community can bring to it. But focusing on do I have my slide? Got my slide? Yeah, I got a slide. One slide. There we go. All right, so my punchline is modeling for mission, services, and outcomes. So this is a Weather Service perspective. We're not doing modeling for modeling's sake. We're not doing modeling for modeling metrics. It's really focused on mission, saving lives, protecting property, enhancing the economy. And services, warnings, watches, forecasts, and impact-based decision support services that ostensibly, if they're working really well, benefit outcomes, right? And outcomes is the real driver. Are we saving lives? Are we protecting property? Are we enhancing the economy? So that mindset is very critical path, and it's commensurate with our mission to society in general on all those accounts. So I think that question, and it's become like the level of its rising keeps going up because we see in some cases where our modeling forecasts are outstanding days in advance. We don't miss too many big winter storms anymore. We don't miss too many landfalling hurricanes. We have days of lead time to prepare communities for those big events that will be high impact, et cetera. In the mesoscale, not necessarily so, right? I think that's clear. There's still things we don't understand about the mesoscale environment and the boundary layer and convective initiation. So our modeling still has, there's still ways that modeling can improve a lot, I think, too. But a lot of decisions are made in that, 0 to 12 hour time frame. So emerging, I think, in a weather service context is the idea that we have modelings for different decision spaces, seasonal, sub-seasonal, the global, days 7 to 14, and then regional models. And now we're on the brink, I think, of a new wave of mesoscale and hyperlocal models. So this was mentioned yesterday, Kevin Garrett, about the worn-on forecast model as an emergent model for our mission of IDSS, because we know the best regional CAM models still can't really grasp at the detail we need to provide specific guidance and forecasts to communities. So continuing, we still want to improve those models, but really pivoting to sort of this worn-on forecast where we, on a given morning, if it's deep convection, we deploy nests across the country where they're appropriate for fire weather, for severe weather, for extreme precip, and that becomes our emergent ConOps, where our highly trained forecasters can interpret those probabilistic ensemble models in a way and convey very concrete actions to decision makers in which they will act on. And we've seen evidence of this already, where there's a strong signal in the WAFs and a SUE contacts an emergency manager and says, hey, I think you should evacuate this mobile home park and move people to a shelter because it looks like you're likely to have tornadic storms in 2 hours. 2 hours is a lot better than 10 minutes of a worn-on observation, like a tornado vortex signature. So 2 hours, you can do a lot with 2 hours. And so that's starting to look like a next best thing. And then I would take it even further if you look at what NCAR's working on with their fast eddy model, like turbulence resolving kind of model at the street level. That is potentially really lucrative for where people live and decisions they make. Autonomous vehicles operating within an urban environment may be impacted, et cetera. So the integration of that kind of model where people live is I think really important. So all this to say is that in weather service, that's where we're going to continue to advance all the great stuff that EMC has been doing with its partners in OAR over many, many years, but starting to get more serious about deploying, with AI technology. Maybe we have a swarm of, nested models running across the country, depending on what's the events of the day. So I think I'm very optimistic about that and our ability to use that technology with its flaws, with the models that aren't perfect, but with highly trained forecasters devoting their time not to editing grids out to day 7, but actually analyzing these models for that benefit. So we're going to be pushing very hard on worn-on forecasts in the next 12 months or longer to make that a new sort of in the cloud, born in the cloud, will live in the cloud sort of thing, and advance those operations. And really looking forward to the community getting interested in that more, and EMC is standing up to that, acquiring sort of into their fold the worn-on forecast models. So, over.
Thank you so much, Steve. That was perfect timing. We are on to our next presenter, who is joining us virtually, Mark Osler.
Good morning. We okay on a sound check?
Yes, sir.
Thanks. It's a pleasure to be here. As John noted, I serve NOAA as Senior Advisor for Coastal Inundation and Resilience. I really regret I can't be with you in Boulder, but appreciate seeing so many familiar faces. Hi, Steve and Gina, and I did get a shot of the audience earlier. I'd also like to alert y'all to my colleagues, Ed Myers and Saeed Mogimi, who are with you in the room and continue to be engaged throughout the workshop. And on behalf of NOAA, National Ocean Service Assistant Administrator Nicole LaBeouf and Deputy Assistant Administrator Rachel Dempsey, I'm pleased to give highlights of National Ocean Service, or NOS, modeling insights and priorities. NOAA carries significant responsibility for operational modeling at the coast. These mission requirements, of course, include forecasting of weather at the coast and and at sea. And NOAA carries an array of additional and distinct modeling requirements. These include high-resolution modeling and prediction of sea state, tidal currents, and salinity, which impact buoyancy, all impacting commercial navigation. Such modeling informs pilots about real-time keel and bridge clearances and directly improves safety and efficiency of vessel route optimization and port operations across the nation. Coastal modeling is also vital to NOAA's missions to protect human health by enabling monitoring, forecasting, and warnings of harmful algal blooms, the subseasonal and annual predictions and forecasts of high tide flooding at the coast, flooding in the absence of storms, and responding to oil and hazardous chemical spills and supporting search and rescue efforts. The focus of this workshop is important to the National Ocean Service, and the mission of NOS is important to NOAA and to this community. For fiscal year 25, we've made significant progress on several key initiatives. One major focus was on UFS governance, where NOS contributed to the design of a new framework. We are grateful for the enthusiastic invitation, support, and engagement from our Weather Service and NOAA research colleagues to take up a leadership role in this important initiative. NOS also provides funding to support for the new UFS Science Advisor, further confirming our commitment to supporting the UFS framework and ensuring that NOAA's operational missions at the coast are reflected therein. Significant operational achievements include multiple upgrades and advancements within NOAA's Surge and Tide Operational Forecast System, or STOFS. This includes upgrades to STOFS 2D Global, STOFS 3D Atlantic, and implementing STOFS 3D Pacific for the first time. Additionally, we successfully demonstrated a stable application-level workflow for UFS Coastal Development Team. Additional updates from the past year were the successful testing of the West Coast Operational Forecast System to improve surface salinity forecasts, incorporating a full suite of freshwater discharge from coastal watersheds, and development of a new module for NOS skill assessment, improving our assessment processes and the visualization of model performance. Looking ahead to fiscal year 2026, our priorities are centered on model consolidation, expanding geographic coverage, and streamlining operations. Key strategic priority is consolidation of our many legacy modeling systems. The overall scope here is to go from many smaller models to fewer, larger regional models. For example, in the Northeast, we currently operate separate model systems for each of the Gulf of Maine, New York Harbor, Delaware Bay, and Chesapeake Bay. Each have their own operational forecast systems. These will be working to combine into a single Northeast coastal ocean forecast system in the coming years. We're also focused on addressing critical regional gaps of coverage, inclusive of Pamlico Sound, and then in Puerto Rico, and expanded model coverage for the Pacific Basin and Alaska. A third major initiative is the unification of our operational workflows, working to establish a standardized workflow template that can be used across all of the Ocean Service operational forecast systems. And of course, all of these efforts, past, present, and future, have a continued legacy of embracing emerging technology, inclusive of GPU and other compute methods, enabling faster and higher resolution and increased leverage of probabilistic forecasts as operational costs become reduced, as well as advancing AI and ML capabilities to increase model efficiency and enhance data access integration through our operations. So to close, NOAA carries significant responsibility for operational modeling at the coast to enable safe marine navigation, enhance coastal resilience, protect human health, and respond to hazardous spills. There is significant value to the nation resulting from ever further integration of these ocean service modeling efforts within the wider UFS framework and this community. NOAA's committed, Ocean Service is committed to continuing to improve on NOAA's ability to integrate coastal operational requirements within this framework and collaborate ever more efficiently with our many partners within and outside of NOAA. I encourage you to seek out Ed and Saeed throughout the workshop. Ask them questions about their work and share with them what matters most to you with respect to operational coastal modeling within the UFS. Know that myself and Rachel Dempsey look forward to hearing from them and from you directly about the outcomes of the workshop and tangible next steps. Thank you. Happy to pass it back.
Thank you, Mark. Gina?
Good morning, everyone. It is with such great excitement that I speak to all of you this morning. I would say I've been WPO director for 9 months, but this is the most official remarks I think I've given in those 9 months. So I'm very excited to be here today. And I want to share a story. I'm someone who likes to share stories, and I think this community, Bill LaPenta is still a very well-known individual and person who really inspired what we're doing here today. How many of you knew Bill? Yeah, so many of you, so many of you. I am humbled that I'm in a position that he once held. In fact, I think we both are. And around this time of year, I always think about him. Just days before he passed away, the Weather Program Office held a retreat. And Bill had a meeting, and he came in late to an icebreaker. And we all had to pick like a toy out of a box. And he picked a rainbow-colored lollipop in the shape of kind of a unicorn horn. And that's what he said. We had to come up with a reason why that marker and that toy made meaning to us. And he took it, and without hesitation, he went, you know, sometimes you do need to be a unicorn in this job. And I thought, and I remember that ever since. And I thought, yeah, when I come here today and I see all the different types of expertise that is represented here, I think of you as a bunch of unicorns. And we come together to make this wonderful community. And it's really, really inspiring to see that. And I'm delighted to be part of that with you here today. Thank you. Innovative paths take time, persistence, and often a whole lot of patience. Since coming on board as director, I've taken time to learn about community modeling. As many of you know, I'm not a modeler, so this has been a really lovely journey to learn about the history, the desire for a community modeling board, right? A way to give feedback to NOAA, and some of the roadblocks that the community has experienced. Together with partners like Steve from Weather Service, Mark from Ocean Service, and I've got to give a huge shout out to Fred Carr from OU and Jim Kinter from GMU. We found a unique path to jumpstart the Community Modeling Board. And so it is with extreme excitement that I announced that there will be an ad hoc committee under the Weather, Water, Climate Enterprise for community modeling. The goal is to mature that ad hoc committee over the next year into a community modeling board underneath that commission. We are now soliciting volunteers for that committee. And I hope that many of you here today will take a screenshot of that QR code and consider nominating yourself or nominating someone else to join that activity. We are delighted, really, really proud and excited to see that move forward. In addition, on the OER and Weather Program Office side, we are busy at work. Many of our EPIC employees are here today and this week. We're working to invest in MPAS, trying to significantly and holistically incorporate MPAS into the UFS. That is a major initiative for our larger OER community. You've heard about Project Eagle the last couple days. I'm sure you'll hear about it more in the coming days. An EPIC version 2.0. We want to make sure that the UFS and the social and technical and IT infrastructure of EPIC works for you. Please consider nominating yourself for that committee so that we have a way for you to give that feedback to us. And of course, you can please contact me anytime throughout this week as well. Thank you so much.
Thank you so much, Gina. I appreciate it. I noticed you were speeding through because we had only a couple minutes remaining. I really appreciate it. And this is just a quick note. Part of my job as the MC of today is I have to keep everybody on time. We have such a packed schedule. So if you hear me interrupt your presentation, please don't take offense to it. I'm just trying to keep us on schedule. And that being said, I'm going to introduce our next set of chairs, Ms. Allison Gregory and Tracy Finera.
Can we have our student presenters come up, actually, and sit? I don't know, Shira, we might be kicking you out. Rowan, Michael, Anna. Who am I missing? I'm missing one.
There you go. He's here.
And Shreyas, obviously. Guys, testing you. Rowan, just you're first, so you should just come up here. So these are our student presentations. They have 10 minutes apiece, and if they don't mind, we're going to save all our questions at the end. So write down your stuff, and let's get started.
All right, cool. All right, hey everyone. For those who don't know me, I'm Rowan. I'm a rising junior at Colgate University studying computer science and geography. I'm from northern Michigan, right about here. You know, folks from Michigan, they like to do that. And I'm here because this summer I worked as the La Penta intern with NOAA under the Weather Program Office, specifically as the UFS Student Ambassador. Oh, I pointed this screen. There we go. Okay, so the UFS Student Ambassador Project has the goal of getting students interested in Earth systems modeling. If you want a robust community of modelers, you need students learning how to be weather modelers. Good coders don't just pop fully formed out of the forehead of Hendrik Tolman. They need to be developed. So for this project, we split it into two components, a technical and engagement side. So for the technical side, I created a tutorial using the UFS short-range weather app to model severe weather. I provided feedback to the UFS development team on usability and user experience. And I created a post-tutorial survey to evaluate the effectiveness of the tutorial. For the engagement side of things, I created a social media campaign to promote the UFS and NOAA internships to students. And, well, I'm here, so that's also part of my internship. To get right into the test case, so for this case I chose to use a derecho. For those who aren't familiar, they're essentially a complex of severe thunderstorms that produces exceptionally powerful winds. The specific storm I chose to use was the August 10, 2020 derecho. This storm produced winds up to 140 miles per hour, or 150 miles per hour actually, which is equivalent to a Category 4 hurricane for the tropically minded. And this storm also produced $11.2 billion in damage, making it the single costliest severe thunderstorm event in history. The other reason I chose this case, besides its significance, was that Gallus Jr. and Harold in 2023 had authored a paper simulating this very case in the SRW under a variety of different conditions, so I had an excellent piece of research to work off of in developing the tutorial. The tutorial itself uses the short-range weather model, which is the regional weather model within the UFS, and I used guide users through 4 different test cases. So 2 different physics suites, the RFS V1 beta and the GFS V16, and 2 different grid scales, 13 and 25 kilometers. I chose to go with coarser grid scales to reduce barriers to entry in terms of computing power. 3-kilometer res looks great, but you need a lot of cloud resources, a lot of HPC compute to run it. So the idea with this, with providing a variety of configurations, is that users are then going to be able to run their own forecast cases themselves. So if they have cases they want to run, they'll know how to configure the model sufficiently enough. I also included a feedback survey at the end, as I mentioned earlier. If we want this tutorial to reduce barriers to entry, we can't just throw it out there and expect people to use it and not know whether it's actually helping. So, and just to give a quick view of the kind of results you can expect to see with this tutorial, this is on the left, the RFS V1 beta running at 13-kilometer resolution, and on the right is observed reflectivity. And while it's not a perfect match, it's pretty good, especially for such a coarse grid resolution. And I think providing this kind of good model output for students during the tutorial will encourage engagement, encourage using the tutorial, because it's neat. For the engagement side of things, I did a social media campaign with the La Penta Live theme, so I live blogged my internship through a weekly series of posts to promote not just the UFS, not just Earth systems modeling, but NOAA internships as well. And for the students in the room, please do apply for La Penta internships. It was a wonderful, wonderful experience. And yeah, you should definitely apply for that. Not just because I'm the UFS ambassador, I'm telling you too, but also because it's cool. So as with any project, there are some challenges. So on the technical side of things, the main issue is the complexity of the UFS software. And anyone who's worked with it knows this. It's a massive, massive piece of code with many different authors and many pieces of software from many different times as well. So if you run into errors, which you can see by the next bullet point I did, it can be difficult to solve them without outside support from the development team. In addition, I did run into a slight issue with configurability. The Gallus Jr. and Herald paper turned on and off convective parameterization and got interesting results out of that. I was not able to do that without writing additional code for configuring new physics suites, and considering the purpose was to develop a tutorial for students, I think that would be a little much to ask, especially non-programmers to do. Additionally, the container was not as portable as it could have been. Obviously, it's never going to be as easy to download as an app, but I ran into some issues setting up on a cloud instance where there were additional prerequisites not listed in the containerized tutorials. For the engagement side of things, the main issue is the limited reach of Epic's social media. So you can see here we have about 1,200 followers, and look, I know we're all here right now, but we can admit this is a fairly niche topic. We're nerds, right? But I think we can do better than this. I'm sure some of you in the room have more than 1,200 followers. The other issue I ran into is a lack of peers engaging with the UFS, so I didn't have other students to bounce ideas off of to talk to, and if we want a robust modeling community, we need users talking to each other. So some lessons learned. The big lesson was that students are going to need direct support to work on the model, both in terms of technical support to understand the software, and in terms of computational resources. That also connects to the engagement side of things. I think we should focus on engaging with departments and getting students working on the model through their faculty advisors rather than just working on it themselves. And ideally, even we could get it in the classroom so that students are doing this not just on their own time, not just as part of research, but actually as a learning process within the classroom. Going back to the technical side of things, I do think we need cleaner code and more extensive documentation. I'm not going to get into the nitty-gritty of it, but if anyone in the room programs, you can read that code there, and you might cringe a little bit. We can do better, especially if we want other developers to be able to read and understand and work with the code. Bouncing back to the engagement side, I think if we want to expand our social media presence, we should work with existing influencers. Some of you might giggle a little bit when I say influencers about weather. But you can see here, this video has about 18,000 views, and it's a pretty granular forecast breakdown, and it's featuring Chris Broyles of the Storm Prediction Center, who talks about his work. I think we could work with content creators like this and expand our social media reach, and there's precedent for this at NOAA. Finally, I'd like to close with the personal impact that using the UFS had on me. So I ran the test case at a 3-kilometer resolution. You can see a couple different fields of that here. A little disappointed with the results. Timing's off, intensity's off. And I took this to Brian Scateri at the Storm Prediction Center, who's an expert on derechos. And he said, no, these are great results. Here, take 8 other test cases, go write a paper about it. Now look, I'm a computer science major. I've never been told to write a paper. I was awestruck. And I think this is the kind of experience we can offer to students if we get them working with the UFS weather models. I'd like to thank my mentors this summer, Allison Gregory, Jose Enrique Alves, and John Tenhove for making this a wonderful, wonderful experience. I'd like to thank Priya Pillai, Adam Clark, Jen Vaught, and Charlene Barone for being subject matter experts on this project. I'd like to thank Bill Gallus and Michelle Harold for their 2023 paper and for giving me the input data used in the tutorial. I'd like to thank UCAR for flying me out here for hosting this conference. It's been a wonderful, wonderful experience. And I'd like to thank everyone who provided feedback on the tutorial to make it an incredibly polished product. And as a final person I'd like to thank Alex Alder, who turned this tutorial into a website that is live now. So you're welcome to scan the QR code, go check that out, and yeah, hope you enjoy.
Yeah. Anyways, I'll be speaking more about science, unfortunately. Fortunately, too. My voice sounds better than this, but I hope you guys will be able to enjoy this as well. So anyway, my name is Michael Kwejoben of Howard University. Before I begin, I'd like to acknowledge my contributors to this project. Dr. Lu of Albany, Sunny Albany, Dr. Shiwei of Albany, and then also part of the joint setup of JCSDA team, Dr. RL, also of Howard University, and then Dr. Shendan of JCSDA, Dr. Corey Martin of NOAA NWS NCEP EMC, also Dr. Andrew Tangbon of NOAA NWS NCEP EMC, and then Dr. Senchal of Howard University. So aerosols is becoming a very important part of our forecast, both for our weather, climate, and then air quality. Accurate representation of aerosols in our ICs results in very improved forecast, and that means we need to have like very realistic representation in our initial conditions. So for this project, what we seek to do is to demonstrate the current aerosol capabilities of NOAA GCAV JEDI, which was earlier presented in the week, and then establish a foundation for the next phase, which is to develop a framework to be able to extend the current system towards a vertical profile level, assimilation improved aerosol representation of initial conditions and then forecast. It was better to be able to divide this into two phases just to make it easier for us to be able to interpret and then make understanding. So like the process to reach our goal. So the first phase will be assimilating VRS AOD, which is that will constrain the aerosol fields in our more initial conditions to be able to make the forecast along the line. After that, we'll be able to evaluate our model performance, post-assimilation using independent observation models to quantify the improvement in our forecast quality and also, look at the improvements with data assimilation. In our phase 2, which will be a vertical profile comparison, that will be a prologue to be able to, get into the next phase, which will be to compare model vertical profiles with Calliope extension coefficient profiles, and then we're able to analyze concentration differences and identify representative discrepancies between the model and then observed vertical structures. So this is our model setup, and then also a bit of details in there for our entire simulation. I'd like to emphasize that this is a weakly coupled model. Our simulation framework, which is JEDI, which I believe everybody should be using. And then our domain resolution will be 100 kilometers, pretty low, but yeah, we seek to run higher resolution. Our forecast length will be 6-hour cycle for 16 days. And then our control will be UFS forecast regraded with, MERA2 data into our ICs. It's also important to emphasize that NOAA itself runs a continuous model, so we begin our simulation right at the beginning of initiation. So then this will be done, theoretically, most of the time we like to, when you think back to Lawrence model and things like that, you like to, run the simulation until it gets to a point of stability, and then you begin your simulation. But however, for this case, because, it's a continuous system, once we get observations, we begin our simulation process. So then our spin-up cycle, which is, that period where we consider, from the beginning of initialization to the point of stability, will also be a part of our, our cycling. So then from the beginning of cycling, we'll also include, data simulation, and then we'll discard, a period where we'll consider our spin-up cycle and then do our evaluation from the period where we consider. So here is a schematic just showing a bit of what it looks like when it comes to DA. We have our NOAA VRS observations and our model forecast, which will be our background, or we call our prior state. And then our DA method, which is 3D FGAT. So this optimally, combines both the NOAA VRS observation and the model forecast, and then finds our analysis, which is our new best state, and then makes a forecast back to our model forecast. Below is also a schematic showing how 3D FGAT works, which is first guess at appropriate time. What happens is that observations come at multiple times when you think about satellite observations. So then at all the points where you are getting observations, you keep on finding analysis, and then interpolates back in time and then forward in time to the point of to find your first guess at appropriate time, which is denoted by the deep blue dashed lines, pretty much in the center. So without further ado, we'll go straight to analyzing our results and then observe some of the improvements and then some things that we can see within that simulation cycle. So our experiment period was from 2023 September 30th 00Z to 2023 October 16th 00Z. So looking at so we'd like to analyze our innovation, which will be how far our background is from our observations. It's pretty good to be able to understand that, to be able to know how much the simulation step is, helping regards to finding the new analysis state or the best states for our next forecast. So, okay, it's already done. So, looking at the red circle, we can see certain, you can see within the within the Sahara and the Sub-Saharan region, where you can see differences between the background and observations. And then that's to say that this analysis is done at 2023 October 8th, which is like 9 days after initiation step. So looking at the background and looking at the observation, we can definitely see certain discrepancies when it comes to the Sahara and the Sub-Saharan region. Looking at aerosol loading, there's much of a difference in that. So the next step, I would like to look at the background and observations, which was already shown, and then look at the analysis. We can obviously see certain improvements in the same circled area back in the previous slide, sorry. And then we can also observe in the bottom right corner, where we can see the increments. That is, looking at the analysis, which are new best states, and then, subtracting that from our background, which are old, our prior, basically. I'm sorry. So anyway, so we can obviously see definitely the DA method adjusts the background, by constraining the analysis towards the observation, reducing the overestimation, and then compensating for underestimations. In effect, the biases is also being reduced in the background fields, pulling the analysis closer to the observation, and in regions where values are either over or underestimated. And then moving on to verification, which is with MODIS. Looking at the results, we can definitely see, very good spatial patterns when it comes to the model, which is on the right, and then and MODIS on the left. On the left, sorry. We can obviously see, very good spatial patterns when it comes to the model. But however, we can see definitely in areas in the Sahara and the Sub-Saharan region, we can see underestimations in there. Which either calls for improvement definitely, or maybe a longer period of assimilation for sure. On top of that, definitely we can talk about results. We're running 100 kilometers, so definitely have like very low resolution. So definitely running higher resolution might also result certain differences, of course, maybe improvements or maybe something more accurate. So on the average, we can definitely notice that the spatial pattern in the model isn't too far off from our MODIS data. So yeah, just like I said before, this is just a difference between the truth and then the background, and then it's just back to what I was saying earlier. It's just to notice that on the average across the entire region isn't too far off, but definitely there are areas within the Sub-Saharan region where it requires improvements when it comes to the assimilation step. So moving on to the next stage, which is comparing, in preparation for our next step, which I earlier mentioned, where we'll be looking at the vertical profiles. In here, I'm trying to demo currently what is being worked on, which is, we are currently, demoing, I'll be demoing what we are currently working on, which is the LiDAR operator that will be helping us to be able to compare Calliope extension profiles with our model states right now. Our current model is in the period where Calliope, isn't valid in terms of like data collection. So this is just a demo just showing what exactly we are trying to achieve in our next step. So of course, that's a big question. What's next? Anyway, so in summary, AOD is just a measure of extension of light over a whole atmospheric column, and it carries very limited amount of information when it comes to the chemical composition and the sizes and particles, and also cannot provide information on the vertical distribution in the atmosphere. So consequently, what we do is, consequently, the resulting analysis is largely dependent by the prior information of our background, containing the model state at a given time. This provides very limited ability for AOD data to be able to correct the aerosol speciation sizes and the vertical distribution in the atmosphere. So in our next step, what we seek to do is to conduct high resolution experiments restricted to the temporal window of Calliope, and then also to compare our model states with Calliope extension profiles. The last two are still currently being worked on, which is the LiDAR forward operator, and then also the assimilation step when it comes to the vertical profiles.
We are at time.
Yeah. Anyway, so yeah, of course, I can't end without acknowledging those who supported this, which is NOAA ANZ for providing the GCAPS model. Of course, computing resources, NOAA Office of Air Resource Laboratory for helping us able to regrid mirror data into our ICs. And then, of course, the technical support from CADRE and then the Joint Center for Satellite Data Assimilation. And then this was also supported by the US Department of Commerce and the National Oceanic and the Atmospheric Administration. Yeah.
Next up, we have Mackenzie Larson.
One moment.
Oh, yeah, I can do that. Okay, hi everyone, I'm Mackenzie Larson. I'm a fourth-year PhD candidate here at the University of Colorado Boulder. And today I'm going to be talking about also my LaPenta internship from this summer, and we're going to be talking about the evaluation of initial condition blending within MPAS to inform the RRFS version 2. So kind of just to dive right into it, one process that occurs within the RFS is called partial cycling. This is the interruption of continuous cycling to essentially restart and force regional simulations with global data to prevent model drift. So what you see here on the left is some RFS output. It is a regional simulation kind of focused over CONUS. And so twice daily it is forced with lateral boundary conditions of updated global data from the Global Forecast System, or the GFS. And if we look at this in more of an operational timeline, on the top line here, you're seeing the RFS full cycle. So it's forecasting every hour, and twice in the background, you can see on that bottom line, you have the RFS partial cycle that's going on, where essentially the model is restarted with updated GFS large-scale atmospheric fields, and then eventually that model is essentially, after it's spun up, put back into the RFS full cycle. But what we know is that this is computationally expensive and complex, so our group has been working on a different method to see if we can replace this. And that method is called initial condition, or IC blending, and this is where you blend higher resolution regional ICs with coarser resolution global ICs. So our regional ICs that I'm going to talk about throughout this presentation are going to be 3-kilometer ensemble Kalman filter, or ENKF analyses. And in the schematic I'm about to show you, these are going to be denoted with an S for small-scale data. And then our global ICs are going to be those quarter-degree Global Forecast System, or GFS data. That will be denoted with an L for large-scale data. So let's walk through how this IC blending works. We're going to start by interpolating both that large-scale and small-scale data down to the native MPAS 3-kilometer mesh. So here you can see the top line is that large-scale GFS data. It's been interpolated down to 3 kilometers, and that small-scale data from the ENKF is already at that 3 kilometers. From there, we're going to upscale the small-scale and that large-scale data. Essentially, you can upscale it as coarsely as you'd like until you get to your coarsest mesh. I'm only showing 3 here. But the way IC blending really shines is by calculating these perturbations that are shown here in these little green deltas. So an example is if we have a field on mesh 3 for the large-scale data, if we interpolate that back down to mesh 2, and we subtract the original L2 minus L3 on L2, essentially we're storing in that perturbation the difference in what was lost when we coarsen this data. So we're going to save in both the large scale and small scale data, what information is lost when we coarsen this data. And we're just going to hold on to those in those little green deltas. And now it's time to downscale and essentially combine and blend this data all back together. And we do that using specified weights. So an example weight distribution is shown here in the top right, where you have the different meshes that you specify on the left column going from 3 kilometers to 480 kilometers. And then your weight values range from 0 to 1, where 0 is that you're getting all of your information from your small scale data, and 1 is that you're getting all of your information from your large scale data. So if we start combining these back together at our coarsest mesh, that W value is going to be 1, so we're getting all of our information from the large scale data. But as you continue going through, we're going to add back in those deltas. So we're going to continue weighting the data, but then we're also going to bring back in that information that had been essentially lost, you can think of, at when we coarsen the data, all the way until we get back down to that 3 kilometer native MPAS mesh. And so why does this work? So blending those perturbations, so those deltas, store that scale-dependent information. And from there, they're weighted to tailor contributions from larger and small-scale information. So larger weights are assigned to the data sets that provide the large-scale fields for a given mesh and wavelength. So kind of the overall goal of this study in our group is to inform the development of the RFS version 2. Specifically, we want to ask, can we forego that partial cycling and just replace it with IC blending? So my goal this summer as part of the LaPenta internship, I had 2 research questions. First, are regional MPAS simulations sensitive to different blending weight distributions? And is there really a best weighting distribution? So to kind of give you a little more background about the simulations that I'm going to talk about today, they're regional MPAS simulations over CONUS. We have 5 initialization times at 0 UTC for 5 days in May of 2022 during the spring forecasting experiment. Those small-scale data, or regional ICs, are those 3-kilometer partially cycled ENKF analyses from the RFS DA system. And that large-scale data, or global ICs, are those quarter-degree GFS data. And so throughout the summer, I tested about 15 different weighting distributions, but I'm only going to show 5 here. Before I started this summer, the team was using the leftmost column here, the control weights, which will be shown in a black line in the following plots. And then essentially, as you go kind of from purple, red, blue to teal here, you're getting less global information included to more global information being included. So let's just kind of dive in. If we look at mid-levels, specifically 500 hectopascal U wind over CONUS, we look at bias, so those blending simulations from the weights on the previous slide, minus observations, which are RTMA data. You want a bias closer to 0 here. You're looking at 3 to 36 hours of forecast. Again, you can see that all the simulations are essentially following the same trajectory, the same forecast, but there are, just subtle differences. All of the lines aren't directly on top of each other. You can also look at that 500 hectopascal moisture, just noting the small y-axis, but we're seeing a bit more sensitivity here. And specifically, I want to draw your eye to that weights 14 line in the teal, especially at 21 hours. It really has a much lower bias than the rest of the simulations, likely because it's including the most global information. We can also look at low-level reflectivity, specifically east of the Rockies, looking at fraction skill score, going from 95th percentile on the left to 99th percentile on the right, where you want a higher fraction skill score is better. Again, we're seeing a lot of sensitivity. All of the lines aren't directly on top of each other. But one thing we really noticed looking at other metrics as well and other variables is this difference between weights 9 in the red and weights 14 in the teal. So weights 9 has the least global information, and weights 14 has the most global information. And you can see how they kind of flip-flop throughout all of the simulations. So there's definitely kind of something going on there that we're looking into. But it's likely due to the varying amounts of global information that they have. So kind of going back to those research questions, are regional MPAS simulations sensitive to these different blending weight distributions? Yes, hopefully I kind of proved that point, that you can see that all those lines aren't directly on top of each other. And is there a best weighting distribution? It's too early to say that for right now. We're currently doing some more research to determine which is necessary. And part of that we realized, why we can't really say that there's a best weighting distribution, is that our findings are kind of indicating that when we use these partially cycled small-scale data from the ENKF, so they're partially cycled on their own, twice daily, they're also getting GFS information. It's hard for us to tell actually what the blending is really doing, like how much is it really helping. So to kind of investigate this further, we ran some continuously cycled global MPAS simulations using a different DA scheme, but also the GFS blended ICs. And so we're just starting to look at this, but to kind of give you a teaser, looking at reflectivity again, those fraction skill scores like we saw before. The only difference here now is that on the green line, you're having only the small scale data, no blending. Orange line is only GFS data, no blending. You can see all of the different simulations essentially kind of fall in between that envelope, and we're definitely seeing that sensitivity. Greater sensitivity is what we saw, so that's good. Okay, and then we're just working on this for RFSV2. Thank you.
Okay, good morning, everyone. This work is a part of the WINGS PhD Dissertation Fellowship, which I received from NOAA WPO, and it's in collaboration with my PhD advisor, Dr. Anant Iyer, and my WINGS mentor, Dr. Christina Stan. And the title is Case Studies of the Monsoon Onset Vortex and Early Season Monsoon Features using the UFS coupled model. So a quick background and introduction of this particular phenomena. The Indian summer monsoon extends during the boreal summer months of June to September, and it is characterized by various semi-permanent synoptic features, which is mascarene high, which is a subtropical high pressure in the southern Indian Ocean, and the southeasterly trade winds from this mascarene high cross the equator to become southwesterlies, and at 850 HPA you have a strong low-level westerly to southwesterly jet stream known as the Somali jet or the Finlater's jet of the Horn of Africa. And you also have the tropical easterly jet, which is an upper level, upper tropospheric jet stream peaking around 150 to 200 millibar level, and it is a result of the outflow from the Tibetan high. So what exactly is this particular phenomena called the onset vortex of the monsoon? As shown in the previous slide, the monsoon is characterized by high vertical wind shear because of strong low-level westerlies and upper-level easterlies, and that's why during the core monsoon months of July and August, tropical cyclogenesis is not observed over the North Indian Ocean region. However, during the onset phase of the monsoon, which is a transition from pre-monsoon to monsoon season, that is in late May and early June, a vortex forms in the Arabian Sea, and it often has an intensity of a tropical depression or a tropical cyclone, and this is termed as the onset vortex of the monsoon. It is a synoptic scale feature, part of the large planetary scale monsoon circulation, and the infrared image here is from 2 years back. The onset vortex in the Arabian Sea went on to intensify into tropical cyclone Biparjoy. And it was one of the longest lived cyclones in the Arabian Sea, having a lifespan of, I think, more than 10 days. To give a much more broader context, this is a Hofmöller diagram of precipitation. So the y-axis is latitudes, and you can see that during the summer months, there is a sudden northward shift of the ITCZ or the advance of the monsoon precipitation, and the contours denote the zonal winds at 850 HPA. The orange dot is the median location when the onset vortex forms, which is in the first week of June. So the formation coincides with the rapid increase of zonal winds and seasonal northward shift of precipitation. We studied this particular phenomena for two important reasons. First is it affects the advance of the monsoon, so either it can bring in or set in the monsoon early, or if it intensifies into a strong tropical cyclone and moves away in a northwesterly direction towards the Arabian Peninsula, it can result in a drier start to the rainy season or a delayed start to the rainy season. And since most of these onset vortices become strong tropical cyclones, it is a coastal and maritime hazard as well, and many of these cases have become category 2 or category 3 to 4 equivalent hurricanes and have caused considerable damages as well. And no previous studies have focused on predictability of this particular phenomena and its impact on the subseasonal monsoon rainfall in short to medium range forecast of global models. And this is the research gap which I try to address through my research. The questions which I'll be addressing is, the Somali jet is one of the most studied aspect of the monsoon, and there is a well-established literature that stronger the jet, higher the rainfall over the west coast and central parts of India. So is this particular well-established phenomena captured well by the UFS? That's first thing which I'll be looking at, and then we'll be looking at few case studies of the onset vortex in 3 case studies from the UFS subseasonal to seasonal prototypes, and try to understand what possible thermodynamical factors are likely to affect the forecast, and how do these forecasts impact your early season monsoon rainfall. So the data I'm using is UFS S2S prototypes P5, P6, and P8. For validation purposes, the atmospheric fields are compared with ERA-5 analysis, the tracks of the onset vortex are compared with the JTWC best track data, and the rainfall is compared with GPM iMerge. So large-scale features of the monsoon. Your jet index is given by the mathematical definition highlighted in blue, and stronger the winds, higher the rainfall in the central parts of India and west coast of India. And also the Somali jet is also tied up with the formation of the onset vortex. So how well is this particular feature captured in the UFS? Here is a linear regression analysis. So the colors denote the anomalous increase in rainfall corresponding to 1 standard deviation increase in the jet index or the speed of the Somali jet. The time period I've considered is, each UFS run is 35-day run, so it's June 15 to July 19 during the 7-year period from 2011 to 2017. Black dashed lines denote regions which are statistically significant at 95% confidence level. And the main takeaway here is there are some subtle variations across each of the prototypes, but spatial pattern is overall captured well by the UFS prototypes, but the prototypes underestimate the rainfall amount corresponding to a stronger Somali jet. And then looking at the 3 cases, so these are the plots of the tracks of the 3 cases. So black line is the observed track from JTWC, blue is the track in P5, orange is the track in P6, and green is the track in P8. To cut long story short, 2015 case was captured the best by UFS across 3 prototypes. In particular, P8 captures the 2015 case really well when it comes to track and intensity. 2011 is not captured well, both in terms of track and intensity. Well, P6 has a reasonable track compared to observations, but the onset vortex forms much earlier in the UFS forecast compared to actual observations. Whereas 2014, P5 and P6 generate the vortex. P5 has a weak vortex, which is eventually advected eastwards by the low-level westerly winds. P6, the vortex forms southeast of the actual location, and P8 doesn't generate the vortex. So this is an interesting case, which I'll talk about in the next few slides. And possible mechanisms which could affect the forecast in the UFS. So my earlier studies have shown that the potential vorticity structure of this particular phenomena is governed largely by diabatic effects. So if these 2 fields are captured well or forecasted well, then the track and intensity of the onset vortex is likely to match closer to the observations. And this is exactly what we see, if you look in the last row, the black and green lines, the ERA 5 reanalysis and the prototype 8 forecast of the potential vorticity and diabatic heating profiles average 2 degrees from the storm center match closely with each other. So this could be one possible reason why the forecast turned out to be as close to observations. And the jet index has the highest correlation in 2014 and 2015 between the UFS and ERA 5. 2011, there is not much correlation, possibly due to role of initial conditions, because the forecast in 2011 were not matching with observations quite well. But in 2014, in spite of getting the large-scale background flow of the Somali jet index correct, the onset vortex doesn't form, so which indicates that while the accurate forecast of Somali jet index is necessary, but it is not a sufficient condition. And evolution of convection on a mesoscale to synoptic scale, if that is not captured well, then the forecast of the onset vortex is not captured well in spite of having correct background wind conditions. Lastly, looking at the impact of the forecast on the subseasonal rainfalls, the west coast of India is one of the wettest regions in the country, with the rainfall in June itself varying from 15 to 25 inches from north to south part of the west coast. This is a precipitation difference, so the blue shades highlight the regions where UFS has a higher rainfall compared to GPM IMERGE observations. And of course, the along the MOV track, the rainfall is maximized. But the main takeaway is, again, the bottom right panel, 2015 P8, if your track of the onset vortex and intensity is captured well, then overall rainfall difference or rainfall bias over the land region is the least. And this also has subseasonal impact. So, key takeaways is predicting both the evolution of convective features on a mesoscale to synoptic scale, as well as the background wind conditions, is essential. And in the context of the advance and onset of the monsoon, the onset vortex is like an extreme weather event, which can either bring in heavier rainfall or disrupt the rainfall. And the forecast of this particular feature have implications for early season monsoon rainfall. And the parameters which I've considered are the 850 HPA zonal wind and OLR. So these parameters are also used for calculating indices such as the monsoon intraseasonal oscillation or boreal summer intraseasonal oscillations. And those are for the wide region of entire South and East Asian monsoon as well. So if any particular feature which is focused over the Indian monsoon region is not captured well, then these can have implications even for forecast of these indices. And 2015 MOE is the best forecasted. 2011 case is not very well forecasted, and future work will focus more on more cases, ensemble runs, and additional metrics for evaluation. And I'd like to acknowledge NOAA, WPO, and UCAR for the WINGS Fellowship, as well as my PhD advisor and WINGS mentor and PhD advisory committee, and my UCAR mentors as well. Thank you.
Great. Good morning, everyone. My name is Anna Glodzik. I am a second-year graduate student at the University at Albany, and today I will be talking about how we're evaluating the UFS heat and moisture fluxes using eddy covariance observations from the New York State Mesonet. So this is part of a bigger project in which we are aiming to advance coupling evaluation metrics in MET+ for UFS land surface models. And my role in this project is to use the New York State Mesonet Flux Network observations to evaluate the UFS HR forecast model. So up until this point, a majority of my work focused on the quality control of the flux data, which needed to be done before making any of those comparisons with the HR model, and then also an evaluation of how well the network was closing the energy budget across New York State. And then once that work was done, I was able to jump into the comparisons of both the standard site and the flux site variables to identify where the HR model how the HR model was calculating these fluxes, and also some more process-based variables like the Bowen ratio across different sites and also seasonally and diurnally. And this will help us diagnose where energy exchange deviates between the observations and the model. So for those of you who may not be familiar, the New York State Mesonet is now 127 weather stations across New York State that measure standard meteorological variables in addition to solar radiation, soil temperature, moisture, and snow depth. So that map on the left, the standard sites are the black circles, and there's also a few sub-networks shown, such as the snow network in blue, the flux network in green, and the profiler in red. And so the Flux network began in 2018, and we currently have 100+ site years of 30-minute flux data across those 18 sites. And the Mesonet is operated by the University at Albany, where we collect and archive this data every 5 minutes. So this schematic kind of shows my role in this project from the data all the way through the analysis. So like I mentioned, we're using the Mesonet data, which is quality controlled, which I will get more into later, as well as the coupled UFS model output. The evaluation metrics for land surface model processes that we're using are standard variables such as temperature and humidity, but then also things like the Bowen ratio, which are driven by those turbulent fluxes. And then that leads us to the analysis, which basically composes of the HR model comparisons with the observations. And today I will be focusing on time series and diurnal analysis, but MET+ use cases would also fall into this analysis category. So this is an example flux site. This is the Chazy flux site. And I'm just going to point out some important instrumentation. So these flux sites measure all the components of the energy budget. So the radiation components measured by the net radiometer. For soil heat flux, we have 4 soil heat flux plates at the base of every tower, and then we're using that eddy-covariance system to calculate the turbulent fluxes. And these turbulent sensors measure at 10 Hertz. So like I mentioned, we needed to quality control this flux data before we could do any comparisons with the model. So this included a QC flag that was included in the data sets for each flux reading, and this was a value of 1 through 9, 1 through 3 being the best, anything above 7, not recommended for use. And this is based on a series of 3 tests that are carried out by the data logger. In addition to this, I created my own despiking algorithm, which is flags any variables outside of that variable specific threshold, as well as a manual quality assurance where we're just looking at the time series of variables and flagging any times which are not reasonable. So I combined this quality controlled flux data, which is 30-minute resolution, with the 5-minute standard site data to create these comprehensive data sets which allow for easy analysis and comparison with the HR model. And like I mentioned, we also wanted to see how well the network was closing the energy budget. So using these quality control parameters, we were able to get an average of 72% closure across New York State. For the model side of things, I'm using the UFS HR model prototype runs. These are 16-day, 3-hourly forecasts, and the one that I'm specifically focusing on today was initialized July 19th, 2020. So moving on to the analysis, I did all this analysis for the 18 flux sites, but I'm just going to be focusing, for the sake of time, on Belleville, which is a grassy field located right there in New York. So the first comparison that I did was looking at the sensible heat flux as well as the variables that influence the sensible heat flux. So the left-hand column of that plot is the 16-day forecast, time series of that, and then on the right is the diurnal averages over just the first 3 days of that forecast, so before there's any drifting in the model. The first row is the 2-meter temperature. The mesonet is shown in blue, and the model is shown in orange. And as you can see, the model is underestimating the 2-meter temperature. For soil temperature, the model has depth levels of 0 centimeters right at the surface and 10 centimeters, while the New York State Mesonet temperature probes are at 5 centimeters. So I plotted both the surface and 10 centimeter depths in the model to kind of get a comparison with where the Mesonet would line up. But you can see, especially on that right-hand side, that the soil temperature is underestimated at both these depth levels when compared to observations. And this is really important because the difference in the air temperature and the subsurface temperature is what is the main driver of the value of the sensible heat flux. So this difference between these two temperatures was smaller in the model than in the observations. So by way of the sensible heat flux equation, this would lead to underestimated sensible heat, which was in fact shown there in the model versus observations in the final row. I also looked at the latent heat flux and soil moisture. So again, looking at the 0 centimeter depth and the 10 centimeter depth versus the observations, and you can see a pretty large overestimation of soil moisture at both of these depths. And this is a little problematic because the higher soil moisture allows for more energy for evapotranspiration rather than warming the air, which would lead to higher latent values than sensible values. But as you can see, when we're comparing the latent heat flux values, the model actually looks like it's doing a pretty good job of capturing the magnitude. So this leads us to wonder if there's some issue in the partitioning of the energy between the two turbulent fluxes. And then just honing back in on the soil moisture issue that we were seeing in the last slide, we hypothesized that it was potentially just a dry year, and that was making it a little bit difficult for the model to get those really low soil moisture values. So what I did was I looked at 2020 versus all the other available years from the Mesonet data for July and August, and kind of see where the soil moisture in 2020 aligned with those other years. And as you can see, especially during that center period, which is during the model forecast, the 2020 was one of the drier years, and we did this for all the sites, and it was consistently lower across all of the 15 non-urban sites that we looked at. So pulling this all together with the Bowen ratio, like I mentioned, the latent heat flux actually looks like it's doing a pretty good job, while the sensible is being underestimated, leading us to believe the partition of energy between the turbulent fluxes may be incorrect, attributing to more latent than sensible, and that can be reflected in the underestimation of the Bowen ratio by the model during daytime hours, which you can see in the bottom right panel. And so going into future work, we definitely want to dive more into this issue and what is driving that, as well as perhaps looking at some different model runs initialized at different times to get more of a seasonal analysis. And then also, this was only one model run, so we want to update the model run with a new initialization time every 3 days for better agreement over time. Thank you.
So good.
10 minutes for questions.
Yeah. Online, I don't know if there are any questions online, if anyone wants to line up. Great. Let's start with John with our online question.
Yeah, so, hello? Is this on? Yeah, there it goes. It looks like there's a question and a comment, both for Shreyas. The first one's a clarification. What was the resolution of P6, P7, and P8?
All the prototypes are quarter degree resolution, so 0.25 degrees.
Okay, thanks. And then the other one, it seems like there's a comment. Even IMERG, so iMerge, underestimates western GAT orographic rains in monsoon. Is there anything you'd like to say about that?
For at least these 3 cases, we verified the satellite imagery with the actual rainfall as well. So wherever there was deep convection, there was good rainfall. there could be subtle variations between, actually ground stations and iMerge, but overall we were looking at the large scale picture of, because the actual rainfall itself is very heavy. So we are looking at the large scale picture and relationship between the Somali jet wind speed and the total accumulated precipitation.
Thanks.
Yeah, let's go over there. Should just turn on.
I have a question for Mackenzie. Cool. So you were blending the GFS, which uses FE3, and obviously the regional was MPAS. Did you see any issues with using the two different die cores for the blending?
That's a great question. We have not looked into that yet. So I think, yeah, we could try to isolate that a little further. Yeah. Mm-hmm.
Let's go over to this side. Okay, go ahead.
Whatever works. So great talk, guys. So I have a question for Mackenzie. So have you thought about the implications of the weights that are chosen? For an example, like if it's a 50-50 blend, it's like saying that, hey, I'm equally unconfident about two sources of information. So have you thought about like the implications of the weights you've chosen? Is there a philosophy that drives your choices?
Yeah, that's what we tried to kind of start looking at this summer, seeing how sensitive things are really just kind of on some guesses of some different weighting distributions. I think we have a hypothesis that it's probably the best distributions to use are probably based on weather regimes. So that's like different weather regimes might require different weighting distribution schemes. So that's something we'd like to pursue in the future and kind of look at. Yeah.
Got it. Thank you.
Mm-hmm.
All right, go for it.
Actually, I want to say the same thing. Really great presentations, really interesting work. The question is for Anna. I'm really curious, did you look at the radiation components in your study? Because it seems like, there's big issues there.
So I actually just did that this week. So TBD on that, but yeah, that's kind of our next step, basically.
Very good, thank you.
I have a question for Rowan. You mentioned that you had issues with running the containerized version of SRW, is that correct? And if you could expound a little bit more on some of those challenges that you faced?
Yeah, absolutely. So for the containerized tutorial, which was released recently I'm going to back off the mic a little bit, for the v3.0.0, it listed 4 prerequisites, and I'm not remembering off the top of my head, it was 2 compilers, Recodo, and one other piece of software I'm not remembering. The issue was I set up a new cloud instance, I got those prerequisites, and I went to run the model, and it was missing additional software that it needed to actually successfully perform a model run. It was something that I think, given time, I could have figured out, but I imagine, first of all, 10 weeks obviously made it a little bit of a time constraint where I wasn't able to do that. And I imagine if you're having a user who's inexperienced, who doesn't have outside support using it, and they run into, an issue where they have additional prerequisites they have to figure out, that would be a barrier to entry. Yeah.
Thank you.
Mike.
Oh, great. Thank you very much. Back to Anne. Great study. I'm a big advocate for use of mesonets, especially the New York State mesonet. I'm curious, what are your thoughts on extending the work that you have to other mesonets and other networks? I'm thinking regionally, nationally, globally, because there's a lot of stuff we could leverage for improving our models globally.
Yeah, that is something we have talked about. I think that would be great. Obviously, New York State only is a small subset of the United States. We have done a little bit with some of like the Ameriflux sites, so maybe including that, and like the Harvard Forest site is a site that we've worked with the energy budget stuff. So definitely something we want to broaden.
Yeah, thank you.
Yeah, again. So I have a question for Michael. That's a very, very interesting study you've presented, and it's actually not easy at all. So congrats on making it this far into this study. One thing I have a question for you is that did you look into like systematic biases in the unobserved variables? Because in my experience, whenever we assimilate any observation where there's a systematic bias, that translates into a systematic bias in the model, unobserved variables, and that can cause some fairly entertaining bad results. So did you see any indicators of that?
So when it comes to running the model, like that's a whole aspect to it because you're using, EMC products. Most of it has been already developed. So pretty much of what I've done so far is, using what has been already, being developed already, right? So in terms of like, systematic, when it comes to, the system itself, making certain, changes or anything like that, we haven't got into those things because obviously like it's just been a couple of months into the work. So I'm sure maybe probably in the future when we advance in the project, we might probably consider, certain things when it comes to like the baseline of, the entire model.
Yeah. Okay, Nikki, I really strongly recommend you look at the unobserved variables. Just look at like what the time averaged analysis increments look like. You might see some fairly weird biases show up, and that's something to think on in the future. Yeah.
Yeah, I mean, of course, like, time constraint for the presentation, so of course you couldn't.
No problem. We understand. We understand. Don't worry. We understand that. I'm
Yeah, I
just
appreciate
saying,
that.
The next year or so.
Yeah, so I also have a question for Michael. First of all 5 of you, great presentations, of course. So Michael, it's so using a 3D VAR, which is a fixed covariance, and you only have AOD, two-dimensional field. That is just. Wouldn't it be much better to use an ensemble to get time varying covariances? Because I think that must be one of the big issues.
Yeah, when it comes to the DA method, it's pretty hard to make your own choice because there's a system that has already been made, which is currently EMs when it comes to aerosols, they use 3D VAR. I mean, 3D I've got when it comes to aerosol DA. So when it comes to the method, it was a little bit of a challenge when it comes to our selection. So for now, of course, we can only use what they have right now, and then work on that. But of course, when probably in the future when there are further developments with that, then definitely we can maybe look at different methods. Yeah.
All right, we've got a few more minutes. Any online questions? Any other thoughts? We have a question here. Oh, Tracy, do you want to ask? Okay, I don't know which one you want. Okay. So this is a question I think I asked last year to our students as well, but this is for the whole panel. How do you describe what you do to your friends when they ask you? Anyone can start.
I mean, I just say I do stuff with weather models. I don't think most of my friends would be interested in hearing the exact details of what I do, but I say I do severe weather stuff. I work with weather models. So yeah.
I'm trying to be God, but but anyway, I mean, of course, like I just try to let them know, I'm just working on the atmosphere all the time. Of course, when you go to too much details, they feel like you're talking too much about things that are maybe absurd or maybe abstract. So yeah, trying to make it basic all the time, just to let them know I'm working on aerosols, things in the atmosphere all the time. Yeah.
Yeah, for this past summer, I usually just say I work on improving weather models, but like PhD work, I usually just say I study Colorado weather.
Well, I would say I'm working on something which could help bridge the gap between theory and prediction, and then also help in understanding a particular phenomena more from a scientific perspective as well as from a prediction point of view.
Sorry. I improve the quality of the data from weather stations across New York, and I use that to hopefully make the forecasts better.
I love it. Thank you all. Everyone take notes of how to communicate to your peers. That's great. And we're done. We are going to let Shira take over.
All right, y'all, we're gonna let you out for a break. Quick note though, we're gonna be using the, I guess, left to me, but right to you side of the room for the next student parallel session, which starts in about 5 minutes. So you guys have a really fast break. But everybody who's in that side of the room, please leave so that we can close the partition and start the student session over there. Thank you so much. UFS Community Social Science Survey results to be delivered to us by Allison Gregory and Hannah Love. Take it away.
Hi, those of you who can hear me out in the lobby, please come in. We have cool pictures. Okay, can you hear me if I stand? I don't want to stand so close. Okay. Hi, everyone. I'm Allison Gregory. A lot of you may have remembered my presentation last year where we talked about our community and how we weren't sure what it looks like. Last winter, I administered a survey with the help of my colleague here, and so we're going to share some of the results of that survey. So here's a little brief intro of us. I had a life change since last time I was here, but I am the community engagement specialist for the UFS. My background is in social network analysis, which is what we're going to look at today. And I had the pleasure to work with my esteemed colleague, Dr. Hannah Love, and she helps teams, science teams particularly, collaborate better. So she's a professional facilitator, and I'm really excited to have her here with me. Do you want to say anything else?
I think you got it. That's
Great.
perfect.
I'm glad you're here. Okay, so where are we? So this is what we talked about last year, that we kind of need a plan and in order to better study our community. So as you can see, we're convening. We are here. We are collaborating. We are convening. And today we are going to talk about how we can better measure our engagement as well. So let's get to it. Okay, so last year I told you guys that based on my understanding, we thought that the community looked like this. And I said that that's kind of hard to study, hard to measure, and therefore hard to understand how we are going to improve. But today we're going to talk about how our network actually looks a lot like this. But we're not ready for that yet. So Hannah, will you tell us about social network analysis?
Yeah, so just show of hands, who knows what social network analysis is? Like when you saw that diagram up there, do we have, like, what's my level of familiarity with it? Like, hands up if you've seen diagrams like that before. Okay, hands up if you're like, if you said run a social network analysis, I got you. Like, I got your back. Okay, good. So for most of us, this is new and a little different. So we're going to talk about what social network analysis is, how to use it, and then the key thing is how do you put it into practice? Like, what does this mean for you? What does this mean for your organization? So essentially, it's a tool to visually represent relationships and how they grow over time. I like to explain it by thinking about what are other questions you might ask that you could use social network analysis for. So one I ask a lot is, how does a team catalyze once they have funding? So when they start, before they have money, a lot of times it's just like isolates, like the nodes in this network are not connected. And then after funding, maybe a year, 2 years, what does the team look like? We also do a lot of learning networks. So in a classroom, what do they look like at the start of the semester and what do they look like at the end of the semester? And these are all questions that you might ask to study the network or the social network, do social network analysis.
Yeah, and so I decided for all of us here, this would be particularly useful because what we talked about last year was how we were a community of practice, if any of you remember that, and that's because we have a lot of stakeholder groups doing a lot of different things. We have a common interest, but it's not exactly a specifically honed in common interest, and we're all trying to share a common knowledge with one another. So that key thing is informally bound, which makes it really easy for really difficult for us to communicate with one another, so we want to be able to kind of look at it visually and get a different perspective.
So we're going to walk through a lot of these diagrams today. So I want to briefly explain what you're seeing. Each circle, it's called a node, and it represents a person. So this is a person who took the survey in the network.
Yes.
I don't have the clicker.
Oh, sorry. I agree.
Each of these nodes are going to be a different color, and we'll let you know what those colors represent. So somewhere on the network, you'll see a legend like this one. And then each of the diagram is connected with what we call edges. You can just call them lines. Again, there's always jargon, and I try to give people tools and words to overcome the jargon. So circles, lines, they're actually nodes and edges. Whatever you want to call them, I will follow you. And in these diagrams, each person, so each node, completed a survey. And they said, these are the people I'm connected to. So it's everybody self-reporting who they are connected to. And so if I said I go to Allie for advice, then I'm going to have an arrow connecting myself to Allie. If Allie also comes to me for advice, the arrow is going to be double-headed and go both directions. I'm not going to go into detail by this, but the nodes have different sizes. In these diagrams, they're sized by degree. So if I say that I go to advice to 4 people and 4 people say they come to me for advice, my node is going to be bigger than somebody who only goes to 2 people for advice and maybe 2 people go to them for advice. So the more action a node is getting, the bigger it's going to be. We find they're easier to look at. It's easier to tune in and see where the action is. Okay, how not to put these into practice. Don't spend this whole presentation trying to figure out where you are. You're probably wrong. I do a lot of these. You're probably wrong. Don't change your whole program based on a few network diagrams. Think more broadly than that, right? Like, these are some ideas. This is what we're seeing, but don't go out and do like a whole program overhaul. Don't force people to be friends. I get asked this a lot. Are you going to make us do a trust fall? No. I'm not going to force you to be friends. I'm not going to force you to do happy hour. I'm not going to force you to interact. But I am going to give you some tips to think about how to engage new people, invite new people, and be strategic about it.
Okay, so some things we want to preface here is when I initially sent this survey, I sent it out to all of the members of this community who are on the open steering committee meeting, which I understand if that's not you, if you don't attend those meetings, do not be offended that you are not included in the survey. We do have plans to expand further. So the other thing is we used a snowball sampling method, which you might not be familiar if you don't know about social science, but that is where if you took the survey, you list your 5 closest colleagues, and then those colleagues receive the survey as well. So it's called a snowball because it keeps building on itself. And the reason we do this that's so important for this network is because we do not know exactly who is in this network. We know that you have colleagues that you work with and you kind of get an idea of what labs are doing what, but it's not a closed network. We can't catch everyone, right? Who's on GitHub in the back end, in their basement, running UFS code. Hendrik hopes it's a lot of people, but I don't know if that's the case. But so that's why you'll see this network kind of fingering outward into the abyss, is because it could go on forever and we had to stop it eventually. So anything else on methods?
Yeah, I'll just add real quickly that a limitation of all social network analysis is it's typically not dynamic. We're capturing one time point. So if you weren't here yet, if you left this job, came to this job, students graduate, networks change. So this is what we captured in the few months the survey was open earlier this year.
Yes. Okay, so here's a little bit of the boring demographics. 80 people responded to our survey, which is great for us. That's about a 30% response rate, which in the social network analysis world is pretty good. And that's 212 people in our network, so that will also be dots or nodes in our network. And so those are people who took the survey and also people they listed who didn't take the survey. So because of the way we sent out the survey, 65% of the respondents attended the steering committee at least sometimes, and 53% of respondents are members of the working group or the cross-cutting teams, so they're very closely embedded in the UFS work. And additionally, some other demographics, 88% of respondents are mid-career or later, and 97% of respondents have a PhD or a master's degree, so good job everyone. We're a very smart community, but maybe we can think of other ways to expand our reach in those ways. Okay, so edges, what we talked about as lines between each other. In the survey, we asked people, who do you work with? And so once you listed your 5 colleagues, you told us what you did with them. So either you attend the same meetings with them, you work with them one-on-one, or you collaborated on a specific research project or a presentation together. So today, very exciting. Another thing I want to say is that we can get so many results from all of the things we collected, and we are choosing to show you just a few of our high-level summaries, but there is just so much more that we could look at that we don't have time to look at. So first is homogeneity, so who is in our network and who is working closely with this code. Code users and non-code users, we have both of them in our network, and how do those people look? And also working relationships, we saw that those are 3 different kinds of ways you work with people, but there are other ways you can collaborate with people. Are you getting advice from people, or are you learning from people? So those are the 3 things we're going to look at today.
All right, so let's start to really dive in. So friendly reminder, each circle is a person. Each line or edge reports a connection of how those people work together. So they might have said all 3 on this network. They might have said, like, we're attending meetings together, we're working together, right? All 3 of those things that Ali just shared. They might have just shared one, and we chose, for a lot of reasons I'm not going into, not to weight those. So I want to hear from you all. When you first look at this, what are things you observe? And I can run the mic over to you.
Or you can shout it out, and I'll repeat for the...
There's a lot of pink. Yellow's on the outside. NOAA-centric, it's either, and then contractors and feds. Can you say that? They're the bridge? They're bridging some of the people. Yeah, they are. Yeah. Overall, this is a pretty healthy network. If you, in network analysis, we talk about what would happen if you remove one node. And if you remove one node, even if it's a very central node, this network would retain its same shape and same structure. So in general, we have a pretty healthy network. But we also like to highlight places that a network can improve. And so one place Ali and I have talked about is there's kind of a hole in the center. And so one place is like, what would go there? Or like, who's there? And we don't know if these are non-respondents, if they're people that just didn't get the survey. Maybe the center of this network's not well connected. We don't really know. But we did really observe there's a hole in the center. There are also a lot of people on the outside that are only connected via one person. So if you'd lose this one person in several instances, you'd lose a lot of people in the network. They would become disconnected. They'd no longer be attached.
That one is pretty good. Is that what you got there?
Yeah.
Okay.
All right, so I created this network, so I will take ownership of this. I looked at who had a NOAA email address and who had a non-NOAA email address. Ali gave me some free reign, and I was looking at it, and I was like, that's kind of interesting. Like, why do people have it and not have it? And so this is the network that is a result of just the email addresses. Yes, there are methodological flaws of looking at it that way, but that was the data I had as an outsider, and I thought it was kind of interesting. So I'm going to spend a few moments talking about it. Literature says when we want to complete a task really quickly, you want a network that has a lot of homophily, meaning everybody is about the same, and you can do it really quickly. But if you want to create what we call knowledge networks, where you're doing breakthrough science, where we talk about solving complex global problems, creating new and innovative solutions, you want networks that have more heterogeneity. And that might mean people of different disciplines. For me, as a team scientist, that usually means different disciplines. We're looking at unique methods and unique ways to solve problems. And so in this network, I kind of question a little bit if that is more homophily or more heterogeneity. And so we see a lot of NOAA centered at the middle, and then a lot of non-NOAA centered towards the outside. And when I was thinking about this, I I was thinking about how we talked to a lot of teams about like, well, what is unique and like how do you bring that heterogeneity into your team? How do you integrate and infuse that new knowledge? And I think the easiest place to see it is when people bring in new postdocs. And so often when I'm working with a team and they hire a new postdoc, they come up to me and they say, oh my gosh, this new postdoc has this new way of doing things. A lot of time it's data. Like, this postdoc is looking at this data differently and it's gonna make us so much faster. Like, can you believe it? And I'm like, yeah, that's so cool. Like, isn't that great how that happens? And when we add new people or do those little infusions, so often that's where new knowledge can really spark.
The other thing I want to add about this network, because particularly in this group, we spend a lot of time talking about how do we engage with the community? How do we make sure we're including more people, not just NOAA? How do we make sure we include students? And so I just wanted you guys to visually look at this and see these green dots being our non-NOAA people. Maybe it's someone at a university, maybe it's an independent contractor or someone in industry, but I want you to think about what it's like to be them when we have these conversations that's like, how do we make sure we're engaging with the community? Oh, that guy, he's the one outside the community, let's talk to him, and how that kind of pressure can build on them when you see really how few and far between they actually are in this network.
So this is the same network that we've been looking at, right? The same 3 questions. We asked more questions, we'll show them later, but we wanted to really lay this as the foundation. So we asked, how familiar are you with the UFS code base and related applications? And so we've got a lot of people throughout the center of the graph who are extremely familiar, moderately familiar, and somewhat familiar. And these are our shades of pink. And then we kind of have this cluster of green at the top that's not familiar and slightly familiar with the code. So those are things I observe. What are some things that you observe from this network? Is there anything else that I'm missing? We're going to talk more about that. Yes, but we're not sure. I'm going to ask you, it becomes more apparent in the next diagram, so we're going to keep bringing that up. Yeah, you know, we like to think of, like, when we're thinking about practical ways to improve the network, those people to get to the center of the network would essentially have to go through a lot of people or send an email to somebody they don't know. And in some ways, that's highly efficient. And in some ways, if they need access to the center, it's a long ways to get there. And I never know what's best for a team, but I do know that there are differences and teams need to think about which one's best for them.
And the other thing I would add about this network is, in general, the word familiar. Obviously, this was a survey you took by yourself, so we wouldn't know what you exactly intended by saying that you were familiar with the code. But something I want us to think about as a community as a whole is how important is it that our community is familiar with the code? Do we want the people who are on the steering committee to be very familiar with the code, or is it okay if they're not that familiar with the code? So just something to think about.
So same network diagram. How often do you run the UFS code or associated applications? So here green is very often, sometimes, and then our pink colors are the rarely, never, and NA. So like it's not applicable to somebody's job would be NA, and then white is no response. So let's show that line.
Let's.
I think of social network analysis as inherently mixed methods because there's a lot that I can learn from the data. There's a lot that I can learn from what the client gave me. But so often I find things like this that, I don't know your name, that you previously observed that I can't really explain. And I've run a lot of data, looked at a lot of attributes, and I'm wondering if you all have any hypotheses of why there's this line. Why are some people not running the code frequently at all, and some people are running it a lot? And do you have an idea?
I mean, the NA is the hard part. It looks like that one NA node that has a lot of weight on it is connected to all of that green, and if that person wasn't there, it might be a little, but I don't know what NA means. Oh, so they're just a connector. So that person's probably pretty important.
Yeah, we might call this person a bridger or a broker. Yeah. Other hypotheses. There's no wrong answer.
So I want to start off by saying I'm not a social scientist, so I'm just spitballing here. But I'm thinking it could be a divide between kind of what your role is. So if you're more of a management or leadership versus a developer, or maybe even some sort of temp hire. I know we just talked about that a little bit earlier. Just kind of my thoughts.
Model development doesn't mean just writing code. It means model evaluation, and have way more people evaluating the model than people writing code.
I see a hand over here, and as I travel, there's no right or wrong. There's no right or wrong to why the divide happens, but I think it's important to know as you operate that there is a divide.
So can you remind us again how you do the graphic? So why are the dots where they are? Why do you call it why is there a hole in the middle? I can redraw this and there's no hole.
So this is not the type of network analysis I do, but I go to conferences where I sit next to these people and talk to them. There are certain algorithms that are designed that place these nodes. And so you select an algorithm. They're also standard ones. So this is an incredibly standard, this is like the most standard, the most basic algorithm to place them. And they take a lot of things into consideration when they're doing this, but a lot of it's like how closely connected they are, how these connections fall. Usually the people that do this are mathematicians and statisticians, and I love sitting next to them. I learned so much. I also learned that it's not my field. That's not my area.
I do have a question, maybe not directly related to this phenomenon, but can you actually show previous network and this network? In my opinion, many nodes that are familiar with the code should either run or constantly using it. But I noticed maybe some node here never runs the node, but very familiar with the nodes. That's something I couldn't figure out. So have you done any joint analysis of those network before?
We have a slide at the end where we look at all three of those questions because we think that's very fascinating, that who's running it, who's familiar with it, and who's using it are not the same people.
And that goes back to what I said about being familiar. What does that actually mean when people are filling out this survey, of course?
Just something came to me is that evolution of this network in time could be very important. Because if I'm a PhD student today, I'm compiling, working with the code a lot. Next year, I'm running the code. The year after, you're evaluating the code. So I feel like looking at the time evolution could be also nice.
Yeah, that's helpful. Thank you.
You were speaking to my heart because I think social network analysis is best longitudinal because you can compare how the graphs or how the diagrams change over time. Let's do this last one and then we'll go to the next one.
I wasn't just standing there. That's okay. I want to go back to something that Christina just said. And I've worked with a number of people like in the weather and climate community, Tim Palmer, who's a big name in climate change, Julia Slingo, she's the former chief scientist at the Met Office, Tom Hamill used to be NOAA. Anyway, and Christian Jakob is another person in the international community. They say that we need more developers. We need more developers. I mean, we definitely want the models to be used, but we also need people that lift up the hood and work on improving the models as well. So it's one thing to run the UFS applications. Great, we want to do that. But we really need people to be involved in lifting the hood, making the changes to improve things.
What a lovely segue.
There we go. Okay, thank you.
You have anything about? I mean, I don't have anything specific. Just maybe we can just jump to the.
Oh
no, it's not.
Yeah.
It's at the end.
Yeah. So this is our last one where we talk about the
coders versus non-coders. I guess you could call it.
How often do you contribute to the UFS code? And so same network diagram, different attributes. laid on top. And so again, just one more way to look at it and highlighting that who's familiar with the code, who's contributing, and who's running it are different people. And maybe that's okay. We found it to be quite interesting.
Yeah, and I think that's something I encourage all of you to think about and talk to me about later, is, what does that mean and how important is that to us? Okay.
5 minutes. Okay.
5 minutes. Okay.
All right, so we asked other network questions. And this is really where there's an opportunity that if you want to dive into this more, you can contact us. We're happy to talk more about it. So often we measure metrics in terms of publications, citations, invention patents. I get this all the time. But when we're actually looking at, I study teams. So when we look at teams, groups of people, we actually need to think about, well, how are they developing? What processes are they engaging in? And then what do their outcomes look like? And I frequently use advice and learning networks as outcome metrics of how the team performed. Because ultimately, if we want a team to be creating new knowledge and to be innovating, everybody on the team either needs to be getting advice from somebody or sharing advice with somebody. So the network on the left is the network you've been seeing. And the network on the right is the advice network. So we asked, who do you go to for advice? And we didn't ask personally, professionally. We leave this open to interpretation. I find that academics often conflate the two. I can go into a lot of stories about this, which is why we leave it open-ended. And so things that we can observe in this diagram are a bigger hole in the middle. And I think there's a real opportunity here to think about who's in the middle, how do you bridge the middle, why is there a hole in the middle? I don't frequently see that many holes in the middle, and so that's kind of a unique feature of this. And I think maybe it's a methodological thing if people didn't complete the survey, which is why more time points could potentially be interesting. But thinking about if you bridge the middle, it would really change people's paths to get advice and to get information. And potentially it would help bridge the line that we saw previously. So this is the last diagram we're going to show, is the learning network. And for me, a learning network is probably the most important network, because I would like to think that everybody is learning from everybody else. So in this network, we actually see the hole in the middle bridged, and so that felt really good to me. We also see a lot of arms kind of like rolling around the outside, and we've seen that in a lot of diagrams. I'm just kind of pointing it out now so I don't overload everyone with information. That's a characteristic of a young network. We see those in networks that are still forming and still developing. And so we see these arms coming through, which really shows me that there's a lot of potential for growth and that this is a growing and evolving network. So as we kind of wrap up here, I want to offer a friendly reminder that is, when we're growing networks, when we're talking about practical ways to grow them, we're not saying 100% participation, 100% engagement, 100% of the time. We call that burnout. So please don't look at these and interpret them and say like, oh my gosh, we need everybody involved in everything. That's not the message. It's about how do you strategically engage the right people to add to your knowledge network, to learn more, to bring the right people onto your team or into your group to really have innovation, new ideas, fresh things coming in. So I'm going to pass back to you.
Thank you. And yeah, so this is just, I did a bad job and didn't put a key on this one. But the green means you filled out the survey and purple you did not. So I just wanted to show you guys where there is room for improvement on our side, on the methods side, to get more survey responses. And also looking forward, I know all of you are at this workshop, so including all of the workshop attendees in a survey in the future or everyone on the mailing list, that's a much larger network and a much heavier lift, but those are things we're thinking about in the future. And then I am just going to overwhelm you and put all these up at once. That I was hired to be the community engagement specialist for this network. And it was kind of a black hole. We didn't really know where to start, but I'm excited to say that this methodology is a great tool to help us kind of work in the direction we want to go in. And so from what we looked at today, the homogeneous network that we have, a great thing would be is if we want to expand that to involve more stakeholder groups, not necessarily more people, but more groups, and ensure that they're all represented. And as you can see, there are actual metrics that we can give you real numbers behind to see the improvement, and also connecting those code users and non-code users, and ensuring that the working relationships we do have are the working relationships that we want, and if they're not, how can we change that? And so a lot of exciting metrics moving forward. That's all I got. Come find me, because we don't have time for questions, so, write them down and come find us.
Thank you so much, guys. That was really interesting. Next up, we're going to hear from the UFS Coastal Project. And we have a few speakers that were added last minute, so I'm not sure who's going first. I am going to hand it to Saeed Mogimi.
Good morning. I'm Saeed Moghimi from National Ocean Services, Office of Coast Survey. Just give a brief introduction of myself here. I'm leading leading a storm surge modeling team. We are the guys guilty for stuffs, surge and tide operational forecast system. We do the development and also operationalization on NOAA supercomputer. I am also having another hat, and I'm leading also UFS Coastal scientific and technical lead at National Ocean Services, and that's basically why I'm here today. So today I'm going to call on two other colleagues to join me for the panel. Dr. Ed Myers, please, and Dr. Ufuk Turunkoglu, please. So meanwhile, my colleagues are joining here. I just want to also mention that the structure of the presentation today is that I'm going to ask my colleagues also here to introduce themselves, maybe for 2 or 3 minutes. Just take your time and talk about your role. We have Ed here more from a leadership side, and then also Ufuk from more development. So Ed, why not you take some time and introduce yourself?
Yeah, good morning. Yeah, thank you very much. I'm really pleased to be part of this discussion this morning. Ed Myers, I'm currently in a detail role leading a team within the National Ocean Service called the Modeling and Prediction Team. And this is a really critical team to NOS as we're working together to coordinate and strategize all the modeling across the National Ocean Service. And as part of this modeling and prediction team, a couple of really key strategies have been put forward and documented in both a vision statement for NOS modeling, a strategy statement, and a modeling implementation plan. And part of the implementation plan is, as Mark Ostler pointed out this morning, looking how best to consolidate modeling across NOS, and also how to really strategize the coordination of all the coastal models and the different types of models that NOS provides. And one really key component of the implementation plan is the UFS and EPIC. So I'm really pleased to be here this week, and because UFS and EPIC is really fundamental to how we move forward with modeling across NOS. And what Saeed is going to be talking about today, the UFS Coastal, is really a cornerstone of how we move forward on this front. And it's really critical to have this community working together, and really pleased to be working with Ufuk and the NCAR ESMF team and the modeling team within NOAA and academia, because we're working all together really important advancements are being made in terms of this next generation capability for NOS modeling. And I really appreciate, I know, Saeed, you always really emphasize the word partnership in the work that we do with the community, because really we're sitting down with UFUC and many of the folks here in the room on a weekly basis, meeting several times a week with the community and sitting down side by side, and we're working through these issues. So there's a great appreciation from all of us in terms of how we work together. And so anyway, I'll stop here and hand it over to I think UFUC.
Thank you, Ed.
First of all, I would like to thank you to have an opportunity in here to talk. Since I joined NCAR in 2019, I started working with the UFS weather model in different projects. For example, I start with the UFS S2S project, and then I work with the HAVS, and then now I am working with the UFS Coastal. So my impression is that I am seeing lots of difference between different projects. There are lots of similarities, but each of those different projects or different applications has its own way to do different things. So they need different requirements, they are using different components, they are using different code, sometimes different workflows. It's getting more complicated. But at the end of the day, they are trying to achieve the same thing, being some kinds of an operational product, creating some kinds of an operational product, but for different purposes. But all of them is using the same code base. And I think this is a great achievement in terms of using the same code base for different applications, since I am seeing lots of divergence over there. So yeah, I am working at NCAR as a part of ESMF team, as an application developer. Then yeah, if you, I think, yeah.
So we are going to proceed with this presentation. I am planning to have maybe 15 to hopefully less than 20 minutes, and then we are going to have some time also for Q&A. Very much appreciate any feedback during the Q&A. It doesn't need to be a question. You will have a recommendation, suggestions for more interagency and also public and agency partnership. So we were very happy to hear more about that. So starting here, as you can see, I'm kind of, yesterday I already gave you a very brief update, so I can say this one is a little bit more kind of extensive update. We have a very good representation in this specific UIFCW, and I really need to thank the coordinators, organizer for giving us this opportunity to talk about what the work we are doing. So we are not really doing lots of development, given the restriction in resources and budget and personnel and things like that. But what we are trying to do is to build on a safe and on a good platform, on a good foundation. So then basically we follow the best practices that EPIC put forward from the beginning, and kind of trying to be a good kid as we are developing these applications. So today I'm really, what you see here as members, these are active developers. These are people are providing codes and actively working on development side of the UFS Coastal code base or applications. We have NOS team, and just by the way, Jana Haddad, Dr. Haddad just left us, and we are really looking forward to technical project management with the science background. Reach out to us. That position is open. We are looking to fill that position. And then ESMF NOEPC team. We are working also with Esquizem, Weber-Shree, ROMS, ASIC, and FVCOM and CICE. These are our core coastal-related models. In particular, Esquizem, ROMS, ASIC, and FVCOM. These are like our National Ocean Services kind of operational official models. For CICE in particular, we are working with Oregon State University that they are helping with the development of the CICE. And I'm going to call a lot on different people. And if there are more discussion and presentation posters, and I'm going to kind of let you guys, if you are interested in different part, I would point you to go and see those. And here is just as Ed suggested, we are having a few high-level documents that we are following. And thank you to Tracy for sharing this slide with me. This one is from NOS Modeling Vision. Basically, we are at NOS supposed to kind of, or aimed to support multiple different applications like safe and efficient navigation, coastal resilience, search and rescue, ecosystem health, and so on. However, what you are hearing from us up until now and today is more on the physical oceanography side. And so we are kind of getting ready and geared up also to bring more of this type of application as we are moving ahead. So today I'm going to talk about a brief conversation about UF's coastal code base and a few applications, in particular these two applications, and then also a little bit about operational workflow and moving forward. So there were multiple people coming to me asking how we can get engaged. So we are I'm a co-founder of this open GitHub organization. This is in our working with our partners. They didn't really want to come to know our GitHub. We didn't want to go there to their GitHub account. Said, okay, why not we go ahead and create our own community? And that's where ocean modeling collaboration created. And then now we have these two kind of GitHub repos. One of them is the fork from UFS weather model. Basically, we call this one UFS coastal model, right? And then the other one is UFS coastal application. And there are lots of information there, documentation, our milestones, open issues, and discussions, and so on. Going to the code base a little bit here, I just want to mention that UFUC is going to have a 15 minutes in-depth conversation about some of the challenges and the development of the code base. I'm not going to talk more about that. I just want to draw your attention to the right-hand side where you can see a schism, ATSIR, ground, and FVCOM is already included in the fork from UFS weather model. And they are basically part of the UFS. You can compile them, and then we have a regression test for all of these four, nightly build and testing through CI/CD. Epic kind of workflow is ongoing. It's not perfect yet. We are working on it, but we have majority of this already implemented. One thing that I keep talking about is coordination between UFS weather model and UFS coastal, because we are still connected. We are still updating UFS coastal model every few months. We are still pulling the changes downward, but we don't have a possibility of push our changes upward. So every time we pull, we have a few conflicts across the system. We have to go fix those conflicts. And we think this type of thing could not be manageable. In a Q&A, hopefully Ufuk can talk a little bit more about his challenges and moving forward, what would be the best practice. We are supporting multiple different configuration. One configuration that we have spent lots of time was to connect to sea ice. We actually try to use the sea ice configuration as it stands, forking, but we noticed that the way we are exchanging information with sea ice for this coastal application like Alaska project we are working on is different, so we needed to change the cap and also some other places. Again, Ufuk can talk about that one in more detail. I'm not going to talk about that. We had a lot of success on that front. And again, Scott Dorsky from OSU have a presentation Thursday afternoon. Please attend to that one as well. In terms of unified workflow, again, at National Ocean Services, we have a few disjointed workflow. We have comps that run OFSs, as well as then we have STOF's workflows, all based on bash scripting and not very well maintained. There are lots of redundancies there. So what we are trying to do with this project is we want to build a modern, modular, Python-based workflow. And we partnered with Water Institute for this project. And Mansour on Friday going to talk more about the progress we are making on that front. The other pain point that we have is when we are working with our partners, University of Notre Dame, for instance, for global stuffs, and we see everything is fine, perfect on our shadow model or our parallel model at partnership side. But when we want to bring the same model and run it on NCO side, on WCAS, everything falls apart. And always you say, okay, this upgrade gonna be great, and then again, the same thing happens. So one of the things we want to do, and we are obviously doing our baby steps here, to have a CI/CD to run actual workflow that we have at NCO. We kind of run the same thing, and that's why we also trying to do the containerization and everything to have exact same variable space, exact same directory structure at NCO, so then we can run, even on research side, we do the same thing. This is our first attempt to use just container, GitHub Action, and Parallelworks, and we are kind of want to push it now to use Singularity Container for this, and then eventually we like to try to get this on application level to CI/CD pipeline and Jenkins on Epic pipeline. So a little bit about the applications. So I will start with CCOFS. This is Southeast Coastal Operational Forecast System. This system is supposed to be coupling SCISM as ocean model, WaveWatch 3 as wave model, using CMAPs. And we are working with WIMS and COPS and other partner and ESMF team on this specific application. So at the moment, we are working with our partners from EMC and WaveWatch 3 community to kind of wrap up the WaveWatch 3 component. We have a very good progress on this. Let me see if I get the pointer. Yeah, so as you can see, we really walked through all of these test cases, and each of those have its own regression test. And right now, we are at the last kind of one, trying to get the 3D. 30 minutes, okay, thank you. And again, this is, we are using a small test case for the WaveWatch 3 and SCISM 3D coupling at Dock, North Carolina, and still we are working on the 3D coupling part. Stuff 3D Alaska. So this one, not only we have SCISM and WaveWatch 3, we also have sea ice. For this one, as I said, we are working closely with Oregon State University. Please go see Scott Dorsky presentation Thursday afternoon on that one. So here you can see the first attempt was just to run sea ice within the UFS infrastructure and receiving data through the data cap. And then recently we were kind of successful on running both ocean model and sea ice all within a kind of a UFS infrastructure. And from a wave side, again, as we are working on resolving some of the issues with the WaveWatch 3 coupling on 3D mode, we started to explore the internal wave model and SCISM just to get an idea about how the waves kind of condition works. And again, we are concentrating on the Bering Sea at this point, and we are also looking into satellite altimetry as our data input, and had some good success on setting up the wave model. And as you can see, starting from without wave boundary condition, including wave boundary condition, and then uncoupled, coupled 2D and coupled 3D. As you can see here, we are kind of adding more and more accuracy, and I think we are happy with the results. So just the next step here. The project success is really required to secure more dedicated funding to support not only our personnel, but also our partners. As well as I also want to, again, stress on the shared high-performance computing infrastructure is really, really the key for us. We need to have our partners and us working on the same environment. And we went to NSF, and we are really enjoying using Hercules, but so we are not really able to use other platforms at RDHPCS efficiently because of this. We really want to see more support, and thank you to EPIC program, Maui, and the team, but we really like to see more support from EPIC. It's really vital for us, and we are investing a lot on those infrastructure, and otherwise, basically, we kind of feel like we are left alone. So, and I know Mario and the team here going all the way, and but that we hope to see more a structured way of supporting. As one important milestone, we are going to work on one-way coupling of inland hydrology to coastal ocean model in FY26. Besides working with the waiver recoupling, and then we will expand on UFS coastal. As I said, we will continue working on using CI/CD workflow, and that is basically it for now. And I kind of think it might be a good idea to open it for some questions or recommendation. If there is any, yeah, please.
Say, you mentioned that you had a problem with trying to get some of the new code that you had developed, the similarities between the environment that you tested it on and actually getting it into WCOS2. Can you expound on that a little bit? Are the problems generally coming from dissimilarities in conformity of the environment, or is this from just the performance of the system itself, like the hardware? I'm just curious.
So there are two things. One is the actual folder structure, and like this, because often the model in a way that works on a partnership side or where we are working in like NSF infrastructure is not necessarily exactly following the same folder structure, scripting, job card, and everything. And even there, like the previous upgrade, just missing maybe one space or a Perl difference, whatever, took us 2 weeks to find out why they are behaving differently. So that's one part. The other part is different libraries, compiler options for optimization, and we see the speed up is not necessarily the same as we are getting because we are working on the other side for a few months. So there are really different flavors, but just not having these similarities prone to have more errors. It could be human error or machine-related issues.
Okay, so it seems that it stems more from the conformity of the environment versus just the performance. Even if Epic was somehow able to deliver something like something that's not quite, doesn't perform quite to the same computational levels as WCOS2, but was able to deliver a similar environment, that would alleviate a lot of your, I guess you would say, headaches.
I would like to see, in possibility of having 50 error, we reduce it to 3 error. Or 3 mistakes. So basically reducing that, because when you do this type of upgrade, you are often doing it under lots of stress, time crunching, and things like that. So it's just, we also have a chance of higher, basically human mistakes. So we want to just reduce that by having this conforming similar environments.
Okay. Thank you.
Does anybody else have any questions before I ask something kind of unrelated? Oh, are you out of time?
No. Actually, we have 20 minutes left. Oh, okay. I speed up my. I thought we were almost out. But anyway, yeah, no, we have plenty of time.
Okay, so my question is, today we were talking about getting more community involved. We've been talking about getting more students involved, more people involved in the UFS community as a whole. Now, the Ocean Service has done something and accomplished something that everybody else is trying to do with the UFS Coastal Model Evaluation Project. Can you talk a little bit about that and how you were able to get these developers that you had on the first slide to talk to new schools that haven't used these code bases and train them to grow our community?
Thank you very much for that. That's a great point. So this UFS evaluation team, there was still ongoing a project, and in there we kind of wanted to have independent testers. I think we were, maybe Ed, you have a better recollection of that. We had more than 5 different institutions. Each of them has different postdoc and students. So suddenly we have 20, 30 fresh eyes and on the code, and starting from really bottom up, running a standalone model, then validation, verification. I see Said also here. Maybe he can also chime in. One of the successful postdocs working as a part of this, and it was a great, I guess, not only helping us with the development, but also capacity building and making a team more interested and ready to join us. I don't know, Ed, if you want to add anything to that.
Sure, yeah, that's a great question, because, yeah, it really follows the philosophy of the graduate student test, that we should be able to make our codes and applications available to the community and have graduate students, early career scientists be able to take that code and apply it, test it, and make contributions, all of which happened during this whole project with the coastal application teams. And yeah, it was great to see the contributions being made, and we learned so much. And in the process, like Saeed mentioned, it helps develop these early career scientists, to be part of that whole network that we previously discussed in the previous discussion. Just so, yeah, it was really great to see it all come together, and the recommendations are informing what coastal models are going to go into the unified forecast system. So from start to finish, it was just a really great process to see how it evolved, and really a success story for the team.
Yeah, thank you. Just want to mention something. I kind of speed up myself, and I missed to say something here. So we started with the 4 core models at National Ocean Service. However, due to some of the restriction of the funding and resources on both sides, we decided for this year of upcoming year, FY26, we concentrate only on 2 specific applications that share more component to give us the chance of leading those applications to somewhere more useful, instead of us spreading team across so many different combination of coupling systems. So the fact that we decided on this one is not because we are having one model on top of the other one, is more because of giving us the opportunity to develop them, and then in an iterative manner, when we get to somewhere, then we come back and add more maybe model component and open it up for more development. And again, we are actively also submitting proposals for getting more and more kind of projects. And however, that I just wanted to provide this because I know modeling from different community are looking at this. I just wanted to have this clarification. Please.
Thank you for a nice talk. Since we had a little bit of time, I have 2 questions.
Please.
So my first question is how your work is feeding back into the UFS weather model. It looks like you had a fork of the UFS weather model, and then you had a couple additional components. Are there plans to add those component models into the UFS, the ROMs, for instance, and SHISM? And do you feed back into the UFS weather model source code? That's my first question.
Yes, thank you very much. Excellent question. I let Ufuk to perhaps talk about the answer to the question, also some of the challenges or suggestions that you have to help with this process of not only receiving information but also kind of paying back.
My impression is that bringing a new component to UFS weather model is straightforward. So there is no any issue over there. You can bring that component. You can create a specific regression test about that. The main thing is that the developer of those components needs to spend some time, because, for example, let's assume that you bring a new component to UFS weather model and then port it to WCOS2, and then you have some issue related with that component. And then what will happen in that time? So the developers of those components needs to dedicate their self to solve those issues, because we are just working in the upper layer. We are trying to couple them. We are trying to solve the issues. But at the end of the day, if there is an issue in the component itself, or some updates could lead some issue in the upper layer in the UFS weather model or something like that, we need to get some I think we need to get some promise from the developers of that specific component to solve those issues. So at this point, we don't know the ROMs developers will have enough time if we have some issues in the UFS weather model or not. So that's the only concern in my end.
Yeah.
So
there are also other kind of, I guess, the bandwidth also on the weather model side. Because accepting, we are actually advocating and following up on not only pulling, but also pushing. But there are also lots of constraints, and UFS weather people are really working around the clock. There are always a lot of priority for them to work on. So we just don't want to like start imposing even more load to their current high really pressure workload. Otherwise, I think it would be a great idea, and that's why I kind of also bring it up in the yesterday that having a kind of how UFS coastal and UFS weather model can exist in a structured way, exchanging the data, not only receiving the code, but also feedback is not only a new component, because as I said, we changed like sea ice component, right? Sometimes we need to change a mediator to some extent to accommodate our work. So these are the feedback that we can provide, but we know that weather model side, and we are proactively working on that, thinking about it, and hopefully we will find a solution to share this type of information.
Yeah, I just want to add one minor thing. So maybe rather than pushing everything in a once time, for example, if there's an interest to use, for example, ROMs under UFS weather model or something like that, maybe we can push that development only at the beginning, and then maybe we can push only one regression test that supports the ROMs, and then we can start working on it, and then that we could expand that push maybe with another component or something like that. So it could be an incremental thing rather than pushing everything in once.
Yeah, no, I fully understand the technical and programmatic challenges with that. I guess maybe it's more of a philosophical question on what is the UFS. If it's probably beyond the UFS weather model, but maybe a discussion point. My other question was maybe a little more simpler, and I was just wondering if there was a scientific reason or scientific motivation to use ROMs instead of MOM6 and HICOM that's part of the UFS weather model.
I think this question is definitely beyond my line of expertise, so I would defer that. I mean, if there is somebody or Ufuk, okay.
Yeah, the only thing that I can add about that, the ROMs is structured grid. It's using the curlinear or regular lat long. It doesn't matter. You can create those kinds of grid, but other components, FECOM, AdCirc, and CISM is unstructured. So especially for the coastal process, using those unstructured models is vital, because you can represent the coastal line offshore in a much more higher resolution. So those extra components bring extra complexity and extra capability to, especially for the coastal. Okay. But for example, using ROMs rather than using the MOM6, it's a different scientific question. But ROMs, my impression is that ROMs is one of the most sophisticated ocean component. It also includes data assimilation, tangent linear calculation. So it might suit better for specific applications.
Thank you.
Please.
Question here. So I was interested in your future developments with the one-way riverine or the hydrology, inland hydrology connection there. And you didn't specifically mention, I'm not too sure if you would leverage the land surface component of the ESMF framework and the modeling there to say, okay, we're going to generate like these surface runoffs and subsurface base flows and route them on a river network, and that's what's going to feed into like the boundary condition of the AdCirc or the ROMs, for example, there, to sort of do that. So that's very interested in the river coupling to the coastal model.
Thank you for the question. So I just so you have different levels of kind of technicality for resolving this issue. So currently, First of all, in terms of like fully two-way coupling between surface, subsurface, this is not really the scope of the work we are doing right now. And that's really what I called fully two-way coupled inland hydrology and coastal ocean models. At the moment, what we are thinking is kind of just receiving the discharges at the boundary of the mesh or inside the mesh as a source term, and then having precipitation across the domain, and assuming all of the precipitation goes directly to runoff, which is a crude maybe estimation, but that's basically what we're working for. In the past few years, we had a great progress on including this on a component level. So like AdCirc, SCISM, ROMS, and FECOM, all of these four are capable of resolving, getting those inputs and the discharges and running their model. So this is already resolved. So what we are trying to accomplish here is to, instead of these different models, read those as an independent input file. We read the output of, let's say, national water model as a centralized input through the data cap. And then the data cap be in charge of distributing those data given any ocean models getting included. So that's basically the work that we want to start doing in FY26. I don't know if I answered your question. Okay, thank you. Okay. Yeah, right. So is there any other question, comments, anything we need to know and we suppose, and it seems like we don't know about it? Please. I don't necessarily want to keep you away from lunch or getting outside for fresh air, but yeah, please, Tracy.
Yeah, I was asking, I was wondering about, you were talking about the connection with the EPIC team, with the workflow and CI/CD and things like that. Can you tell us a little bit more about how UFS Coastal and the Ocean Service is becoming part of the community through kind of streamlining those workflows?
Thank you, Tracy, for this question. Again, I will take my stab on that. I will let Ed maybe talk about it, and I see Maui in the room, so maybe we can have a little bit of conversation here. Again, I'm talking about this more from a scientific, technical lead that, okay, I need this. But there are lots of other moving things, parts that need to get those connections right. So from National Ocean Services side, there need to be some constructive conversation at leadership level. Okay, what is the budget, what we want to do, how much we need to invest, and then of course we as a technical level, we let them know, okay, we need this amount of resources on our side. EPIC also inform us, okay, if you need this support at this level, you need to have this or that. So this, I think we have to, maybe we can start from both ways. So we can start the conversation at the technical, scientific level just to estimate what are the resources we need. And we want to do it on an iterative manner. We don't want to say, hey, we need 25 people here, 50 people there. Okay, maybe we can start with some baby steps of, and let me back up a little bit. We are already getting a lot of support from EPIC. So all of those CI/CD implementation, all of those code management, we are getting a lot of support already. But I'm guessing these are all really kind of more maybe as a colleague-to-colleague type communication. Some of them are also structurally funded, and I'm not really necessarily aware of all of that. Maybe again, Maui can shed more light on that. But I think we need to really start the communication both from leadership side and also from a technical level side to get to somewhere in the middle to have some agreements and moving forward. But thank you very much for the question. I don't know, Ed, any comments from your side?
Yeah, and just in general, I think, yeah, within our NOS team, we're also trying to rethink how we work on a day-to-day basis, just embracing, for example, the agile DevOps approach to making sure that we have, this continuous cycle of, getting, a first implementation in place and then continually refining. And so, yeah, I think continuing to embrace new ways of thinking, but also this new framework of how this community is coming together with all these important components, and CI, CD, and EPIC have been really fundamental to all of that, and training as well. So I think we need to be, I know Saeed, you've coordinated some of the training across the ocean service to make sure that we're up to speed on a lot of this. So it's, it's on all fronts. We need to think about the way we work together and embrace some new methodologies, because it's really empowering to see the results that come out of all of this.
Maui, please.
Yes. Hello?
Yes.
Okay. So since EPIC is mentioned, I feel obligated to say something, right? So I want to mention that when I listened to the social network analysis earlier today, I want to echo what mentioned there. So this is a very different community from the weather community, but we learned a lot from the collaborations with the coastal community. And in fact, some of our ideas was not able to realize in the legacy weather application, but it was realized here. So I see a lot of benefit for us to keep on collaborating with each other and move the UFS together. So we are already part of UFS, and whether or not EPIC can spend more resource to support the coastal application, that we should discuss that more.
Oh yeah, thank you for the good news. Okay, okay. Is there any other question? No question one, no question two, question three. Okay, thank you very much, everybody. Thanks for attending. Highly appreciate it. Leave it to the master of the day, please.
All right, thank you so much. That was great, very interactive presentation, which we'd love to see. All right, we're gonna break for lunch. I'm gonna give a 5-minute warning at 12:55 to let everybody know that we're starting again. In the South Bay, you can find the parallel session for global application across scales, and in the Center Bay, which is this middle one right here, we're gonna do cross-cutting data assimilation. And a reminder about Just your friendly 5-minute warning. We'll get started at 1 o'clock in about 5 minutes. I'll try and figure out how to open it. I haven't, since it wasn't. No, that's okay. I'll go to the close one. All right.
Until that's fine. Okay, good afternoon, everybody. I hope you enjoyed your lunch. We're opening a data simulation session, and there'll be for speakers, will be a person here who's not here right now. She's coming back. And she will monitor your time and signal to you. If you're over time, I'll cut you off. And with that, JJ, you're the first speaker, and we're looking forward to learn about your work at Tomorrow I/O.
I just wanted to make sure that the laser pointer worked. Okay. So I'm going to share with you today an internal evaluation that we've been doing of our Tomorrow microwave sounder.
using a JEDI and UFS system that's very much community-driven as far as the capabilities that we're able to achieve. Yeah, so without further ado. So our Tomorrow Microwave Sounder, or TMS as I'll be calling it, has heritage in the NASA Tropics mission. It has similar capabilities to, say, ATMS or MSUA and MHS as a combination, although at different frequencies and very different channel characteristics. So we do temperature and humidity sounding. Where we differ from Tropics, or where we've improved on it, is that we have additional internal calibration targets and also perform extra on-ground calibration that gets us better spectral response functions, and we also have a digital spectrometer in the F band. So all in all, what this means is that we have a low-cost instrument, and we've taken this from a proof of concept in Tropics to more of an operational ready instrument. So being low cost, that allows us to launch a lot of these into space simultaneously, or to have a lot of them in space simultaneously. And that was really why the company picked up this satellite in the first place. So on the bottom, you can kind of see the motivation for why we're doing this. The current program of record, or I should say current, when I was running these experiments in January, had microwave sounders revisiting at around 700 minutes, and we're going for something less than 60 minutes. And microwave sounders provide a very large impact on weather forecasts. This is shown in a lot of different studies. And we're able to do this by launching these satellites and get the high revisit rate by launching them in many orbital planes. And so I'm showing you a collection of the orbital planes we have already on these 7 satellites that have already been launched. I'll only be looking at 2 satellites in this study, S2 and S4, but we have a planned constellation size of around 12 to 18 instruments. So the objectives for what I'm about to show you is to establish a TMS assimilation methodology that can be used and adapted in the community, and also provide a first research level estimate of how much TMS is going to benefit in NWP. Now there are ongoing evaluations at EMC. Dan Holdaway mentioned this yesterday in the data assimilation discussion session. So we're supporting those evaluations, and we by no means say that this is the end-all be-all right here. So to give you a sense of our NWP system, we draw a lot from GFS and GDAS as far as the configuration goes. One thing is that we are using FE3 JEDI, so we're not using GSI. But still, FE3 JEDI, all that development really comes from EMC and JCSDA, so we're very dependent on the public community, and actually me and one of my co-authors have come from that community ourselves. So we're very much in support of it. We're using 3D ENVAR, which differs obviously from the GDAS, and only 30 members. This reduced configuration allows us to run a lot of research experiments to figure out what the best configuration for our instruments are. You can see that we're assimilating in our January experiment, which is the one I'm presenting today, microwave sounders, in situ observations, and a couple satellite-derived variables. We don't have the IR instruments in yet. That's still an ongoing development. So to give you some sense of what our research level system can do, here's microphone. Oh, it's back. Okay. So here's forecast skill versus upper air observations for a few variables and at different levels. Our own analyses are shown in the... I feel like this keeps dropping out, sorry. Our own analyses are shown in the dashed purple, and GDAS analyses are shown in the solid red. So you can see that we are definitely not as good as GDAS, and we don't expect to be, given our current configuration. But we feel that we're close enough in order to come up with some early conclusions on impacts that microwave sounders might have in an operational setting. So what does it mean to establish in a new settings or configuration for a TMS instrument? First of all, for a microwave sounder today in operations, you want to be able to assimilate it in all skies. This is basically par for the course if you look at ATMS and AMSUA, et cetera, at various operational centers. And so that involves an observation error model and quality control specific to cloudy scenes. And so that's what's shown on the right is our scaling of the observation errors versus a cloud impact parameter on the x-axis for various channels. Comparing the solid and dashed lines is just showing that our estimates are in line with what we've diagnosed those errors ought to be. We also apply extra quality control when to remove pixels when observed and modeled cloud impacts differ significantly. It doesn't have much impact on the number of obs we assimilate, but it does have an impact on forecast quality. Okay, so in early runs of our experiments, we did find out that we were getting some negative impacts actually from TMS. This is not what we want, right? We're trying to sell this data. And that's shown in the bottom figure. So there's all these little blue segments. Those are where we have a negative impact on 6-hour forecast scores versus GDAS analyses in the middle of January. And it turned out that this period of degradation aligned with a transient beta angle precession of the S4 instrument. So S4 is in a 45-degree inclined orbit. This is very different from current operational satellite microwave instruments, which are usually in a sun-synchronous orbit, as S2 is. As that beta angle increases, is shown in the top figure, the orbital plane becomes more perpendicular to the solar vector, which imparts a lot more thermal variation on the satellite. So ultimately, what we found is that we needed to affect a solution through bias correction. So that same figure I was showing before is now on the left. And then in the middle is when we add some extra intra-orbital bias predictors. I don't have the details here, but these are in a preprint that I can share with anybody who's interested. So we're getting closer to neutral effects during that period, and then also a lot of positive effects outside of that period. And overall, we get an RMSE reduction. That's what's shown on the far right. So this is a problem that exists in this low-cost, small payload that we are still trying to improve in our L1B product through better calibration, but also through improving this variational bias correction. Thank you. So we felt that that was good enough in order to proceed to OSEs, where we're actually comparing our instrument impacts to others. So our control experiment in these OSEs assimilates all the data that I mentioned before. And then I'm going to show results from 3 different denial experiments. One where we're removing TMS, both satellites, so those are in 2 separate orbits, and then ATMS on 2 instruments, or on 2 satellites, sorry. But that's actually, they're both kind of in the same orbit and only 180 degrees apart. And then also MEDOP-C, removing AMSUA and MHS. And MEDOP-C shares an orbit actually with MEDOP-B. So there's a lot of, are we actually filling gaps with these independent orbits going on in the results? So here we're verifying against ATMS. These are background fit RMSE increases caused by denying either MEDOP-C or 2 TMS. So when we deny the 2 TMS, the striking impact is really for channels 17 through 22 of ATMS. We get up to a 4% improvement so it's showing an RMSE increase here, but what that means is that in the control run, it's actually an improvement. Up to a 4% improvement for those ATMS water vapor channels. And then also we get improvements near the surface on channels 1 and 2, and even up to the tropopause from denying or from including TMS, let's say. MEDOP-C has a much larger impact in the stratosphere, and that's to be expected because TMS doesn't have as many stratospheric temperature channels. So these are in line with the channel characteristics of the instruments. Moving on to more extended forecasts, these are 0 to 4 day RMSE changes when we are either removing ATMS, so both ATMS instruments, or 2 TMS instruments. Anything yellow means that the instruments have a positive impact on the control. You can see that both have very similar signatures as far as the altitudes and pressure levels and lead times, although ATMS has a slightly longer lead time impact for water vapor. The impacts aloft for temperature are actually about half as much for TMS as they are for ATMS, although at the surface, TMS has just as large of an impact as ATMS. So these are global impacts. I have a lot other figures that I didn't really have time to present today. Happy to talk to anybody if they're interested in particular regions of the globe. So in summary, we do have an effective assimilation strategy that we're ready to share with the community. Those come as JEDI YAMLs that we can easily share. Please reach out. And then essentially everything there is things I've already said. Again, this is all in a preprint that we've submitted to QJRMS. I can share that to you. Just please reach out. I also want to point out that we have a bunch of other people from tomorrow. Forrest, Randy, Max, and Mariah are all presenting posters tomorrow on their data-driven forecast and DA work. Please visit them and learn more.
Thank you, JJ. Any questions from the audience?
You have one. I have a question from online.
Take one question.
Okay. The question is, will this data be available to NOAA, NWS in the more raw ASCAT type WinBarb/speed layer?
Barb means in this context. So EMC is already, and sorry, NESDIS is already getting this data as part of a data pilot, and that's being shared with various NOAA stakeholders internally. So yes, it already is being shared. I don't know about the format exactly. Okay. I'm sorry.
No worries. Thank you.
Yeah.
Thank you. Next speaker is Ming Hu.
Okay, good afternoon, everyone. And I'm going to report our recent progress using JEDI for roofs of next version RRFS system. So I think most people know the acronym. And I actually list a lot of colleagues here. That's long. I spent a lot of time tap, and then I realized actually those are all colleagues working on data simulation. So we have equally actually long colleague list. I believe you will see maybe tomorrow during our modeling section that working on model. And we're actually working as a team. And you also can see actually there is a lot of colleagues from GSL and also lots of colleagues from EMC. And that's our core development team, but we do work very closely with also other colleagues from like NSSL, from OU, and from other labs. So it's really a huge team to working on this, building the RFS, and my talk only talk about our GI data simulation and tuning. So, okay, works. So what is RFS? And it's regional convection allowing deterministic and ensemble forecast operation system. And we have target localized weather hazards. There's a lot actually. Basically everything we try to make the forecast. And also the benefit, many users, I have a long list of users, and actually, they are actually, because it's operation, there are many users. And the major future for RFS is actually we're running the 3-kilometer grid cover North American domain. That's a huge system. And every hour we make 18-hour forecast, and every 6 hours we make 84-hour forecasts, both from deterministic and from ensemble members. Roof version 1 is towards operation right now, and we build Roof version 1 upon FA3 LAM and the GFS. And the Roof version 2, we try to build it upon the MPAS and JEDI. So this is a flow chart to show Roof version 1 DA cycling and the forecast strategy. And I'm not going to go to the details, and it's just it's a very complicated system and built upon the model and analysis. And this talk right now, I will focus on just one box called ENVAR, and in KF, that's basically our deterministic and ensemble forecast box here. So a little bit introduced to the JEDI, and I think everyone knows JEDI is basically developed by the GCSDA and led by GCSDA. And we pick this as our component for rules version 2, and we are under very extensive evaluation and development to using JEDI for our system. So what purpose is using JEDI is actually we try to maximize the positive impact from all observations available to our system to improve the model forecast through an hourly simulation system. So we have a clear actually target when we evaluate and test JEDI, like we need to run deterministic cycles. So we test 3D VAR, 3D InVAR hybrid analysis method, make sure it's give us the good results. We need to run ensemble forecast, so we test GETKF analysis. And we have all sorts of observations, like we have up air, and we need to see the improvement from up air to our environment and mesoscale forecast. And we're using surface observations to improve the near surface forecast. And we're using radar reflectivity, radio velocity, lightning to improve the storm forecast. Like we do using satellite readings data for improving environment forecast. We have cloud analysis too to improve the cloud and the fog forecast. Like we ran coupled land atmosphere analysis, certain kind of, to improve the low-level atmosphere forecast and the soil forecast. We also want to add AOD and PM2.5 analysis in this new version to improve smoke and dust forecast. So in our system, because we mixed large-scale data, small-scale data, so we do want to run multi-scale data simulation to using all observations at one set of the analysis, not the two set. So that's our area that we are actually very actively working on. Now, what we do is actually we run lots of experiments, evaluate the impact, and then do further tuning and development. We run real-time experiment, and we also run retrospective experiment. So we designed very basic cycling strategy, not like very complicated real-time operation runs. We designed this very basic strategy to evaluate the impact of the DA system. So we cold start MPass model 0 and 12Z and do 12 forecasts. Then we do hourly cycling with DA like MPass plus JEDI. And every hour, then we compare 1 hour forecast from 11Z with the 12-hour forecast from 0Z. So we see the improvement of the DA in 11 cycles. That's what we do right now. Here is actually the results. So first is what MPass JEDI variation analysis method looks like right now for our system. So we compare with MPass JEDI and FE3 GSI from Rules version 1. So this is up air RMSE forecast against sounding data from our retrospective experiment. So when we show the dashed line, it's 12 forecast. That means there's no DA impact. But when we show the solid line, which is 1 hour forecast, that shows the 11 cycle data impact. So origin line shows 3D InVAR. It's clear that compared with dashed line, it's improved, right? It's clear reduced the RMSE during the forecast. And then it's good. And then when we move into blue line, it's a 3D analysis. Both are improved based on the compare even with the orange line. That means 3D VAR give us even better forecast right now. But when we check the red line, that's the hybrid. So the GSI hybrid still further improve the impact of the data, but somehow actually MPass JEDI hybrid mixed that red line and the blue line. So it does not show further improvement. That's the temperature, and next is wind speed forecast. The same story. When we compare with the dashed line, the orange clear shows positive impact, and then the blue line is further improvement. Or for JEDI, blue line is actually mixed with the orange line. It both shows consistent positive impact. But when we check the red line, the GSI clear shows that red line further improved compared with blue and orange. Then actually, but JEDI, this red line is really mixed with the the other two lines. So our conclusion here is actually JEDI 3D-VAR, 3D-NVAR works very well, give us consistent positive impact. But somehow the hybrid need more work to double check, make sure actually it's a kind of give us positive impact like GSI. So another big piece for us is the surface data. Like here you see we test the surface meta observations. This is basically one forecast time series to show with data and without meta observations. So we can see this blue line is with meta observations. So it gives us consistent improvement compared with the test that without meta. But we do further to tune the model observation operator, like using model 2-meter temperature as background, which is actually the blue line here. So we can see the same RMSE time series for 2-meter temperature, and the bias is a dashed line. So if you compare, we can see the blue experiment further improved. That means using 2-meter temperature as background for a model does improve the forecast. Because we're using 2-meter temperature as background, we do not need to turn on the vertical observation area inflation. That will further improve the impact of the data, which is the orange line. So another side is we adjust the terrain. We do terrain adjustment for surface temperature. So we do the test, and it works as expected. So I don't think I can show the details here. And another side of work is testing GETCAF. We do show that when we run GETCAF, it's improved ensemble forecast, even better than deterministic forecast at this moment. And also, when we're using the GETCAF in our ensemble data simulation cycles, when we use this ensemble forecast in deterministic, it's even further improved the deterministic forecast. So GETCAF works very well in our hourly simplified cycling with aircraft data right now. So quick summary about we test that JEDI actually very extensively. So this is a quick summary about what I talk about. So we test that very well, and it shows very good impact, and we still need to working on something. Thank you.
Thank you, Min. We have time for one question.
Every presenter is going to have 12 minutes. At the end, we will have time for questions if we stick to the schedule. We will have about 26 minutes if we stick to the schedule. So if everybody can hold their questions to the end, that would be great. Is this on? Is this working? No.
Okay. Christian, you're next.
Okay, today I'm just going to tell you about a new component that we've coded in the JEDI system, which is the hybrid tangent linear model. And I'll show a few results for it. But what is the hybrid tangent linear model aimed at? In particular, it's for 4D-VAR. I won't belabor the 4D-VAR cost function. I'm sure a lot of you know what it is, but this is what it is. The key part is that we look at observations over time. This is the general idea, if you're not too familiar. We run some forecast that we hope out to TN, past TN, we're looking into the future. We have observations of our system. By solving that, by minimizing that 4D-VAR cost function, we usually look for an initial condition, that takes such that when we rerun the model, we're consistent with those observations. It's just the general idea. So if we want to do that, we need to minimize the cost function. The way that that's done is using something called a tangent linear model. So if you look at this perturbation here, you see this M that's moving an increment, or this L, moving a perturbation in the model forward in time. So it's this piece that we're really interested in and that we're going to make a hybrid tangent linear model out of. How do you do 4D VAR? I won't go through all of the steps for time, but point 4 there is we need to calculate the gradient if we're going to minimize it, and the key there is that L. That's called the adjoint, which is directly related to the tangent linear model. So you need this tangent linear model and adjoint to make 4D VAR computationally practical. If the model physics change or added once you've coded one of these, that can make your TLM not so accurate. That's where we want to do the HTLM, in particular because it can be a full-time job to maintain a tangent linear model. So if we have an HTLM, what we'll end up, I'll talk about doing is using an ensemble to correct that tangent linear model. Okay. So the HTLM is actually based on the localized ensemble tangent linear model, and this, I think, gives a good sense of how it works. So we're interested in that L, and let's say we don't know it at all, but we want to try to learn it. If we consider just the jth element of our state vector increment at some given time, and we'll suppose that it depends on a bunch of points around it. You could kind of think of that like your stencil or something, but we'd call that the region of influence. And if we do that, we can solve for, well, if we assume it depends on that region of influence, so say we're interested, at that green point in the figure taken from one of Sergey's papers, we might consider that region of influence these red dots here. If we want to discover that matrix, we might solve for this mu j, which would correspond to the non-zero values in the jth row of that L matrix, which is the tangent linear model. And if we want to learn it, we can use an ensemble doing that by running the full nonlinear model. That would be these bold parts, so looking at actual increments between an ensemble, and then sampling around that influence region size and setting up just a least squares problem to solve. So if we set up that least squares problem, we get the normal equations, and then we use a pseudo-inverse to try to find each one of these mu j's to build up that matrix. But in practice, if we do it only with this ensemble method, you need a very large ensemble and a very large influence region. It makes it computationally difficult to do. So this is where we come up with the idea of a hybrid tangent linear model. So suppose we have some simplified tangent linear model. This might be the dynamics only, or we've just added new physics and we don't have that in there yet, but we have most of the things. The idea instead is that instead of just sampling those increments directly, we'll first use the tangent linear model we do have, which we typically refer to as the simplified tangent linear model, to a vector increment forward first to get a guess of how that perturbation would have changed in time. Then we'll do basically an LETLM to find a correction to try to include through the ensemble the missing physics that we didn't have. So here's what that would look like there on the bottom in an equation. I'll show a cartoon of what this is doing in a moment. But basically that dx minus is simplified tangent linear model has been used. Then we solve that least squares problem to get a correction to see where we should have been had we had a full TLM. Just to give you a sense for what that ensemble matrix looks like and what we mean by an influence region, suppose we had a 3-layer model with 2 variables, and I'm interested in this particular grid point that's in the red box, and let's say my influence region size is 3. I would just sample points, including that point, 2 above, 1 below, but then also for the other variable, I would include that. We don't have to do all the variables, but usually we're looking at everything that that point and variable might depend on. Okay, so just to give a cartoon in case that was too much too fast, the idea is that we might have our complete TLM, which would advect a perturbation forward in time, and then we might have our incomplete TLM, and it's not quite right, it's missing something, but we're going to find these HTLM updates that sort of push us back in the right direction so that we're getting a TLM that's accurate. So how do we do this? Well, we run a nonlinear control, so some central member, and then we run an ensemble. We initialize, this is how we'll calculate those updates, but we initialize increments at the beginning based on that nonlinear ensemble, and we initialize increments at all of the times that we're interested in, so like the observation times. Okay. Then we're going to save those, and then we're going to go back and take the first increments that we had and use our simple TLM to forward them in time. So this is like our first guess of what the TLM should have done, but we had these nonlinear increments that we can compare that are actually exactly how the perturbation would have gone, that we can compare it to that first guess. So we take these to form the equation to get that little VJ update term to basically solve this problem. But of course, in reality, we have also other variable dependence on this as well, right? So this hopefully gives a sense of the problem that we're trying to set up. So how do we do this in the hybrid tangent linear model, or how do we have it coded? This is just an alternative form of the update, and I'll just refer to this CJ. We call that an HTLM coefficient. That's what actually does the update. You multiply that by the influence region. I don't know if the pointer's working, but in the middle there. You can put this into a matrix, and the key part here is really just that if we wanted to run, say, or move an increment forward in time, we'd first apply our little L, that's our simplified tangent linear, and then we simply apply our update once we've pre-calculated those coefficients. And then your adjoint is straightforward. You have these coefficients in a matrix, it's just the transpose, just like it should be. So you do first, I guess unupdate, but do your adjoint update, and then use your adjoint model to go backward. Okay, so how do you get the coefficients? So first we initialize those increments. We initialize the increment ensemble using the nonlinear values. We'll forward those, and we'll actually get a coefficient when we move our first and update before we forward again and calculate new coefficients. When we do that, we're going to save those out, and then once we have all of those, we repeat that, once we have all of those, then we're ready to do 4D var. So we'll have coefficients at every time, then we can go back and do a regular 4D var. So I'm just going to highlight just some results that we're getting. This was using NASA GEOS for atmospheric chemistry variables, work with Miriam. It just shows in the blue line some of the linearization error when you don't use an HTLM. And then you can see in this first one, is that the pointer? Well, that the error is basically crushed to zero. This in the middle is just a zoomed in version of that sort of HTLM runs purple line showing this for different ensemble members, and that it's pretty robust with ensemble members. You can get good reductions in linear error. And then also we see reductions even for variables that we're not directly updating. So in this case, air pressure thickness, once we use the HTLM. That was with NASA GEOS. There was also some work done with SOCA. So JEDI is generic. You can use it with any model that has an interface to JEDI. We also saw some nice reductions. And we have some interesting adaptive regularizations and other things that we've added as well. All options that can be easily configured and used. This is just a picture of some of that linearization error on a map for volume mixing ratio of ozone and a volume mixing ratio of carbon monoxide. And you can see on the bottom with the HTLM that it's basically zeroed out in space. This is RMSE. So I think that's fun to look at. And then just to summarize, if you want to do 4D var, you need a TLM, but they're difficult to maintain. Some of our initial experiments show that the HTLM works, and we get good reductions in linearization error, and all we need is our nonlinear model. And we've tested this with GEOS. Dan Holdaway had an intern that's looked at this, I think, with GFS and SOCA, and it seems quite promising. There's possibly some future directions. We might want climatological coefficients, kind of like you think of a hybrid B, maybe there's a hybrid HTLM, or maybe some ML emulator of this, or run it on GPUs, or maybe AI ensemble generation to actually calculate those coefficients. And sorry, that was pretty fast, but thanks. Ah, perfect.
Yeah, I'll prefer to ask the questions right now. So if there's any questions from the audience, I'll take it. I'll have a question. So storing all these coefficients, is that how feasible it is for realistic models? Are you running out of memory? Is it hard?
That's a good question. So there's two ways we can do it. We can calculate the coefficients first and then write them out and read them in, which it is a lot of like disk, but then you're not running it in memory. We have yet to do like really hard tests of this. I've at least run it at like C83 with FV3 JEDI. It's expensive. I should say that we are working on some optimizations with some funding from the UK Met Office, where we'll have a little bit better with OpenMP. That should speed things up. And then I think it would really be great to run it on GPUs, but to have like you can keep the coefficients in memory. We haven't really like vetted how expensive that is, but it at least runs at C384. But that's a good question. But I guess we're still experimenting would be the answer.
Okay, thank you. And see, it's 384. It's, you know, it's not a toy resolution, so thank you. That's great achievement. Okay, I think Peter Jan, you're next.
Okay, good afternoon. Thank you for being here. I'd like to talk about nonlinear observation errors and how we can use them, how we can estimate them, and how we can use them in our present-day systems, which assume Gaussian observation errors. So I'd like to acknowledge my PhD student who did most of the work, CG1, is now a postdoc at GFDL, Ellen Geer from ECMWF, and Josh Chen, who's my cadre postdoc. So let me see. Yeah. So let's first go to how do you estimate non-Gaussian observation errors? And the idea is as follows, right? You can just look at innovations. Innovations are the difference between observations and the model forecast. And there's also, and the innovation is also the difference between the errors in the forecast and in the observations. And so we have the first equation there, and now if you write that in terms of probability densities, then you get a second equation. You see that the PDF of the innovation errors is the convolution of the PDF of the forecast errors, and the forecast errors come from an ensemble in this case. That's why you see ENS there. So the convolution of the forecast errors and the observation errors. And so this is an equation to tease out the observation errors, but you have to do the deconvolution, which is actually not that complicated. It is quite a stable system. You just need some smoothness, add some smoothness, and then you can do the deconvolution. So that's the trick. It's very simple. And the question now, does it work? So we used oh, no, I don't want to go here actually. I mean, it works in simple tests. You believe that. What's happening here? Okay, I see there's something. Oh, this is still the old version of the slide. So, so these are results. I just took the 37 gigahertz observation, so the errors in those measurements. So it's I show you right. It's the vertical polarization, the SSMI observations. On board. Well, anyway, you look at all the details, and we tested it using the ECMWF system. And my student went there for 2 months to do all this. And so these are the results. And I depict the errors as function of the cloud amount. So the picture on the left is for cloud amount between 0 and 10%. In the middle we have 20 to 30%, and on the right we have 40 to 50% cloud amount. And you see, you get these observation errors. They are not Gaussian. They look a bit like Gaussian, but you see they're skewed. There can be big biases. Look at the middle picture. I have a bias of about, well, 5 Kelvin, something like that. So the nice thing is, with this estimation of the errors, we don't have to do any bias correction in the data simulation anymore. So of course, okay, you get these observation errors. Are they any good? Well, of course, you can check during the back substitution. So just look at your. So we essentially checking if the deconvolution worked. So we can tease out from the observation errors and our forecast errors. We can do the convolution and see if we can get the innovation errors back again. So that's what I'm trying to show here. So you want to compare the red line. With the dashed line, and you want to be these two to be on top of each other. The red line are the actual innovation errors, and the dashed line are the estimated innovation errors. So just checking if we did the deconvolution properly, and you see it works quite well. So now we have these observation errors, and now we're gonna want to use those non-Gaussian observation errors in a data simulation system that assumes Gaussian errors. So how do you do this? Well, we need a data simulation method that is an iterative method. So it could be a variational method, it could be an ensemble var, it could be an iterative ensemble common filter, or an iterative ensemble common smoother, or some nonlinear method that uses iteration, particle flows, you name it. So how we do it is as follows. So you see the drawn line, that would be the cost function when we incorporate this non-Gaussian observation error. You see it's not nicely quadratic, but it has some weird shape. So how it works is that we say, okay, for a Gaussian, to define the Gaussian, we need 2 points. We need to know where the mode is, and we need to know the standard deviation. And how do we determine that? So we're gonna fit a Gaussian for every iteration. So for every outer loop, I should say. So we start with the outer loop, and we start with the blue dot. That's our starting point. And then we calculate the gradient of the cost function there. And we're going to use that to estimate the standard deviation of a Gaussian PDF. So we fixed the mean, for the mean of the Gaussian, we take the mode of the PDF. We can just calculate what it is. And for to find the standard deviation of the Gaussian, used in the 4D var in this case, we make sure that we take the Gaussian that has the same slope, the same gradient of the cost function as the nonlinear PDF. So in that way, we can now use in the inner loops, we use the dashed Gaussian PDF. And then for the next outer loop, we do this procedure again. So now we have the green dot, and we again calculate the slope, and come up with the corresponding Gaussian, which is the green dashed line, etc. And then we do this for the number of outer loops that you have. And we can actually show that this converges, not always, but theoretically we can show that there is convergence for this method. So let's use this in a real system. So we use it in the ECMWS system. So we took 3 months in summer, 3 months in winter. And what I'm showing here are the observational the observation errors, the PDF of the observation errors that we're using in this system, as function of the innovation in this case. That's what I'm showing. So on the right we have the standard way of doing this. We estimate a Gaussian PDF, and then we use that in the data simulation. So this is what ECMWF is standard using for this specific channel 12. And then we can look at what our method would give us. That's the middle plot. And then on the right hand side you can see the difference. And the interesting thing, thank you. The interesting thing is that if you look at the difference between these two, the difference is actually huge, right? Especially in when the innovations are small, then we get quite a large difference in the error that you should use. And now if we use that in the real system, like I just mentioned, so we're looking at 9 to 21 hour forecast. And so we only use this method on the SSMI channels, and then we looked at how good we forecast other observations in this time interval. So these plots are such that on the vertical we have the different channels, on the horizontal we have the normalized standard deviation. So 100% is the existing system, and red is what the new method gives us. So it's the reduction in the error. So being smaller than 100 is good, and the blue line. I'm not going to talk about the blue line. There's anyway has to do with the quality control. Sorry, the bias correction. I'm not going to talk about that now. So you have to see if the red line is below the 100%, then we're doing good. We get an improvement, and you see here for AMS. Sorry, it's not my. Anyway, for this specific satellite with these channels, we see that globally we get an improvement, and we get a bigger improvement even in the tropics. And get similar results for the GMI and for geostationary satellites. So in general, we see a big improvement. If you look at the infrared channels, this is Chris here. You see it's a more mixed bag. Globally, we don't improve much, and we actually get a small degradation in the lower wave numbers. For the tropics, it's better. It's more or less an improvement everywhere. So the yeah, so in general, we get a much better result. So to conclude then, the interesting thing is that we developed this very simple methodology to estimate observation errors, non-Gaussian observation errors. It's extremely powerful. We tested it on real data. We're using, I showed you examples of using this in the UIFCW25 system. We can implement these errors, these non-Gaussian errors, in iterative standard data simulation scheme. We don't have to change sort of anything. It's just a small change at the beginning of each new set of inner loops. And we see improvements. But the interesting thing is we didn't do any extra tuning, right? There was no retuning of the system. This is just changing the errors, run it, and we get improvements. That is not something that you see very often in these operational systems, because everything is already typically very well tuned. But yeah, so now we're using looking this. We're going to work on the Rufus. Still the RRFS, the Rufus system with GSL, and we're going to look at coupled observation errors. Sorry, correlated observation errors. And that's all I have. Thank you very much.
Thank you, Peter Jan. We have one opportunity for one question. Then.
Is this turned on? So did you have the variational bias correction turned off for those experiments?
Yes. Yeah, we don't need it anymore.
Okay, thank you. I'm going to go next. And I hope I'll be able to hold on to the time limit. So this topic of this whole week is empowering collaboration. So this is a great highlight of a collaboration between NOAA, MITRE, and NVIDIA. And I'll talk about TORs and end-to-end machine learning models that combine forecasts with data simulation. And the list of co-authors is pretty long and includes contributors from PSL, NOAA, PSL, MITRE, and NVIDIA. So this slide actually speaks a lot to the priorities that Steve Smith identified earlier today about developing not better forecasts, but better products. So on the left, we have traditional system where we have prior forecast. Observations come in. Let me see. Can I? Yeah, there you go. Observations come in. Data simulation blends them together. We have model forecast that produces some products and value. What we're trying to develop is an end-to-end ML system where prior still comes in, observations still come in. We have AI-based parameterized data simulation, AI-based parameterized model, and potentially parameterized user products that generate value. And the idea is that at the end of all of this, what you want to do is to run optimization loop that optimizes parameters that derives the best end-to-end system and the best products and value. We're having a Sputnik moment right now. There is a lot of research coming out of China that shows that the ideas that we're putting forward here are actually viable, and they tested the basic elements of it, and it works. And you know, I think it's I think as a nation, it's between embarrassing and threatening that a handful of researchers from defense universities in China can produce these results while we're still talking about it. Okay, so figuring out the complete end-to-end training and model pipeline is daunting. So what are the simple problems that we can try and solve? And that's where our collaboration with NOAA, MITRE, and NVIDIA comes into play, and some of the technology came from ECNWF. So the basic idea is simple. So this is how our system works right now. So we have our forecast from a previous cycle, we have our observation, and GDAS system produces analysis somewhere in between the two of them. And then we'll have our GFS model that produces GFS forecast that will definitely be far away from, well, some distance away from observations. If we do it with AI machine learning models like GraphCast, we'll take a GraphCast model and we'll produce a forecast from GDS analysis. And in principle, a GraphCast algorithm is trained to produce something that looks more like future analysis than a future forecast. So it will be just a slightly closer to observations. Well, the problem with this is that we actually don't think our analysis is perfect. So if you work with the current system, it's kind of constrained by how perfect your analysis system is. So you cannot have a ML system that pushes beyond the limitations of your analysis. And if you actually look under the hood of GDS or IFS, any simulation system, it's kind of embarrassing that we're using only about 1% of observations. So we really can do better. So what we're trying to develop is this intermediate system that says, you know, GDS analysis is still available to us 4 times a day. Like, let's not just pretend it doesn't exist and throw it out. So let's develop a system that starts with GDS analysis, takes difference between observations and observations of GDS analysis, and produces a better analysis that you can then produce a model forecast with that should produce even a better forecast closer to observations. So the question is, how do you design this analysis system as that produces this better analysis? So you do it through the magic of backpropagation of gradients. So you'll compare your ML forecast with observations, compute gradient, backpropagate it using differentiable ML tools, and update the unknown parameters of your forecast system and your initialization system. And if you do it properly, what you're really doing, you're doing what we always wanted to do. We wanted to fine-tune our data simulation and a forecast model to produce best forecasts. Like, you're forcing that to be true. You're not hoping it's going to be true. So an example, so if you want to improve representation of water vapor burden channels in the atmospheric river, we need to simultaneously improve initial condition, improve the forecast model, and draw to the surface sensitive, well, actually, sorry, things crept in. I meant if you want to improve a 2-meter temperature forecast, you want to have better initial condition, better forecast model, less biased model. You want to draw to surface sensitive observations more closely than current surface analysis, but still draw pretty closely to our GDS future analysis at the upper levels. So the training data set, we're relying heavily on the data set produced at NOAA as part of our various reanalysis activities. So it reinforces the importance of reanalysis in the enterprise. It's really hard to do good ML development without investment in reanalysis. So we're using our what's called reanalysis-like product called UFS Replay that replaces UFS model to ERA 5 and ORS 5 reanalysis and stores results in various forms on Google and AWS clouds. We use this product called Replay Observer. We take the first system and observe it using GSI Observer for a wide variety for the whole observing system. And we're using our archive of observations, Ninja archive of observations that goes back to 79 and to present. And it's a full comprehensive archive of observations for atmosphere, ocean, ice, and land. We're basing our forecast model based on Anemoy forecast system, and here is a work that will be highlighted in detail by Tim Smith in his poster tomorrow. And this specific model is a combination of GFS and HER, so you can see, hopefully on this screen, refinement of surface winds over Conus. For this specific work, we're probably going to use a single resolution model to get started. We're also working on ML-based observation operators, and one might say we're not the first ones working on it, but we have a very specific target for it because we don't want to carry 130 2 vertical levels and 7 microphysics variables. So we're asking question, what is the minimal state of the ML variable that produces still good prediction of brightness temperatures? So for illustration here we have, I think, channel 1 of ATMS. So we have GSI observations on the top here, and you can kind of see water burden high in the tropics, but also propagation from, transport from tropics to extratropics to atmospheric rivers. There's a great example here in the northern and southern Atlantic. GSI CRTM can simulate it pretty accurately, and so can the ML forecast model trained on our replay observer. But what we're interested in our system is this quantity called observation minus the forecast in observational space. So here is observation minus CRTM and observations minus our AI CRTM. And you can see that we capture all the salient features. There is a little bit of difference here in this specific region that can be improved. But most interestingly is this ablation study at the bottom. It shows that this is a x-axis, the channel number, and the root mean square error of AI CRTM compared to CRTM prediction. And it's higher for the surface sensitive channels, but low for mid-troposphere and stratosphere channels. And what we did, we ran our AI CRTM, with a whole bunch of number of levels from 127 down to 16, equally spaced between top of the model to the bottom, and with GraphCast levels, which is 13 levels, but they peak only at 50 hectopascal. And even GraphCast levels do degrade prediction, but they're not bad. So this AI CRTM model learns something about higher stratospheric channels from a single 50 hectopascal stratospheric level. One of the last results slides, we did train we pre-trained an S operator or DA operator that behaves like a 3D VAR. So we had a whole bunch of 3D VAR increments and a whole bunch of observation minus forecasts for ATMS and conventional observations. And you can say that the bottom figure looks similar to the top. It's not as detailed. It has fewer observations going inside of it, but it's pretty good for pre-training. So finally, where we're at right now, we're we're plumbing all the pieces of this system together to actually do what we want to do, is to take GDS, compute the mismatches to GDS, and propagate it forward with an anemometer-based model, propagate the gradients backward, and update the known parameters. So that's where we're at right now. The papers coming out of China are extremely encouraging. They just show that it should work. They tested all the elements. So they didn't do the same thing, but they tested the elements that goes into this system. Summary, we are fine-tuning data simulation model to increment GDS analysis to optimize multi-day forecasts. We want to fine-tune our data simulation and forecast model against real observations. It's to be determined which observations we're going to go with, probably conventional at first. What we really want to do is focus on improving the utilization of underexploited observations like surface-sensitive channels, and specifically for our project, those low-peaking channels over the Pacific. And there is interest from our external partners to extend it to the ocean. That's it. Thank you. Time for one question. I'll go with John. John didn't get his chance last time. Oh my God, John. No, I cannot go to back to the slide. Okay, go. Apparently I can.
Provide like a Bayesian interpretation of what's going on with the green arrow here? Like what happens going from the red to the green?
It's a conversation I'm having with Peter. There is a Bayesian interpretation to it. There's a full Bayesian interpretation to it, but I'm not going to do it right now. But if you want, we can talk about it.
Talk after. Thanks.
Okay, thank you. We're going to pass the torch to Clara.
Thanks, Sergey.
All right. I am going to talk about land data assimilation developments for NOAA's global NWP system. I'll give you an idea of what we're doing at the moment and sort of how this fits into the bigger picture and hopefully demonstrate the value of this work. Before I move on though, I would like to acknowledge my many co-authors on this work, mostly at EMC, who've been working really hard on getting this implemented. Okay, so for a very quick background, all major international NWP centres use LandDA to improve initialisation of their land states, and this has been demonstrated over and over again to improve NWP forecasts. There's 2 examples of that on the right. Unfortunately, for global NWP at least, NOAA's LandDA is very far behind what is done internationally. At other centres, they have all been using LandDA for decades in their operational systems to constrain model soil moisture, soil temperature, snow amount, and sometimes also snow temperature. By contrast, in NOAA's current system, GFSV17, we have only a simple snow depth analysis, and we don't actually have a soil moisture or soil temperature analysis at all. Instead, we do this sort of retrospective correction with observed precip. And so for GFSV17, which is the next version of this system, which is scheduled for launch next year, this is going to include a major upgrade to our LandDA. This consists of 2 components, upgrading the snow DA and then also introducing a soil moisture and soil temperature analysis. If we start with the snow DA on the left, so the current system at the moment, we basically take a externally produced gridded analysis and then sort of merge that into our background. And so what we're going to do for that is remove that dependence on that external analysis and instead directly assimilate the observations ourselves. For the soil moisture and soil temperature analysis, we're going to move away from that method relying on correcting with observed precip and instead go to directly assimilating observations like is done at other centres. So I'm going to quickly introduce both of these schemes. I'm not going to go into any of the technical detail though, so feel free to come and talk to me if you have specific questions. So for the soil moisture and soil temperature analysis, at other NWP centres, this is done using methods that are different from the atmospheric DA and tend to be much simpler. The reasons for this are historical. This is what was most appropriate at the time. And in each case, the initial soil analysis schemes were based on the assimilation of screen level temperature and humidity. So those are the observations that we get from weather stations. Some centres have later also added in assimilation of satellite soil moisture so that we can get some more direct observations of the land state. However, for NWP, by far, we get the biggest improvement in forecast skill from the assimilation of the screen level obs, because you're going to fit what you the observations that you assimilate. So when we thought about how to design this for NOAA, we had the advantage of not being tied to a historical approach. And when we sort of stepped back and looked at this, we realised that now the methods that we use for the atmospheric DA are also appropriate for land DA, and so we decided to use those much more advanced methods to also do our land DA. And so what we're essentially doing is we're using the ENKF component of our atmospheric DA to also do the soil analysis. We're also initially just going to assimilate the screen level temperature and humidity, again, because that's where we get the biggest improvement in forecast skill. The system that we have at the moment is an interim system. That's sort of the first step towards where we want to go long term. I've attempted to describe it here in a schematic. So what I've got here is the current atmospheric DA system. The important details are the boxes on the bottom. That's our deterministic forecast that is used for the main forecast at high resolution. Its states are updated with a variational analysis that brings in error covariances from an ensemble that then assimilates all the atmospheric obs. To keep the ensemble, so that the ensemble also sees the same atmospheric obs, we do an ENKF on the ensemble. And so the way that we've added in the soil analysis is what's shown in red in this slide. So first of all, we've added in the screen level observations. We've also added in the soil states to the ENKF control vector. So that's now a strongly coupled analysis. We haven't yet coded a variational update for the soil states because that's rather complicated to do in our current DA system. And so what we do instead is we just upscale the ensemble mean soil moisture increment to the deterministic resolution and apply that. So just this slide here demonstrates some of the background work that we did to come up with this design. So early experiments with the GSI, just purely with the ENKF, showed that we got improvement in the low level O-F from each of these experiments. So the red is where I just add in the screen level temperature and humidity. The plots here show the difference in the root mean square error. If it's negative, that's an improvement. The aqua colour shows the improvement that we get from just including the soil states into the atmospheric control vector, into the ENKF control vector, but without adding in any additional observations. And then the dark green is what we get from both. So this is essentially a strongly coupled land atmosphere ENKF DA with the addition of the screen level obs. And you can see quite clearly there we get the largest improvement. And so that's the configuration that we opted to go with. As I mentioned before though, the atmospheric DA is the hybrid system, so we needed a solution that would work with the hybrid system. Variational methods aren't very well established for land DA, but theoretically they're very attractive, and that's where I want to go long term. But again, we've had to use this interim solution for now. So we're currently doing forecast impact tests. There's a typo there, they're actually at 25 kilometres. I had hoped to have results in time for this meeting, but we unfortunately found a very significant bug in our observation processing, and so we had to start again. What I've shown you here instead is just the O-Fs against radiosondes and aircraft for the first month of the experiment. Red is the control, black is the soil analysis. Where it's shaded, that's where the soil analysis is giving us a significant improvement. And you see exactly what we'd expect to see, those significant improvements close to the surface. And this is actually a larger improvement. I see larger improvements in the 2 experiments I've done with this sort of interim hybrid solution compared to what I get with the ENKF. Okay, so moving on to the snow depth analysis. So for this, we have opted to do a version of what is done elsewhere. So we're using a 2D VAR to update the model snow depth from station snow depth and satellite snow cover observations. This is implemented in JEDI. It is designed to very closely mimic the optimal interpolation schemes that are used elsewhere for the snow depth analysis. I'll explain later why we opted to do it as a 2D VAR instead though. And then again, we've got that hybrid system. So we need a solution for the ensemble and the deterministic member. So for the ensemble, we just apply the 2D VAR to the ensemble mean and then apply that increment to each ensemble member. Plot on the right shows the improvements that we get from the in the snow depth itself. And then these slides here show the scorecard from a forecast impact experiment. So if you haven't seen these before, it's basically lots of different metrics. Green is good. Green means that the snow DA has improved. The performance, red means it's degraded. So we do see a lot more green here than red, and particularly in the places that we would expect. The large triangles indicate high significance to those improvements. So yeah, this all looks really good, particularly if you look on the left, if you follow that day 1 of the Northern Hemisphere down, we're seeing improvements in the low-level fields, which is what you would expect. I'm a little bit disappointed that this doesn't progress beyond the first day of the forecast, and I'm looking into that at the moment. The other thing that gives me a lot of concern is if you look at the plot on the right in the very bottom row, 1,000 hectopascal, we've increased the Northern Hemisphere biases in temperature. Looking into this, what's actually happened here is that we've reduced one of the compensating biases, and that's why this doesn't actually show up in the root mean square error. So this doesn't actually concern me that much. One thing that does concern me is that we have increased a cool bias over the Rockies, and I think that might be associated with the lower quality of the station observations there, but I'm still looking into that. Okay, so this is a summary of what we're doing at the moment, which I've just gone through. So we're planning a major upgrade to our land DA. We're introducing a strongly coupled ENKF for the soil moisture and soil temperature analysis. Of course, pending successful forecast impact experiments. We'll need about another month before they're finished. So far, it looks positive though. We're upgrading the snow DA to directly assimilate observations with a JEDI-based 2D VAR. So these updates together will bring NOAA's land DA up to, and I would actually argue ahead of, particularly for the soil analysis, international standards. And experiments to date show significant improvements to the land and atmospheric states. So this is the 2 schematics for what we're doing now, the 2D VAR for the snow and the coupled ENKF for the soil moisture. Where I really want to go with this in the long term though is what's described on this slide, which is essentially a hybrid solution for both. It's both useful to be using the same DA method as you're using for your atmosphere, but also there are a lot of strong arguments for the hybrid for both. So for the snow, we've actually made a lot of progress on this, thanks largely to the flexibility of JEDI. I have to call that out. So Seganar, who's a contractor at EMC, has done experiments in a land-only system, comparing the 2D VAR, an ENKF, and a hybrid EN-VAR, and found significantly better improvement, and actually much better improvement from the DA when you use either the hybrid or the ENKF. And then in terms of the soils, we have Yanjun Gan, who works with me in series, is funded to start work very soon on implementing a 3D VAR soil moisture analysis, because that's the piece that we're missing on the soil side. And then on top of that, of course, we plan to add new observations, satellite soil moisture being the really obvious one, and also add new control variables. Snow temperature is the next one I want to add, and that's actually a project that Yanjun is also working on and has a poster on tomorrow, which I encourage you all to go and see. All right, thank you.
Thank you, Clara. We have time for one question. Peter Jan.
Thank you, very nice. Why do you treat the snow differently? Why don't you just do everything in one?
It's a good question. Basically, it's achievable. This is snow depth. I don't know that the largest impact that the snowpack has at NWP timescales is whether or not snow is present. So I actually don't know how informative the atmospheric observations would be, yet the prognostic variable is the snow depth. I actually don't know if there would be, it's an interesting question. I don't know if there'd be a lot of value in doing a coupled. Ultimately, maybe I'd like to go in that direction. The thing I don't know how to resolve is that for the snow temperature, we definitely do want to go to something more coupled because there is a lot of relevance to the temperature observations. For snow depth, I'm not sure. We can talk more about this too because there's also a very technical detail that could be a problem.
Thank you, Clara. Next presenter is Lindsay on space weather.
All right. So today I'm just going to talk about some of the things we, the JCSDA and our partners at NRL, have been doing to form an initial implementation of space weather assimilation capabilities within JEDI. So here's my obligatory what is JEDI slide. I think everybody pretty much knows. I'll just point out that most of JEDI's capabilities, or previous capabilities, are in weather, neutral atmosphere weather, and as well as chemistry, land and snow, and then various ocean and sea ice assimilation. And that, especially for the purposes of this talk, JEDI is designed with reusability in mind, which is very helpful for our rapid integration of this new data assimilation type. So just a little bit of a basics about the ionosphere. It begins about 50 to 80 kilometers, depending on how you start to define it, and extends to upwards of 900 kilometers above the Earth's surface, and is formed by photoionization from those high energy emissions from the sun. Most people are familiar that solar activity is associated with sunspots, flares, coronal mass ejections, etc. However, of course, in the atmosphere, the solar intensity also varies by time of day and also time of year. So you can see the distinct diurnal variation of the ionosphere over here on the right. And then down here on the left, you can see a depiction of the Earth's magnetic field. So these magnetic field lines basically form the grid on which most models of the ionosphere do the modeling. So a little bit of motivation on why we would study variations in the ionosphere. First, of course, there's impacts on technology such as GPS navigation and satellite communications. It just introduces some extra error into those signals. However, also what our partners at the Navy are much more interested in is the frequency and distance impacts on long-range radio communication as well as over-the-horizon radar. So our purpose of this particular study today is to form initial implementation of the ionospheric data assimilation within JEDI For that, we'll be using a basic climatological model and a sort of pseudo-cycling method, which will set up the framework for future implementation of physics-based ionospheric models. So to look at the ionosphere, most of the data is either ionosonde or GNSS. So the ionosondes are a vertically pointing high-frequency radio transmitter. It just sort of sweeps through a range of frequencies, and based on what frequency you're at and the return time to the transmitter, you can get a vertical profile of electron density. So here's an example of kind of what it looks like. And then they smooth it out using some software. And here's a map of just in general where those vertically pointing sensors can be found. Again, as I said, the other main measurement for the ionosphere is GNSS, which either is from, which gives you a measurement of total electron content, either from the GPS transmitter satellite to the receiver satellite or to the receiver on the ground. And so it is a vertically, well, along the path, line of sight integrated measurement. So down here on the left is an example of the locations of those ground-based receivers that we can use for GNSS tech. And then for our space-based tech, we're looking at Cosmic 2 due to its long record of high-quality data. However, you can also get it from a whole bunch of other GNSS measurements. So we'll be looking into those later on. So our model for this pseudo-cycling system is the PI-IRI. So the IRI is the International Reference Ionosphere, and it is a climatological model of the ionosphere produced from about 4 years of data. It's updated fairly regularly. It's considered the gold standard of ionospheric profiling or ionospheric information. And the PI-IRI was developed at NRL by Victoria Forsyth as a Python implementation of that International Reference Ionosphere in order to speed up the computation time as well as reduce the computational cost of running the IRI. So PI-IRI takes as input f10.7, or the flux at 10.7 centimeters wavelength, which is basically a measure of the intensity of the sun, as well as, of course, the date and time of year, date and time of day, rather. And then uses a lookup table of these various electron density points and gives you a profile of electron density, which we then use as our initial background in our pseudo-cycling system. So first we take the electron density from its native geophysical or magnetic grid coordinate system, which is shown by these sort of black or blue lines, transform it to a regular grid, which is what's currently required by JEDI, and then use the currently implemented JEDI observation operators, or a slightly modified version of those. Then we take our ionospheric observations from the ionosondes as well as the GNSS, convert them to JEDI's standard YOTA format, and then feed those into the JEDI data assimilation system to produce sort of an improved electronic or ionospheric state, or sort of like a analysis state. And then, since PI-IRI is not a forecast model, it's just a climatology, as a sort of stand-in for a model in order to get this sort of pseudo-cycling system set up, we'll just use a simplified Gauss-Markov model and feed that back in to complete our sort of cycling loop. All right, so status of our project so far. We're currently in the middle of this project. We have developed the YOTA converters for all of our data, so ionosonde and the GNSS data. as well as we have used that vertical interpolation operator, which we currently use for radiosonde, and tested it to look at the ionosonde data. It works fairly out of the box with really almost no modifications, just a little bit of different setup. And we have also developed that code to convert pi-IRI from the geomagnetic grid to a regular grid. And we're currently working on adding those pi-IRI JEDI interfaces now, as well as the unit tests that we'll need for all of the new code and the new YOTA converters. Next, we'll sort of work on modifying the ionospheric or neutral atmosphere bending angle operator, GNSS operator, for use with ionospheric tech. That will probably require a little bit more modification, especially than the vertical interpolation operator. Then we'll develop that sort of pseudo model code just to, so that we have the framework ready, and then test the pseudo cycling system. Right. So there are a few challenges associated with ionospheric data assimilation. One of which is, of course, the relative scarcity of observation data, especially compared to the neutral atmosphere. There's really very few data, and most of those are from the GNSS, which, as I said before, is an integral measurement and not a point measurement. So we also have to consider where along that integral to weight the measurement and how to weight that. Also, there are several pretty rapid processes within the ionosphere, which traditionally have necessitated a low data latency requirement for the data of 15 to 20 minutes. So that also further reduces the amount of data that we have. Again, and the last challenge is the localization, which my bullet got cut off, but basically the electron density is correlated not in geographic space, but along the field lines. So for example, this black point over here at the North Pole would be more correlated with this black point over here at the South Pole than it would be with, for example, the yellow point next to it, even though these are much further apart in geographic space. So a traditional localization is somewhat, or at least a localization along a regular grid is somewhat meaningless. So future work would be continuation and then completion of this initial setup of the end-to-end ionospheric system. And then we will, of course, support the implementation of current and future physics-based ionospheric models just by removing that Gauss-Markov model and inserting the physics-based model, as well as integrating any future ionospheric measurement types. And then by using JEDI's sort of easy plug-and-play code, we'll be able to apply diverse data assimilation methods in order to find an optimal strategy for the ionosphere data assimilation. And that's all I got.
Thank you, Lindsay. We have time for one question.
Yeah, that pi-IRI database that you're using there, maybe, I don't know if that's well suited for AI ML training, and then, okay, try to use it as a forecast model, not a CLIMO model. I'm from the Fleet Numerical Meteorology Oceanography Center, so we are running a Navy operational ionosphere model. So all the work that you're doing here with NRL is directly applicable, so we look forward to all the innovations that you're doing and the transition of that to operations. Thanks.
Look at all the AI implementation also as we look at the simulation methods.
Lindsay, we have one last presentation from Hyun Suk.
Two years ago at this workshop, I gave talk on the MOM6 coupling to regional hurricane forecast system, which is HAPS. Now, 2 years later, maybe it's the natural course of direction, about the ocean data simulation using Marine JEDI. So current HABs, right now we are using MUM6 initial conditions from the RTOPS DA, from the 0, 6, 12, and then 18 forecast time for each cycles. So my project is to improve initial conditions that represents better thermohaline conditions in upper ocean, with the eventual ultimate goal of improved hurricane forecast system. So the method that I employed for today's presentation is a 3D bar. It's based on the SOCA 3D bar. In here, B matrix, the K equation in this B matrix, K is the balance operator. Currently, not like the atmospheric side, we have to we are mainly focused, using the geosteric balance side. So I'm gonna touch upon this, loophole for this K, later of this talk. Okay, so we ran the daily analysis for 2022 using daily observations of the North Atlantic Basin. These are the examples of the ADT, sea surface height, over the 24 hours period in the top panels, and then sea surface salinity along the swath at the different, at the same time. But black dots on the upper panel and the cyan dots are representing in situ observations that we are utilizing. These observations are very important for simulate subsurface structures in the ocean model. Okay. So obviously SSD, these are very, temporally, not only temporally and spatially highly covered. So I'm not showing this. Next. So we have a handful of validation metrics, and the first one is the SSD, which is against austere at the 120th degree resolutions for products. And this is a time series of the correlation coefficient in the top, bias, and then RMSA in the middle panels, and the skewness at the bottom. And for free run, is in the blue, and then data simulations in orange. So definitely having data constrained the forecast MUM6 improves quite a lot by 3% for correlation, 45% RMSE, 25%, which was a negative bias, but brings up for the two the zeros, and the 50% negative skewness reductions. Second one is obviously in hurricane forecast system, forecasting ocean heat content, very important. In other words, ocean thermal currents, position of thermal currents is absolutely essential. So this is one example of the free run on the top, and on the right side is a simulated forecast period, sea surface height in shade, and also I superimpose the free run thermal front in a blue, and then visual observations in a black, and the data analysis in a green. So it shows that having the data simulation, we do have bring the Gulf Stream front right directions, and then all the separation of the Gulf Stream, bring the to southward. So middle panel time series is the measurement of the front, and the 0 is observation from Abysso, and then these are the modified Hausdorff distance over the entire 2022, shows that free run is continuously increases. It's almost 120 kilometers at the end of December, but having this data simulation in green shows that pretty much constant. It's about the 20 kilometers errors with respect to Abysso observations. And the loop current, definitely all the hurricanes going through the Gulf of America. And then this loop current frontal, again, it's very important, especially. Because of a very thick, warm layer in the Gulf of Mexico, it is very hard to distinguish of the Gulf front by using only sea surface height. So we have to use SST. And the middle time series panel, it is the same as shown in Gulf front, and it shows that in quite improvement from the mean 108 kilometer deviations to reducing almost 30 kilometers. And the bottom panel shows that the extension of the loop current, in other words, northward, and then has a quite improvement as well. Okay. Now, going into the larger scale validations, this is a comparison of the transport along the cable that AOML has been maintaining last 30 years, providing valuable data observations to validate transport. And observation is in black, and then data simulated in green, and the free run is in the blue. Okay, so all those stats here, again, having a simulated observations simulation is much better, especially during the summertime, as you see in during the July and then September and even August, the green curves close to the observations. Okay, next one is it's about the Caribbean inflow and the outflow. Okay, this Caribbean flow is carrying very warm waters into the semi-closed basins. Again, this is hotspot where the hurricane becomes generalized and then intensifies greatly. So CB2, which is 66 degree on the Gulf of Caribbean Sea, we do have a number of observations through the GOMO project, and the vertical line shows that observations at that time, different years, and then our data simulated output is in the black curve, and the free run is a gray curve. Okay, so there are almost 20 subidrous differences. Okay, so data constraint in the black line is very not only shows that seasonal variability and also reduces large westward transport, and the green curve shows that the some of transport LA1 and LA2, which is pretty much residual going into the Caribbean Sea. So pretty much black and the red curve is very similar to each other. So assume that we have pretty consistent transport comes into the not the Caribbean Sea. And then final validation is upper stratification. This is 12Z on September 17, Hurricane Fiona. Okay, so there are green dots with the black circles is at the forecast period at the 6-hour intervals. And then through this forecast period, I plotted temperature and salinity in a test diagram on the bottom left from the free run in the blue and the free, data simulations is in the green and the observations in red. So key point is having the data simulation, especially salinity at the surface, is very improved quite a lot, and the and subsurface maximum as well. So this one tells us a great improvement in the surface ocean conditions, demonstrated by 7 ocean metrics: mixed layer temperature, depth, Z26, surface salinity, salinity maximum, and the maximum salinity depth. So having, especially data constrained simulations and 26-degree isotherm, and then salinity maximum is improved from negative up to almost positive or zeros. Okay, summary, definitely improves all the larger scale and also small stratification in the upper layers. So this is pretty content, but these are the daily MAM6 analysis. Now I'm gonna go into apply this approach to the operational hurricane forecast, which requires 6 hourly, okay? Now, when you do the operation running, you have constraint of a data observation coming in. Mainly you have to take the data from GTS, often you see the data is coming in late, especially in the ADT, which is shown in a red colors. They're having 2 days delay, which is very important, as I mentioned earlier, to balance K parts. Okay, even this figures shows that that are in ADT comes in every 6 hours, but these are 2 days delayed. So I put in all the observation into that observation time rather than arriving time to GTS. So using that conditions, we have done a real-time demonstration for hurricane season this year, covering Dexter and Aaron. It's a almost 52 cycles. We run it, and then we verified 43 cycles shown on the top right. Mean absolute error for track in A, mean absolute error for V maximum intensity, C and D's are biased for wind, and then minimum pressure on the right side. So having the ocean data simulation, definitely having better scale in the initial time, which is I circled all the time. But we do have some degradation in a track predictions. So future work, yeah, we have to improve given the condition of the operational environment, how to overcome 2 days delayed ADT. I'm thinking about using machine learning in order to overcome that hurdles. And then we are exploring other options so we can improve analysis at the 6 hourly. And then bottom box is showing when we transitioned all the research, everything, we require about the workflow correspondingly. So I'm working with all the EdPIC team to get to have a more robust workflow for the future applications. Thank you.
Thank you for your presentation. We have time for one question. Or we have. And they're going to be all for you.
Really nice. Is it working? Really nice presentation, Hyun Suk.
Thank you.
I noticed that you said you ran a really long, like year-long cycled experiment. I'm wondering if you've compared cold starting and then starting the DA cycle against a much longer integration to see at what point. I'm sure they'll never converge exactly, but approximately how long you need to cycle before you get a reasonably stable solution.
Yes, we did, and then turned out that it becomes stable almost 30 days. So again, I didn't touch upon it in the cold start versus warm start. Daily analysis, obviously it's warm start. So when we apply to the operation side, we have to consider something to overcome deficit. Yep.
Thank you. I have a quick follow-up question. What was the size of your domain?
It's North Atlantic. It's from pretty much transatlantic, east-west, and then 2 degrees north up to the 47 degrees north.
Okay, great. Thank you.
Thank you.
I think we have a lot of questions online to Minku. If the moderator, the Slido moderator can, do you want to do it or do you want me to do it? I'll do it. So the main question was about why Jedi 3D VAR is better than GSI 3D VAR. And it's kind of hard, like, it's a bit of a flashback, like, you have to remember that, but.
Okay. Does it work, right? This mic. So the details, there is a story behind this 3D VAR, and actually Jedi using the same static background error coherence, just like GSI, and it's using recursive filter just like GSI. So when we run Jedi 3D VAR with GSI recursive filter with GSI static BE and compare with GSI 3D VAR with its own static BE, it's actually produced quite similar results. So I did not really put the figures side by side,
but it's actually produced very similar positive impact results when we test against, when we're using aircraft data only.
Just to clarify, so in your slides you presented today, did you use a recursive filter in JEDI, or you used something else?
It's a recursive filter, actually, with the GSI static BE when we run JEDI 3D VAR. It gives us clear positive impact. We do have our own generated static BE from 1 year GFS NMC method, but it gives us positive impact, but not as big as we directly using operation static BE.
Thank you. There is another question for you, and I'll try to read, see if it makes sense. When these models that use updated ops, will they be updating hourly or just in time in operations?
Updated ops, I'm assuming that ops means older than our time. Our data time window is half hour. That means plus and minus. Update op maybe means half hour older, minus 30 minutes. When we're using this data, we run 3D VAR, and we did not really find the update op. Okay, so it's really dependent on the model observation type. If it's up-air aircraft data, I'm assuming update op is maybe 30 minutes older, or even it's fine. Especially sounding maybe 60 minutes older. But for the surface data, we do try to use the observations close to the analysis time, as close as we can. Usually it's within 10 minutes. That's, I assume all the data means actually that's old. So in our system, we do hourly cycling, okay?
Thank you, Min. I have one question from me. So in your experiments, which data were assimilated?
Okay, so for the up-air, the experiment I showed for both analysis like 3D VAR, 3D VAR hybrid, we using aircraft data observations, and for the GTKF analysis, we're using aircraft data. We mainly show the up-air, and for the surface data, we mainly focus on the meta observation stations.
Okay, thank you. We have plenty of time, so if people have questions, please come up and ask your questions to speakers.
Question. I have a question for Peter Jan. So when you do this deconvolution step, you have this assumption that you have a good handle on what the prior error distribution is, and so one challenge we have for, say, like bias correction, for radiances, is it's hard to untangle the contribution of bias from your background state versus the obs. And so do you worry about this, in what you're doing? Is that you may have like a bias that you're not accounting for properly in your background errors that get shoved onto the observations?
Yeah, that's of course a problem. So what we're trying to use, so the ECMWF system, their ensemble is quite well tuned and or bias corrected, if you like. Yeah, so indeed we need a good forecast, errors, because otherwise, yeah, we're pushing everything in observations. If you look at the whole system, right, in the end, it might not be too bad. Because yeah, we never know, right, where the errors are, and if you look at Dirigier, whatever other method that we have out there, we always have those problems. And we don't know if the errors are in the observations or in the forecast, and it's typically a blend, and we just have no independent way to figure it out. But, yeah.
Yeah, I mean, I feel like there's nothing wrong with also just maybe like assimilating, like unbiased observations first, and then having this preliminary distribution that you use for your prior, and then using that for your deconvolution step, so it's presumably less biased.
Yeah, so our method is not an online method to estimate observation errors. It's so you estimate them, let's say 2 months of data, and then you have them for that time of the year, so they can be seasonal dependent, etc. But it's not an online method to do it. So I guess we can't really do that.
Thank you. Do we have more questions? Okay, go ahead, John.
Again, sorry, Peter, Jan. Yeah, and also, when you extend this to multivariate errors, for the case where you have, say, like, error dependence across channels, for radiances and stuff like that, do you get a unique solution when you do the deconvolution?
Yeah, very good point. So at the moment we're using Gaussian coprolase, which I don't like. So my postdoc is a very smart guy. He just started on this. But we're exploring all kinds of possibilities. But indeed, it's if you think about trying to estimate a non-Gaussian PDF in, let's say, a 10-dimensional space, yeah, you can do the best that you can. You can approximate, but you know beforehand that you won't get the exact right answer. That's a good point.
Thank you. Any last takers? Well, if there's no last takers, we have extra 14 minutes. Oh no, the moderator from online is coming.
I don't know if you could see it on there, but it's a response to Ming regarding the question. I believe Jedi 3D VR is better than GSI 3D VR. It's but one of your slides showing our MSE vertical profiles suggesting Jedi 3D VR is better than GSI 3D VR. So yeah, it's more of a statement. I don't know, so.
Yeah, I suggest maybe Minku, you can reply directly on Slido. Or write to Shugwan, who is asking this question.
Yeah, that works too. So.
Okay, enjoy extra break.
Alrighty, we're about ready to kick it off for our late afternoon session, which is Emerging Technologies, AI, and Machine Learning. I'm going to hand it over to our chairperson, Kevin Blackman. We have a couple other chairs who haven't rejoined the room yet, but they will be with us shortly.
Okay, thanks everybody for coming here. I love the name of this talk. It's Emerging Technologies. I feel like this talk next year is going to be called What's Already in Operations, with the speed of everything moving. So I'm really looking forward to this and appreciate everybody's time. And for the first talk, it's going to be Jun Wang on data-driven MLWP model for global weather forecasts.
Good afternoon. My name is Jun Wang. I will follow up with the topic on machine learning weather prediction model development for global forecast at MDC. First, I want to thank the team, those people, Ling Ling, Xiao, and Jianjun, they were doing machine learning model training, and other people who are helping with verification. And I also want to thank EMC management for the support. The content, I will talk about how we built the Eagle version 1 global deterministic system, the Eagle Solo, and then follow up with Eagle Ensemble system and some ongoing development and summary. So a very quick update on the Eagle's current status. For us, the version 1 global Eagle Solo, it is a deterministic GraphCast trained with GDAS and initialized with GFS. And global Eagle Ensemble, it is also based on GraphCast and fine-tuned with several data sets and also initialized with the operational GAPS version 12. And the results are ready on DESI. So at this time, we have 1.5 years of Eagle Solo and about 3 months of Eagle Ensemble. For Eagle Solo system, in about this time, 2024, we built a global forecast application with GFS analysis as input. We set up the near real-time experiment with 2 configurations, and I listed the code repository and also the data on S3 bucket and some preliminary results from EMC MAC. They all show the physically consistent results. And we train a GraphCast model with GDAS. GDAS is our own in-house data, and we train the model with the data using the PerlWorks cloud, which provide us with GPUs, H100 GPUs. The data set is from GFS version 16, about 3 years data. We trained the model in 2 scenarios, Eagle Solo and Eagle Solo test. So the difference is Eagle Solo test is purely trained with GDAS. Eagle Solo, we trained with ER5 and high-res recent years, and then GDAS data. So we provide products on 7 model states and 13 pressure levels, and also 4 surface fields, including total precipitation. We also generate a hurricane tracker along with the forecast. So if you would like to see the hurricane performance, you can see the data there too. This is just a summary of the Eagle Solo performance. And on the left, you see the summer. In the past summer, 500 millibar height anomaly correlation. The black line is operational GFS, and the red is ECMWF high-res, and then blue is the Eagle Solo, and green is Eagle Solo test. As you see, the improvement, especially in the longer lead time, is significantly. And also, we look into the hurricane track forecast. You see The blue lines is GFS operational, and red is Eagle Solo, and green is Eagle Solo test. And both machine learning models perform quite well, reduce the track error. On global ensemble system, the Eagle Ensemble version 1, we actually just using GraphCast, we fine-tuned with different data sets to form 31 member. Each weights we generate represent one ensemble member, and then we initialize those models with GAPS version 12. So total we have 31 member corresponding to the GAPS version 12. If you would like to see more details, we have the NOAA Office node available. Here is a performance of Eagle Ensemble. Sorry, the line may not be clear. Basically, the black line is operational GAPS version 12. The red is what we call the machine learning GAPS version. And then the green line is what we call the hybrid machine learning ensemble and operational GAPS version 12 ensemble. So the Super 62 means 62 members combined with machine learning and traditional NWP models. So I listed here northern hemisphere, southern hemisphere, tropic, 500 millibar height, CRPS scale. As you see, the performance is compatible for machine learning with GAPS version 12, but for the super ensemble, it outperforms either of the machine learning and the NWP ensemble. And I also showed some surface field, including 2-meter temperature, 10-meter wind. The same conclusion stays. Basically, the Super 62, the combined machine learning and NWP, outperforms either one. Here I will talk about some development at this time. In the past several months, we start to update the loss function in GraphCast. As you know, the GraphCast currently is used the weights for the vertical layer, it is using a pressure-based loss function. So PI is the pressure for each pressure layer. And we update that to be a density-based, as we know, because we would like to compute the total error for the global, so we think density is more, it's making more sense since it is physically consistent with atmospheric mass distribution, and also it can better represent the thermal structure. So we update the loss function to be the second row you see the function. Here you see some scores. Still, the black line is operational GFS. The GC GFS control is actually the Eagle Solo test. And then the green line is what we call GC GFS experiment. The 500 millibar anomaly correlation showed here. This is just 1 month. As you see, the improvement, you can see the improvement for both 500 millibar ACC and 200 millibar temperature anomaly correlation. Because the purpose for us to make this update is to see the vertical structure. So here I show the vertical structure of the geopotential height bias. On the left is for the northern hemisphere, middle is southern hemisphere, and right is tropical. As you see, on the each figure, top left is operational GFS, bottom is the solo test, and then the top right is the experiment. As you see for the northern hemisphere and also tropics, you see it, the reduced bias. In the southern hemisphere, in the longer lead time, it is slightly degraded. And then also for root mean square error, the vertical structure, as you see here, It is also showed improvement in the northern hemisphere and tropics, and also for the longer lead time, the southern hemisphere, the top atmosphere layer is degraded slightly. Another work, we are looking into the Eagle Ensemble. As you see, the first version of Eagle Ensemble is very simple, fine-tuned structure. And we now, when GenCast coming out from Google, we start looking into a conditional diffusion models. Since the model is, the GenCast is trained with 40 years of ER5, so the first thing we would like to see is the performance if we replace the initial condition from ER5 to GFS. Unfortunately, as you see, the performance is not as good. On the bottom figure left, you see the northern hemisphere 2-meter temperature, ensemble mean spread, root mean square error, and spread. The black line still is GFS, operational GFS. The red is Eagle's ensemble. And then the green line is the one when we use GFS as initial condition. And then the blue line is if we use ER5. As you see, if we change initial condition, the performance went bad. And particularly for this case, we're looking into the weather map. As you see, there is an event happen on day 9 forecast, but none of the ensemble members actually catch that. So that tells us there is some differences between the two models, especially initial condition play a big role. So we start to fine-tune GenCast 1 with 1 degree data, and in here we only have about the 3 years of data from GDAS. And then we changed the GDAS as input, and we tried 3 target data, GDAS, ER5, and then on the figure you see, so the black line is operational GAPS version 12, red is Eagle Ensemble for this particular case, and the light blue is the GenCast with ER5. And then the green line is the one when we train with the GFS input, GDAS as target. As you see, this doesn't help. After the training, still the performance is not good. So we look into the input data and we identify 2 fields. So basically 2-meter temperature and SST. If we replace the 2 fields with ER5 data, you got the blue line. So basically, the performance at least comparable. So that tells us for GenCast, the diffusion models, because you add noise and try to denoise when you're using a different initial condition, and those 2 initial conditions are maybe for those fields at least 2-meter temperature and SST. You
Got
have
1 minute.
Okay, almost done. When you have significant difference, then those kind of noise cannot be interpreted by the model correctly. So we are looking into this, this issue further. Okay, quick summary. So at this time, we have Eagle Solo, Eagle Ensemble version 1 ready. We'll implement those 2 versions, those 2 models into operation. The target date is later this year. And then ongoing development, right now we're transitioning MLWP development work to use UFS to ARCO Anemoy framework developed by PSL and also EPIC. And we are fine-tuning GraphCast with different loss function. Also, at this time, we are looking into different ways to improve the scientific performance. For example, also training CRPS as loss function for Eagle Ensemble. And
we're at time.
Oh, sorry, I will stop here. Thank you.
Okay, thank you very much, June. And if anybody has questions, please follow up with her after. Okay, next is coming up is Sergey with NOAA Eagle Research and Operations Pipeline.
Thank you, Kevin. June gave a great presentation of where Eagle is right now. What I'm going to focus on is describing the concept of Project Eagle as a complete R2O pipeline, research to operation pipeline. And just in case you didn't know, Eagle stands for Experimental AI Global and Local Area Ensembles. There's a lot of work that went in the version 1, and June talked very well to that. There's also people who are working on the follow-up with Animoy, and I can't credit everybody because this list keeps evolving. And there's a lot of people, but really great thanks for people contributing to the future of this project. So AI world is moving fast. So if we look at the evolution of GFS model, so with GFS 16 was transitioned to operations at the beginning of 2021. And GFS 17 is planned for transition to operations sometime about a year from now. So if I did my math correctly, so it's about 5 years of work between two major versions of GFS system. So sometime during that journey, Pangu, weather, and GraphCast papers came out at the end of 2022. And after that, the weather forecast world has changed dramatically. ECMWF, I will compare the timeline of how ECMWF has moved out and NOAA Eagle moved out on this problem. So ECMWF has started evaluating Pangu, weather, and GraphCast right away. And they saw in the first 6 months of evaluation, they saw so much promise from this technology that they stood up a AFS development team, and they have an AFS version 1 ready than 1 year later after the papers were released. And that's incredible. A year and a half later, Animoy was released, and then AFS single and AFS ensemble were put in operations about 2 years, 2.5 years after the original papers came out. At NOAA, it took us a little longer to get started, so we're about end of 2023, where we really like marched, had a meeting here in Boulder, and we started marching down that road. And one of the original contributions that were like really highlighted success of NOAA on this journey was a WolfsCast coming out of NSSL. That was done in the first year of us starting to work on this problem. The Global Eagle and HERCast. So Global Eagle came out this year, and HERCast, our local version of it, came out this summer as well. Global Eagle went from conception to demonstration in about 4 months. Like the models were already trained, but it took us about 4 or 5 months to actually package it into this user experience. And it looks like it will take another 3 to 4 months to make it fully operational in NCO sense of the word. So this experience shows that NOAA can move fast when we want to. Like, we should celebrate that. In a year and a half, in less than 2 years, we went from talking about it to hopefully having an operational system by the end of this year. And side note, Eagle Ensemble came out 2 weeks before EFS Ensemble. So in some respects, we're actually faster than ECMWF. So how does NOAA stay relevant in this environment? So we do need a new and robust R2O pipeline, and I'll talk about this today and about the aspects of it. A big part of it is unified flow platform for AI forecast. So when we have innovation within labs, we can transition it to EMC easily. We work on the same system, contributing to the same code, just like UFS does. A key to the success is robust verification pipeline. There'll be a lot of external contributions coming in, and people will be coming and knocking on EMC's door and saying, like, we have a better model than you. You should buy forecast guidance from us. And having a robust verification pipeline is essential to pick up innovations that are genuine, the ones we should pay attention to, versus just people knocking on our door. We need to draw on the strengths of community, and I think NOAA is uniquely positioned to do that. And I'll talk a little bit separating this concept of Eagle versus OGLE. And we don't have a good acronym for it yet, but OGLE, so if Eagle stands for experimental system, OGLE stands for operational system. Okay, but let's be a bit serious. So, a robust pipeline of innovation. What that might look like? This is a system that we're developing for the future of Eagle, and it's developed in collaboration between PSL, EPIC, GSL, and EMC, and with other people contributing later. So the idea that we want to take all the data sets that are relevant to us. A lot of these data sets are known data sets, but some of them will be external. Euro 5 is a great data set. Why should we not pay attention to it? So we want to ingest these data sets, put it through the training regimen, and we'll have different configuration for different systems. We'll develop a model, and we want to deploy it in the inference system in some real-time environment. And we want to do testing, validation, evaluation using MET tools, co-development with end users, and at the end we have forecast products. We have a hypothesis, development hypothesis, that doing it based on Anemoi pipeline developed by ECMWF and external partners is the way to go. There's 20 to 50 people in Europe contributing to this pipeline, and as far as I know, it's the biggest unified pipeline in the world right now for weather-related applications. So, hold on a second. Robust verification pipeline. So right now, as June was saying, a lot of verification is done out of NOAA EMC using the operational EVS system. And the EVS system is great. Has a lot of graphics. I think it's about a node of 20 gigabytes worth of PNG images that gets generated to drive this website. But it's pretty, it's hard to give it to users. It's not a transferable experience. So what we want to develop is something similar to WeatherBench, where we design the experience, the verification experience, and users can verify their own forecast, or our own developers can verify it easily without having access to everything that's available on WCOS. So GSL is developing this amazing package called WXVX. It's a package that's based on Mat2Go, so it kind of packages the Mat as a Python tool. And it automates all these verification steps, and the most exciting features that we have about it, it's verification against observations. For a lot of work that we do, we just can't make progress without verifying against observations. And that tool will be available for community as well. So Eagle community, there's this great graphic that I'm not going to go in details that EPIC put together, but the idea is that Project Eagle is aspiring to deliver the best AI models for US by leveraging the best of US weather enterprise. EPIC has a role to play, National Weather Service has a role to play, NOAA Research has a role to play, and so does a larger enterprise. We work with cloud service providers, with IT companies, and that's the vision of how this is going to succeed, and that's exactly how we work right now. So a few words about the operational wing of Eagle. It is incredible that after Eagle went into real-time demonstration in the middle of this summer, early this summer, there is a real project to make it operational by the end of this year. What it means to be operational, because Eagle runs 2 times a day, I think one now, but could run 4 times a day. So what does it mean for it to be operational? So a lot of sticky points become around these bullet points. So data residency, to get the initial conditions from operational computer in time to run Eagle requires special plumbing. Output of Eagle should go in certain locations for it to distribute it through the weather service enterprise. The performance needs to be monitored by staff that we have confidence in that model works well. It needs to be reliable and secure, which means it needs to run in some hardened locations. Forecaster interpretation. If it's an operational model, that means forecast needs to be trained about it. So that's a big part of why this takes time. And resources. A lot of people come to us and say, look, we have we can give you resources to run this system. But for a product to be operationally certified, it needs to run out of resources that operations can control. Because if operations doesn't control the resource they run on, they cannot guarantee that this product can actually be sustained. So let me just so what is Eagle today? There is a web page called No Project Eagle, hosted by Epic, that describes the scientific configuration of this project. It has a link to verification page from EMC. It has a link to the graphics from DESI, managed by GSL, so you can look at this forecast. And it has a link to both the GitHub repository for the Eagle models, trained weights that June described, and to the output on Node. So what Eagle could be in the future? Just a quick reference, I have this graphic of no readiness levels on the right, and it goes from 1, which is basic research to acquire knowledge, to 9, deployment to use meet operational mission requirements. So these numbers here in these 2 columns is my guess of what we're at for readiness levels for state of the art in the world, first column, and at NOAA. So atmosphere only, the state of the art is 9. AFS is deemed operational system. At NOAA, we're transitioning somewhere between 8 and 9, and probably by the end of the year we'll be at 9. Is our model as good as AFS? Maybe there's a skill gap, but we don't know yet. We need to run it through our verification pipeline. For regional atmosphere, I would say we're ahead of the game, and same thing for storm scale. Hurricast is in a demonstration environment right now. It is run every day, and we will be collecting statistics to understand how it performs, and hopefully sometime within the next 12 months it will be at readiness level 9. WolfCast, the storm scale system, is an on-demand system, so it's kind of hard to decide what really level 9 means for it. A really big development we're excited about is nested atmosphere, where we're training on a combination of GFS and HER, and I encourage you to see Tim Smith's poster upstairs tomorrow. And it's as advanced as anything else in the world, and we hope that that will provide results that will get us excited about making it an operational system. Coupled GEFS-like system, week 1 through 4 model. We don't really, it's still in the research environment everywhere in the world. There is no operational coupled medium-range weather system, AI weather system right now. We're experimenting with it, so we're somewhere in level 3. Coupled seasonal, kind of weird level 3, but there are developments out there that you might say it's level 5. So we need to make some choices. Do we go with somebody else's development, or we keep maturing ours? Data simulation, I think we're lagging a little behind, and we should be catching up. And question marks, I'm sure there are other applications. Hurricane comes to mind, ocean modeling comes to mind as well. Okay, what's next for Project Eagle? 6 to 12 months. I think we'll be seeing some of the nested development to mature. I mentioned Hurricast and WolfCast already on archive. In the next 12 to 24 months, we will migrate to Anemoy, and you should go back to AI training from Monday to see kind of the experience that we're building. We plan to release verification pipeline against observations. We'll have new AI systems, Hurricast, WolfCast, nested Eagle, coupled model will probably be all within Eagle pipeline. And we need to work on developing the release strategy. So we have version 1, so how do we go from version 1 to version 2, version 3, and so forth? That's it. Thank you.
Thank you very much, Sergey. I think the same. If anybody has questions, please meet up with them offline as we're at time. Thank you very much.
Kevin.
Okay, and up next we have David Hall on enhancing the UFS with NVIDIA Earth 2.
Hello, everybody. Thank you for inviting me here today. I'm excited to speak about our NVIDIA Earth 2 system. And basically talk about the AI tools that we have to offer. Does this thing work? Yes, it does. Good. So when we first started out with this, we were kind of like, okay, is AI going to take over completely? Is numerical weather prediction going to reject AI? And at least at the current status of readiness, I would say that the two are complementary. So it's best to learn how to use these two things together to the best of our ability. Numerical weather prediction respects known physical laws. It handles unprecedented events that are out of distribution from what it's seen. It respects causality, which is a good thing. And trust has been gained in these systems over many, many years of development. AI, on the other hand, has some new and exciting things that it has to offer. It's really fast, so you can create 1,000+ member ensembles, 5,000, 10,000, however many GPUs you have, buy more. Instant kilometer scale downscaling and prediction. You can eventually, potentially do continuous data assimilation. Even the idea of real-time forecast updates where a new observation comes in and immediately you can get an updated forecast. And of course, because it's a very small model compared to the traditional models, it can run potentially at the edge. Like when you're on a ship or something, you have no connection to anything else. So by combining these two, the best of each, you can create a potentially enhanced forecast system, if that's not already a term. So at NVIDIA, we've developed a whole bunch of different AI models over time, and we continue to explore out in every direction. These are not intended to compete with anybody, but really just to show what's possible in the space. So we started out with ForecastNet, which was sort of the first quarter-degree weather prediction model trained off of ERA 5. And now we're up to ForecastNet 3. We have CoreDiff, which is for downscaling. We have Stormcast, which is our attempt at a regional model. SDA, score-based data assimilation, which is our first attempt to, at least attempt to look at data assimilation from an AI perspective. We've recently produced Climate in a Bottle, which is a pretty cool compression technique for making your data set 1,000 times as small, so it's portable. And we have the DeLeeSim model, which is a collaboration with Dale Duran at University of Washington, where we're trying to make an Earth system model by coupling lots of components together. So ForecastNet 3 is our latest version of our ForecastNet model, and it's undergone a lot of evolution. The most recent version has a bunch of great updates, and it is trained in parallel to be very, very fast. So you can train it on very large systems and therefore fine-tune on very large systems. It fully respects the spherical geometry of the system, and it's very stable. It has a new loss function that ensures spectral accuracy while also ensuring local accuracy. And so we've run this thing out for 90 days, and the spectrum looks exactly the way it should, as you can see here. I think this one only goes out to, well, not 90 days, but the spectrum looks really good no matter how long we run this thing out. It was designed to, and that makes it very stable. So here's an example of some of the different ensemble members that you can create with it. So you can create as many as you want. We test it typically with 5,000+ ensemble members. And if you look in the paper, you'll see that we found some interesting bifurcations that happen in hurricane paths that you only find after the 500th member. So below that, you get the main course, and above that, you get like potentially other things that you might not have seen. So a large number of ensemble members really helps you fill out the probability distribution function of what might actually happen. So there's value there. So after we did the forecasting, we said, okay, we need to get to higher resolution. We want to go to like 1 kilometer. And then we're like, all right, well, maybe 3 kilometers is a little more reasonable. We did some scaling studies and said, doing this globally might be really expensive. So let's just try downscaling first. So CoreDiff was our attempt at downscaling, and we did it first over Taiwan, and it was quite successful. It's basically a model where we combine a UNet with a diffusion model. The UNet sort of does the large bias correction from the coarse state to the fine state, and then the diffusion model fills in the details generatively. That was successful, so we moved on to the United States and created CoreDiff US. And so it's a pretty useful tool if you want to get some high resolution likely states out of your lower resolution forecasts. Here's some examples of the things you can get over with CoreDiff US. You see the coarse input on the left, our prediction in the middle, the ground truth, which was ERA 5, no, not ERA 5, HER, on the right, high resolution rapid refresh. It looks good for our various predictions of wind and precipitation. And the precipitation category in the bottom right wasn't even in the input. We can generate fields that are missing entirely because it has that information stored internally in its latent space and can reconstruct it as you need it. We moved on from downscaling to now attempting to do regional forecasting, and that's what Stormcast is about. So it basically takes a similar idea. It takes the global like GFS initial condition and combines it with a HER initial condition, and then says what's the forecast after this, and it uses the same basic idea as CoreDiff, this two-component system that works together. And by combining these two, it basically does regional forecasting without all the complex boundary condition stuff, because it learned that implicitly from the data set. So it combines the core stuff and the fine stuff to give you a prediction, and it does a pretty good job. Stormcast version 2 is a whole different beast, but I'm not supposed to talk about that yet. I think this is a movie, but I'm not going to count on that. So here's some examples of what the states look like. And yeah, no, it's not a movie. It didn't get embedded. Okay, so moving on. So here we can see the accuracy of Stormcast, and we find that it matches a high-resolution rapid refresh quite well. The dotted line is an individual one. This is fractional skill score over the probability match mean. And the ensemble is the dashed line, and you can see the solid lines of the HER baseline. And you can see that it's very comparable. The ensemble does quite well, and the individual ones do pretty well also. And I believe there's been progress since this. So next, let's move on to our data assimilation attempts. So we're like, okay, so the missing thing here is, okay, we can do forecasts, we can do downscaling, we can do regional scaling, but what we really need to worry about is we still have to use someone else's initial conditions. We would like to be able to do, data assimilation ourselves. So we looked into score-based data assimilation, which is basically a diffusion model that learned all of the probable states from the high-resolution rapid refresh data set, and then given a few points from observation, says what are the most likely values to be filled in around it. And so you do a denoising thing, holding these values essentially fixed, and it fills in the rest of the space with a state that is probabilistically likely, and you can do it multiple times to get an ensemble. So here's the basically the training process. It's not all that interesting. So I'll move on to this one, and you can see that the state that it generates is pretty good, considering that there's only about the inputs are only 40 individual stations throughout Oklahoma, and then the outputs have a lot of realistic features that you would expect from a HER state in it. I was at a conference in Bonn a couple weeks ago, and there was a lot of progress on AI data assimilation in various forms, but since I don't have a long list of those projects in front of me, you should go look into that conference. It should be all online at this point, and there were a lot of interesting projects from like Brightband and other companies. So then we have the NVIDIA DeLeeSim model, which is our deep learning Earth system model, which is a collaboration with Dale Duran's group at University of Washington. And basically his idea is that if we couple enough components together AI-wise, we can make an Earth system model that could be competitive with traditional Earth system models, but just like all these things is 1,000 to 10,000 times as fast. There's a lot of value to be gained from that by being able to explore different scenarios and large ensembles and things like that. So these are some early examples from his work where he coupled an AI atmosphere model together with an AI ocean model and was able to get amazing stability and very good statistical reproduction of hurricane statistics across 1,000 years. Not under a climate change scenario, but under the assumption that the climate stays the same. But it shows amazing stability, and it's a good start. Since then, he's added a sea ice component, which he talked about recently, and I guess there'll probably be a publication on that very soon. ClimSim is another project that we've collaborated on. It's about producing stable machine learning physics, and I haven't been doing a very good job, but each of these things, as you go along, you should be thinking of how we could use these together with the UFS system. This isn't like we're trying to compete with it, but these things could all help amplify the UFS system. Anyway, so in this case, we're working with the E3SM model, and we're doing a high-resolution nest of a very complicated, expensive physical parameterization. And we created an AI emulation of that, and you have stability problems with that because once you plug it in back online, these things tend to explode. But they found with the ClimSim project that if you apply certain like clipping and physical constraints to it, it becomes stable and accurate and quite successful. So this is a generalizable technique for combining a hybrid of basically a dynamical model with AI physics. A more recent project of ours is our NVIDIA Climate in a Bottle, where our idea was if you have a data set that is just enormous, in this case the ICON data set at 10-kilometer resolution, I believe, or was it 5? Anyway, it's a very large data set, many petabytes, and you can't really move it around, you can't really work with it unless you have access to that computer that it's on because it's huge. So what we did was we trained an AI model to represent the data, and that the model itself is 1,000 times smaller. You can download this thing, move it around, even expand it on a local computer, and reproduce the states that you would select from that same set. Not the identical ones that are in ICON, but you can get all of the statistics out and play around with the model and make it interactive, so it makes the data essentially portable, usable, and interactive. And it can do a lot of good things. We did a lot of measurements with it, and you can see that it has a lot of beautiful properties. It gets the diurnal cycle correctly, seasonal cycles correctly, spectra are well matched. And then the lower right-hand corner is an interesting application where you can say there's a hurricane here. So you can condition it and say there's a hurricane here, and it'll give you a state that's consistent with having a hurricane there. So you can kind of do experimental things with it and then roll those states forward with another model. Thank you. Yeah, so here's some output from the Climate in a Bottle. So you can see that the output is not low resolution or fuzzy. It's just as high as the original with some pretty plausible looking output. This is visible light, and this is the temperature field, outgrowing long wave radiation, surface winds with a tropical storm down there. And then I zoomed in on each of these a little bit so you can get a little bit higher resolution view. And you can see that everything looks pretty nice. So it does a pretty good job of compressing and decompressing the data set and making it usable. So we have something called Earth-2 Studio, which started as an internal tool just for our own use. We're like, there's all these AI models out there, and we need to be able to compare them side to side and see which ones are better and what their properties are. So we built this own tool for ourselves to do this interactively. And then we thought this would be useful for other people, and it turned out to be very popular, so we've expanded upon that. So Earth-2 Studio gives you a lot of tools to play around with these models and get into them, get used to them, see what, intercompare them. Everything that we do in Earth-2 is open source and free. We're not trying to charge anybody for any of this stuff because the more AI, the better as far as NVIDIA is concerned. And also the more GPU acceleration also, so any way you want to go is fine by us. But so you can take this tool, download it, try it out. It's really easy. Like in just a few lines of code, you can try out one of the models and get some output and start playing around with it. So we're also having a get together October, GTC DC in Washington. You can meet the people that develop these tools, see all the latest stuff. There's always cool new stuff to be seen. So please join us there if you want. Thank you.
Okay, we're pretty much right at time, but I think we do have time for one question if someone has one.
1 minute ahead.
Hey, David, I'll ask a really fast question. In the score data assimilation, are you guys already accounting for like forecast uncertainty, both forecast and observational uncertainties in that calculation? That means, is that a true Bayesian inference process as like we think of in data assimilation?
No, I wouldn't say so. I mean, the uncertainties are learned implicitly from the data, and so you can generate a whole bunch of different states and get some idea of what the uncertainties are in the system just by sampling it. But I wouldn't say that it's very carefully handled in that way. I think the score-based data assimilation is sort of our first step into this, and I wouldn't say that it's been rigorously validated in that sense.
Got it. Thank you.
Okay, perfect. Thank you very much.
Thanks, guys.
Okay, next up we have Corey on enhancing WAFcast calibration and sharpness with a probabilistic loss.
All right, so does this top button, is this the pointer? Is that, oh, okay. All right,
Thank you all for coming. I'll start by acknowledging my co-author, Monty Flora, who really led and pioneered the development of WAFScast, but has since left us for greener pastures in the private sector. And I'll also acknowledge the main contributors to the spring forecasting experiment activity that will comprise part of this talk. So I'll begin with a quick primer on WAFScast. For those unaware, WAFScast is a GraphCast-based emulator for the NSSL Worn-On Forecast System, or WAFS. And so therefore, it issues forecasts on a 3-kilometer grid. It uses 18 members, just like the WAFs, and focuses on 0 to 6 hour forecast times. And these forecasts are valid on the WAF's 900-kilometer grid. So really meant to focus on regions where high-end weather is forecast. We produce the current version produces the standard set of predicted fields that we've come to expect from emulators. But in addition to that, we also have composite reflectivity and rainfall, which of course are pretty important for our application. Now, one of the things that really differentiates WAFScast from other emulators is the fact that it was trained on 10-minute data, and that these data are forecast data. We could have trained on WAFS analyses, but we hypothesized that we would actually get better forecasts if we train on the WAFS forecasts rather than the analyses, and we've since empirically verified that hypothesis. By training on the 10-minute forecast data, we create very high fidelity to simulated storm evolution as represented by the WRF model that is at the core of the WAFs. We've trained on 136 cases from springs 2019 through 2021, so not exactly a gigantic training data set. And if you'd like to see more about WAFScast and see some of our deterministic performance verification statistics, I'll refer you to our recent GRL paper. So I'll spend the next few slides convincing you that WAFScast is pretty awesome. So here we have 6-hour loops of a squall line forecast from WAFScast on the left, and then, oops, here we go. WAFScast on the left, WAFS on the right, and then we have MRMS as truth in black and blue. So you can see remarkable similarities between the NWP and emulated forecast. This is slightly cherry-picked. I will admit that it's not always this good, but it's not that rare that it's this good. Now, of course, one of the main advantages of the WAFScast is that it runs a lot faster. Namely, we can generate an 18-member forecast in about 1 minute on 1 GPU versus around 10 minutes on over 1,000 CPUs with the WAFs. Now, to really drive home the point that we are actually simulating storm dynamics pretty well, I've got composite reflectivity on the top here, and then a vertical cross-section looping on the bottom, showing updrafts within each of these storm cells. So this is WAFS on the left, WAFScast on the right. The red are updrafts, and then the green contours are the convergence, divergence dipoles associated with those updrafts. And then we have cold pool. So it's a virtual potential temperature perturbation in the lowest, like 2 kilometers. And again, you see remarkable similarity between the WAFs and the WAFScast. So the WAFScast is emulating the WAFs with very, very high fidelity. So those were deterministic results. Now I'm showing ensemble results. WAFs on the left. Oh, I keep doing that. WAFs on the left, WAFScast on the right. These are neighborhood maximum ensemble probabilities of composite reflectivity exceeding some high threshold around 40 or 45 dBz. And again, you can see remarkable similarities between the two forecasts. Now, of course, you can also see MRMS truth in the contours, and you'll note there are large errors in both forecasts. So here I'll also make the point that WAFScast, the way it's trained, should not be expected to improve upon the WAFs. It can't correct errors in the WAFs, not systematically, because it's trained to emulate the WAFs. So this is one limitation of WAFScast, but there are some ways to actually go beyond WAFs, and I'll get back to that at the end. Okay, so we actually showcased the WAFScast in this year's spring forecasting experiment in the hazardous weather testbed in Norman. So we did next day evaluations where participants evaluated and compared the WAFs and the WAFScast. during the month of May. And they were focused on deterministic and probabilistic forecasts of composite reflectivity from the two systems. So the main takeaways were that for the first 3 hours of forecast time, the WAFs and WAFscasts were often nearly indistinguishable, and some of the participants explicitly noted that they're very, very similar. However, as we got to the longer forecast times out to 6 hours, the expected smoothing that we've come to expect with deterministically trained emulators started to really become noticeable. And so storms started disappearing and generally becoming too smooth in the WAFscast, but still looked pretty good. The smoothing in the WAFscast is not as bad as what we see in deterministically trained global emulators. So as part of the evaluation, the participants were asked to rate WAFs and WAFscasts on a scale of 1 to 10. So you can see that for both the probabilistic and deterministic forecasts, they were rated relatively similarly. These gaps do increase a bit as we go to the longer lead times, again, because of that forecast smoothing problem. But I would say overall very encouraging performance of the WAFscast. And it's always important to get these subjective evaluations in addition to the looking at objective metrics, which often lie. So again, a concern with the deterministically trained emulators is they tend to be too smooth. Oftentimes they don't forecast extremes well. But with WAFscast, that's less of an issue. So here I'm showing the Texas flash flood event from earlier this summer. We have WAFs on the left, WAFscast on the right. No verification, because here I just want to make the point that the WAFscast is actually able to produce very high 6-hour rainfall totals, exceeding 10 inches. But these are ensemble 90th percentiles, by the way, for both. So despite being deterministically trained, the WAFscast in this form is still able to forecast extremes, which is very encouraging, which means when we go to train WAFscast in a generative manner to overcome the forecast smoothing, it's less of a lift for the WAFscast. We don't have to lean as heavily on those methods. So again, so WAFscast, even in its basic form, deterministically trained, it has decent ensemble spread. It's not terribly smooth, even at the longer forecast times. So why is this? Because with the global emulators, again, oftentimes very underdispersive and too smooth. And this makes sense because they were trained on the ERA5 data set. And because of the unavoidable errors in those reanalyses, these deterministically trained emulators, they can't learn the butterfly effect. The butterfly, so the rapid growth of low amplitude perturbations is completely masked in the ERA5. It's swamped by the errors in the reanalysis. But WAFscast does not suffer that limitation because, in a sense, our training data are perfect. It's the forecast data themselves. There are no errors in a certain sense. So theoretically, we can very closely learn the representation of the atmosphere, at least as simulated by the WRF model, and that without generative training. And here I'm illustrating, in this graph I'm illustrating the growth of very, very low amplitude perturbations with time in the WAFscast, and this is the expected behavior. This is not something we see in the deterministically trained global emulators. Now, all of that said, I mean, there's still some smoothing and underdispersion in the WAFscast, and it'd be good to mitigate those. So recently, I've been focused on training a new version of WAFscast with CRPS loss. So this requires the generation of mini ensembles during training, so that we can generate the CDF that needs to be passed into the CRPS loss equation. So here I'm following the AIFS strategy. So I'm using the almost fair or approximately fair, something AF CRPS loss that they use, and also their noise injection method that they use to generate these mini ensembles. So by doing this, the model is learning to generate individual forecasts that, when combined into ensembles, produce near optimal spread and much sharper forecasts. And here, when I say near optimal spread, I mean with respect to the WAF's truth, because again, that's, as far as the model is concerned, WAF's is truth. And the forecasts are sharper since we're avoiding that double penalty effect, whereby with MSE loss, you tend to over-reward smooth forecasts because you're avoiding the double penalty. Okay, so looking at some results, initial results from the CRPS loss training, we've got WAFs in black. Okay, so we've got spread, so ensemble spread and composite reflectivity left, ensemble mean error middle, and then the spread error ratio on the right. So I'll just focus on the right-hand panel. So the WAFs in black is under dispersive, which is expected for storm scale ensembles. The vanilla WAFs cast is still more under dispersive, as expected, but the CRPS trained WAFs cast is actually about as well dispersed as the WAFs. Now looking at storm location errors computed by generating storm objects and computing centroid displacements from MRMS storm objects, we see much better correspondence of the CRPS trained WAFs cast in blue to the WAFs in black. And then now looking at ensemble fraction skill scores for high-end composite reflectivity, essentially comparing the gaps between the solid and dash curves on the left, which is for the vanilla WAFs cast, and then on the right for the CRPS trained WAFs cast. Again, we're seeing improvement across the board in all of the verification metrics we look at. And finally, to really illustrate the increased sharpness as a result of training with the CRPS loss, these are vertical velocity spectral ratios for the original WAFs cast on the left and CRPS trained WAFs cast on the right. Ideally, these ratios would be about 1 for all scales greater than 2 delta x. And of course, that's not the case because of the smoothing. But we do see much more energy at smaller scales in these CRPS trained WAFs casts, which is exactly what we want to see. So again, these are initial results. Everything I just showed were valid on a 450 kilometer domain, and the WAFs runs on a 900 kilometer domain. That training is in progress. Maybe I can get even better results with additional tuning. But aside from that, we've got lots planned for WAFs cast. WAFs is transitioning to the MPAS die course, so WAFs cast will follow suit. We're already looking forward to training a 1 kilometer MPAS-based WAFs cast, so hopefully that will be running in real time, not too far into the future. I'm very interested in pursuing the AI augmented data assimilation technique that Sergey talked about earlier today. And I think particularly for storm scale ensembles, which tend to be very biased in their initial conditions, that anything we can do to improve those initial conditions will be critical to really unlocking the potential of this idea of huge forecast ensembles, because if the entire ensemble is biased, you don't get as much value, obviously, from simply adding more members. Looking forward to adding more predicted fields to WAFs casts, things like CAPE, storm relative helicity, updraft helicity, maximum hail diameter. I actually have a training run in progress right now. We'll see how that turns out, but also interested in training separate UNet post-processors to try to diagnose these additional fields from the standard WAFs cast fields. We'll be running WAFs cast in real time in next year's spring forecasting experiment, hopefully with these additional predicted fields and with the CRPS trained version of WAFs. And as Sergey talked about earlier, WAFs cast will ultimately be integrated into Eagle and will then hopefully be running in real time whenever the WAFs is running. Thank you for your attention.
Okay, thank you very much, Corey. And I think just like the others, if you have any questions, please get with Corey after. Okay, next is Ling Lu.
Hello,
virtually?
everyone. Can you hear me? Okay.
Yes, we can hear you.
Okay, thanks. That I am going to start to share my screen. So can you confirm you can see my screen? Do you actually see the actual video as well?
Yep, they're moving.
Oh, you
just
can
one
see that.
second.
Can I hide this for some reason?
Yes, just
Oh.
exit out.
Just close exit. So you can still hear me right now, right?
Yep, we can hear you and we see the slides. Perfect.
Okay. So I'm Lin, presenting a physics-based machine learning algorithm for satellite in situ high-frequency radar data simulation using West Coast forecast system, joined with a joint effort for data integration framework. So this project was led by Dr. Pat Burke at NOAA Center for Operational Oceanographic Products and Services. And we wanted to express our acknowledgement to NOAA Co-ops modeling team and Rutgers University worked tirelessly with the Joint Center of developing this ROMS JEDI framework and the computational resource that was offered by the Weather Service EMC high performance computer. That those are the reasons that the project was here. Compared to the previous AI talks, this project was more like a brick and mortar, low bandwidth and high latency type of research. I hope you'll be enjoying it as much as I do because I would offer a lot of science and thoughts instead of just the operational pipeline, that kind of system design kind of topics. So initially, the JEDI platform was actually coupled to the North Atlantic Basin so-called HAFS domain, right? So the actual goal was to apply JEDI to sort of improve the efficiency of the hurricane forecasting in the North Atlantic Basin. And then quite inspired by that, I think Rutgers University and Joint Center worked together to extend that platform for a different ocean model, what's called regional ocean modeling system. So it's a long and hard work for the past 4 years. Hernan Arango from Rutgers University worked with the SOCA team to develop this wonderful model. And now we were able to apply this model to study the very unique issues in the West Coast, such as coastal upwelling, the red tide and drought, the heat that are occurring in the recent couple of years. And we were able to apply this interface for observation integration system that was so flexible that we could incorporate different satellite observations like SST and sea surface height and marine glider in situ observation and high frequency radar observation in the West Coast. We can do our QA, QC for super orbing, for thinning, for this marine glider data and HF radar data, including the high resolution satellite temperature data. So I believe everybody is quite familiar with this framework of JEDI by now. That I want to pinpoint the part that I use the most as a user is the integrated observation data analysis. That it's so flexible that you can write almost every single kind of observation into JEDI, into this unified system, and then you can do some integration and analysis with these data. And also, JEDI works with many different models that we are focusing on the marine component of these models, specifically the ROMS and the MOM6 model. At Coastal Ocean Service, that we mostly apply these regional ocean models to the JEDI application. So a little bit background about WCOFS, the West Coast Operational Forecasting System. It's a huge domain. It's about 300 by 1,000 kilometer in terms of the size. And it has a similar kind of grid resolution, about 4 kilometer domain resolution. It extends from the Mexico in the south to the British Columbia, Canada in the north. Initially, the ROM's Jedi model was designed for a portable, low-resolution model so that everybody could contain it, could test it, and to do the C-test on the Jedi platform. So when we took over the model, we need to do significant modification to the original low-resolution model because WCOPS is a high-resolution model and it has a lot of grid points and it was a huge domain. So, and then the other thing we have to do is to add the tidal component into the model because the original model does not include the tidal component. So with that, we did a tidal verification, and you can see from the figure B that the actual Jedi prediction and the coastal service station mean water level are agreeing pretty well to each other. I'd like to apply Jedi to a specific case study, right? So the actual application of Jedi system. So we identified this interesting case in 2024, early July, that there was a 5-degree of increased temperature throughout the past 5 years at around the Death Valley latitude in the West Coast. So we wanted to see if or not we can identify the probable cause of this heat anomaly. So quite inspired from yesterday's panel discussion about AI, like AI was everywhere in our life. That can AI answer questions such as, can AI help me to conduct these very traditional impact studies that we often do with data simulation and especially Jedi. Like we have this no DA run and the runs that only simulate, for instance, marine glider, the runs that only simulate, for instance, satellite observation, the runs that combine look deep into the ocean and actually identify the heat content of this gigantic, the ocean heat content that would tremendously reshape the temperature that we breathe in, the air we breathe in, because in the West Coast, we have this tremendous upwelling event because the wind blows from the southeast and then carries over the cold ocean water from the deep sea. And if that was the probable cause, then we should calculate the heat content and the barrier thickness, like how these ocean was carried over, and would it be stopped by this barrier thickness? So Jedi did that. So these visualizations are done by Jedi. That was speaking of physics. Speaking of mathematics, when we look at the actual statistics, you can see that Jedi was capable of identifying the kind of data simulation group that could produce the least model error and the maximum correlation coefficients. And it identified this upwelling, the temperature plunge from the offshore to the West Coast. However, if you look at the figure B, that this is the unfiltered raw look of the forecast error, that there is an error that present across all data simulation that was done by our first attempt with Jedi. So there are different approaches to reduce those errors like QA, QC, but can we engage AI to do something about it? So that's where this neural network structure came into place. I wanted to extract the best part of all models and reassemble them into such a system that we took the most flexible Jedi Yoda component. And then we look at the neural network part. This convolutional neural network was supposed to be able to help us identify the very detailed, convoluted details, the features of the 2D satellite image, such as sea surface temperature and high frequency radar. For the in situ observation, the profiles that we would approach this feed-forward deep neural network for us to train the data and to have a lot of training data and then see if it was able to predict. And so this connection was built upon this thermodynamics of WCOPS. So this is, I believe we have seen this a lot in the previous presentations. It was quite inspired by a UNIT-shipped deep connected convolution neural network, but instead of having both an encoder and a decoder, I use a regression and deep collected regression for the right half of this decoder part. So the advantage of this is it's easier to understand about the regression, and it's easier to alter the architect if the physics needs to come to play a role to constrain this model. Here are the parameters that's listed that I wanted to point out that standardization method was we apply zero approach instead of ReLU because of the normalization that it had. And we also partitioned this model domain to 4 different parts in order to increase the amount of training data by 4-fold. And we did this for both SST and the high frequency radar, as you can see. So these are the physics that was inspiring us to configure out the JEDI YODA input and the AI output. So I'm not going to dive into the details, but that here these are the 5 input observations that we put into the system. And here is the first look at the training performance. It was great because it's training verification. So this makes me worry a little bit about overfitting because there are 200 epochs that we could, towards the end, we could slowly testing if we could reduce the epoch to remove this overfitting, because by overfitting, the model might lose its capability of making prediction. For instance, this is the prediction. You see degradation, but however, it actually does not look bad, especially the spatial details of the heat plume and the front. And then in order to improve it, I would suggest we could looking at the local minimum of the loss function and to handpick the lowest loss function and then use them to reconstruct our model prediction. And a similar approach to HF radar. So these are the model parameters that engaged, and I just wanted to show that this was inspired by a publication in 2021 that in order to obtain the surface current velocity, we could train the surface wind, right? That's the dominant factor in the West Coast because of the Ekman flow. Here it's the results of the training. And again, near perfection for the training performance, but a certain degradation, but definitely improved when I compare to when I have only 1 or 2 months of training data. This has like 4 months of training data. So it has great potential that if you increase your training data to 1 year or even like longest 10 years, if I had time, I only had like 2 or 3 months of time to do this work, then it could, I expect the performance to be improved. And the next thing we have to do is this approach is we need to denormalize the data because of the zero approach requires the normalization. And we have to do padding at the boundary because we have to stitch together the 4 different domains for both HF radar and the SST. And then, so here is how it looks. And I want to point out that my title has a physics constraint model approach. So here you see the actual error, the standard deviation of the entire 1 month of training, right? That how do we constrain our model with this error? Like we have to be aware of this error in order to improve it. And similar story goes to the HF radar. And this was really easy for us to obtain the Jacobian of the first layer, from the input to the first output layer. From here, you can identify the dominant factor of this neural network, right? Like for instance, for region 4, that was the T temperature, air temperature, and then the Q air, and so on and so forth. So in your future training or even data assimilation, you would consider to probably exclude non-dominant factors to improve your model efficiency. For the in situ observation training, it was based on this classic deep neural network. And we basically trained 1 location. For instance, this is an example based on the surrounding locations, because based on the classical entrainment theory of the temperature and the salinity. And here is the model verification performance was near perfect. And when we use it to predict the 1 month prediction, and we see actually AI minus observation is doing a little better than the WCOF's model performance. Although there is a slight bias, negative bias present that, again, that for the physics constraint. Yes, great. So lastly, but not least, that you can see JEDI AI scales the computational time by 10 times less compared to the actual classical models. And with that, I conclude my talk. If I have a minute to take one question or so, that would be great.
Thank you very much. We'll have to take questions online, but yeah, thank you very much, Lingmu.
Sure. Were you still able to see my screen, or it's disabled?
Okay, and we're pulling up the slides right now, but next is James Conley on AI-enabled UFS, Fortran Dakuta code translation for accelerated computing, and they're pulling up right now, so just 1 second. Okay, the slides are up. Over to you, James.
All right, thank you. Hi, so my name is James Conley with Booz Allen, and today I'm going to be talking about Fortran Dakuta code translation for weather prediction modeling. So today we'll kind of walk through a high-level summary of our approach, dive into some of the details, and then take a look at how we validated and benchmarked the runtimes between the original Fortran and the translated CUDA, and then finally talk about where we see this approach going in the future. All right, so Fortran to CUDA code translation. Before we dig into it, I just wanted to take a minute to introduce both myself and Booz Allen. So we at Booz Allen are an advanced technology company with clients across the government and civilian sectors. We have a team dedicated to working in the civil space and identifying common challenges that our clients face. As for myself, I'm a software engineer by trade, not a weather modeling expert, but I work as part of our CTO AI group, where we build out rapid prototyping software solutions that leverage AI and other technology. So when our civil team brought this opportunity to us, we felt it was a really interesting application of some of the AI work that we've been doing. All right, so let's get into it. As many of you may know, existing Earth systems models can often require extensive computational resources to run, and it can take a long time to run these simulations, especially on large data sets. It can take many minutes, even hours to run these simulations. So our challenge was, how can we accelerate this process? As many of you may have heard, GPUs can be used to accelerate data processing, but it's not as simple as just buying the fanciest GPU on the market, plugging it in, and expecting your code to run faster than it does before. The code has to be optimized to run on the GPUs properly and harness the parallel processing power that they bring to the table. A lot of these existing models are written in Fortran, which out of the box doesn't run on GPUs. So what we did was leverage an existing solution called Booz Allen Precog, which is essentially a low-code data orchestration platform, to build out an automated workflow that leverages generative AI to translate the Fortran code that these models are written in into a CUDA-enabled language that we can run on GPUs to accelerate the performance of these Earth systems models. During our rapid prototyping phase, we targeted a single component of the WRF model to translate, and we're able to validate and benchmark the code that we produced and show that it runs over 80% faster on this GPU hardware. Like I mentioned, we only targeted a single component for this limited prototype, but we feel that the approach that we built is reusable and scalable across different components of the model and potentially other models like UFS in the future. So in summary, by leveraging advanced technologies like generative AI and NVIDIA CUDA, we were able to run our systems models on GPUs to accelerate their performance. All right, let's get into our approach. At the beginning, we did a lot of initial research and discovery into the modeling space and identified two models that would be good candidates for this prototyping effort, one being the WRF model and one being the UFS. In the end, we chose the WRF model mainly out of accessibility and to be able to focus on building a robust approach rather than spending time getting a model spun up and building all the infrastructure that comes along with that. We already had the WRF model up and running in an internal AWS environment so that we could just get cracking on it and start rapidly building out this prototype solution. With the WRF model chosen, we wanted to kind of narrow down the scope of this effort so that we could really validate the performance of the new code and run it in isolation rather than having to run the entire model itself so that we'd be able to rapidly iterate over different code changes and things like that. So within the WRF model, we narrowed it down to the atmospheric radiation component, and within the atmospheric radiation, the solar eclipse module in particular. We chose this mainly just out of the ability to isolate it from the rest of the model, build a unit test for it without dependencies on the rest of the WRF model code. And it was kind of a smaller code base for us to kind of build this initial prototype in order to scale up later on. For doing the actual code translation, we took a look at a couple different methods. There are non-LLM libraries out there that do enable interlanguage code calls between Fortran and another CUDA-enabled language, but we felt like these didn't really fit the bill of enabling existing Fortran code to leverage GPUs. So that's kind of where we landed on the idea that we really do need to take the existing code, translate it into a new CUDA-enabled language, but it's still functionally equivalent to the original. But we needed it to be in kind of this CUDA-enabled language in order to leverage the GPUs properly. In order to do that translation, we felt like LLMs would be a great fit. With our LLM approach chosen, we needed to figure out what language we actually wanted to translate the code into. There are a few different CUDA-enabled languages out there, but in the end, we chose CUDA Fortran as the target for our code translation. We chose this for a couple reasons. One being that it uses native Fortran syntax so that anybody familiar with Fortran will be very familiar with what CUDA Fortran looks like, and it'll be very easy for them to integrate it into existing Earth systems models. Furthermore, with CUDA Fortran, it's easy to integrate into existing Fortran code. All you have to do is swap out the compiler to the NVIDIA CUDA Fortran compiler, and then you're good to go. So it's really easy to integrate with existing models. This is opposed to other CUDA-enabled languages like CUDA Python or JAX. We just felt like translating it to an entirely new language introduced a lot more room for error and would be harder to integrate back into the existing code base. All right, so this slide shows a high-level diagram of the workflow that we built out. On the left, it starts in GitHub. So this is where the WRF model source code is hosted. So it's an open source community repository that anyone can contribute to. And this houses the original Fortran code that we want to be translating. Using Booz Allen Precog, we are able to automate the process of pulling the source code down from GitHub and then feeding it to the Claude LLM via API calls, running it through a series of iterative prompting to actually do the code translation. Once the code is translated, Precog gets it back and then pushes it up to GitHub again in the form of a pull request. What the pull request does is it allows the scientists to easily review the code changes in a nice visual diff and be able to implement it back into their code with a click of a button. In addition to just the code changes, we have the large language model actually explain what the translated code is doing so that we provide a more contextual description to the user for them to implement back into their code. So they have a better idea of what's actually going on rather than just implementing the code blindly. So this slide walks through a step-by-step breakdown of the workflow that we built out. What you see here is a screenshot of the Precog UI where we built out this low-code workflow, as I mentioned before. On the left, step one is cloning down the GitHub repository. And then we actually have the source code in Precog that we can begin feeding it to the large language model. The first prompt is to have Claude identify sections of the code that would be good candidates for parallelization. Not all code will benefit from parallelization, so it doesn't make sense to just blindly translate the entire source code. We really wanted to pick out specific sections that would see the most benefit. We found that the large language model was actually really good at doing this and identifying things like double nested for loops that are good candidates for translation. Once the sections of code are identified, we have the Claude actually translate the code and generate the new CUDA Fortran. With the new CUDA Fortran, we finally have the model explain what the new code is doing to get that contextual description and background that we can feed back to the user. With all of this information, we write the code to a file, commit it, and then push it back up to GitHub and create our pull request, where we have this full package for the user to review the CUDA translated code and understand what it's doing, merge it back into their model. So this workflow that we built out is scalable and can be applied to larger code bases, swapping out the GitHub repository to look at different models, or even changing out Claude for a different LLM. All right, let's look at some of the benchmarking results that we generated. So we were able to validate and benchmark the translated CUDA code we produced and show that we increased or improved the runtime by over 80% of the work model component. We also validated that the output is within single precision floating point accuracy of the original, demonstrating that we can deliver substantial time savings without changing the results that the model produces.
You got 3 minutes.
Thank you. Here we have some graphs that actually break down the runtime comparison. On the left, we just have a geographic visualization of the solar eclipse model that we translated, just so that we can sanity check and validate that the translated code is actually producing the results we would expect it to. As I mentioned, it's within floating point precision of the original. On the right, we have the runtime comparison between the original Fortran and the translated CUDA Fortran. On the graph in the middle of the slide, you can see that there's a significant runtime improvement using the CUDA Fortran. On the x-axis, we have the number of geographic data points included in the simulation. So you can see that as the size of your simulation grows, you see greater and greater benefits from the GPU acceleration. This enables you to do a couple things. One, it can run your existing simulations much faster, but two, it also allows you to run much larger scale simulations in the same amount of time. Finally, the graph on the far right shows the ratio % speed up of the new CUDA code. And you can quickly see as the size of your simulation grows, you see drastic improvements from running it on the GPUs. Finally, I'll just mention a couple places we see this going in the future. One, like I kind of mentioned before, we targeted a single component for this prototype, but we do believe that what we built out is definitely scalable to more components and models in the future. We would really love to scale this up to larger code bases, potentially even thousands of lines of code, rather than just the few hundred we did for this translation, and even apply it to other models like the UFS. We'd love to explore how this can be integrated with existing infrastructure, potentially translating certain components of the model and integrating that back in with existing modeling infrastructure. We know that there are similar efforts going on in the space out there. So if any of you guys are doing similar stuff, we would love to have a conversation with you and see where this goes. Again, my name is James Conley. My contact information is here on the slide. Feel free to reach out over email. My colleague Lauren Bernard is there in person at the conference, so you can talk to her with any questions too. And yeah, if we have a minute for Q&A, happy to take any questions right now as well.
Okay, thank you very much, James. We do have exactly 1 minute. If anybody has one question. Otherwise, we could move on because we have a panel right after that, so I don't see anything. So if you have any questions after the fact, because we were actually just having a conversation about this yesterday, so feel free to reach out to James. So thank you very much.
Thank you.
Okay, if we can just get one more round of applause for all the presenters, and thank you very much.
Thank you so much to all our presenters, and thank you for everybody who stuck around with us so far. We have one more session for you. It's going to be really interesting. I helped design it. I'm very excited about it. And we're going to hand it off to our session chair, Alicia Bentley. All of our presenters for this session are remote, by the way.
Thank you very much. Can everyone hear me, just to check? We good? I hope so. All right. Well, hi, everyone. Thank you for coming to today's 5 p.m. Mountain Time panel discussion. It's titled Creating Better Feedback Loops Between Users and Developers. Again, my name's Alicia Bentley, and I'm the Global Verification Project Lead at the Environmental Modeling Center. And our in-person moderator is Rusty Benson. So thank you, Rusty, for doing that. Today's panelists in alphabetical order, not the order on my screen, are Cody Berry, Michelle Harold, Logan Poole, Letitia Williams, and Castle Williamsburg. To start, I'd just like each panelist to give about a 2-minute introduction to themselves and to answer for us the following question. From your perspective, what is the single biggest hurdle between a user's request and a developer's keyboard? And I think we'll go in alphabetical order if we can. So maybe Cody Berry, we can start with you.
Sure. My name is Cody Berry. I am a research meteorologist with NOAA's National Severe Storms Lab. For about the past 9 years, my research has focused on using NOAA's hazardous weather testbed as a mechanism to solicit user feedback on experimental products and tools that are under development at the lab. Historically, users in the HWT have been National Weather Service forecasters, and we use mixed methods like focus groups, interviews, and surveys to gather feedback, as well as some other things like blogs and case walkthroughs. I have primarily focused on broadcast meteorologists and emergency managers as users in this space. And to answer your question, in my experience, the biggest hurdle, I think, between a user's request and a developer's keyboard is understanding why the user is making the request and how it would make their job easier. There have been several times when developers have more innovative ways of fulfilling that request than what the user is recommending. So understanding the motivation behind that request is key to unlocking a developer's creativity.
That's excellent. Thank you, Cody. Next up in alphabetical order is Michelle Harold.
All right. Hi, everybody. I'm Michelle Harold, and I'm calling in remotely from very exotic Boulder, Colorado. I'm over in the Foothills Lab, but I co-lead the Developmental Testbed Center's Met Plus team, which supports and develops the Met Plus verification package. We've already heard a lot about Met Plus this week. So at its core, Met Plus is a verification framework that can span a wide range of temporal and spatial scales and enables both objective and reproducible evaluations over a broad range of forecast applications. So in addition, it's really available. It's a community package that's used both heavily in research and operational institutions, such as NOAA's EMC, as well as the US Air Force. So what kind of makes this work especially exciting for me is kind of being at that nexus of the space among developers, scientists, and decision makers. I also get to do it along an incredible team of both collaborators and folks here in the DTC. So our team consists of software engineers, scientists, as well as statisticians. So that can both allow for having scientifically rigorous as well as operationally useful outputs. So really looking forward to today's panel. Oh, I forgot to answer the question. From my perspective, I guess I would say the biggest hurdle between a user's request and a developer's keyboard is really translating diverse needs into action. So also, for being honest, funding, that kind of drives development as well. But our Met Plus users do span both research and operational communities. So that just means that requests can really range from experimental ideas to sort of more mission critical type of requirements. So in this current environment, while we would really love to do everything, we can't do everything all at once. So the real challenge is actually aligning priorities. So understanding what the user needs, and then also understanding the full scope, and then looking at what the developers can actually realistically deliver. So, and how that fits within sort of like the broader Met Plus ecosystem. So I guess that would be my answer to that question.
Thanks, Michelle. Appreciate it. And we love working with you too. So thanks for Met Plus. Next up in alphabetical order is Logan Poole.
Good afternoon, evening, everybody, depending on where you are. Some of us are more east than others. I am Logan Poole. I'm a meteorologist, forecaster, probably the very basic user that turns sort of a lot of the work that we've seen in this conference into actionable things for the public. A lot of the products that the public is going to receive are sort of parsed and synthesized through folks like me. So I've been at the Weather Forecast Office as a forecaster in Jackson, Mississippi, which has the reputation, earned or otherwise, of being one of the busiest convective and otherwise, we produce probably as many or more products than almost anywhere else in the country. It's a very active area, and we find ourselves using these tools all the time. I've been a forecaster in the private sector before. I've done media and broadcasting. I've done development work. So it gives me a little bit of insight into how some of this works. I wouldn't count myself on any sort of level of what many of our speakers have been speaking about so far. And I try diligently to the best of my effort to stay up to date on some of it. And that's part of my answer to the question in a moment, but it can be a challenge. Most of my work is operational fundamentally, and I've been doing this for a number of years. Been working in the weather enterprise for a little over a decade now, and all different facets of it. So to answer the question, what's the biggest hurdle between the end user and a developer? To me, I think it's sort of twofold, depending on a directional exchange of information. It's how do you find that common fabric? For us, I have told you I have a little bit of insight into how some development can work. Don't count myself a professional, certainly not anymore. But at least I feel like I can formulate some questions in a way that can be applicable in a coding sort of framework or a development framework. And I know how to ask those questions. And then the reverse side, coming from a developer, I sort of have an idea of what might be possible. Not to deviate too much from that answer, but we deal with that. Cody mentioned dealing with emergency managers and social sciences aspects. We deal with some of similar things where in that reverse situation, we are sort of the experts and the high level technical thinkers. And those folks are the ones who might struggle to be able to communicate to us. So we are dealing with it in reverse. So we have some familiarity to it, but I think there is a real strong need to figure out a better way to talk to each other. How do we help each other understand how do we ask the right questions, and then how we can formulate those coming backwards to be able to answer them in a way that's parsable.
Awesome. Thank you, Logan. Really appreciate it. Next up, I think the thing went away, but it's Letitia Williams.
Hello, everyone. I'm excited to be a part of this panel. I'm Leticia Williams, and I'm with the National Weather Service in the Office of Science and Technology Integration. And I am a part of the Service Delivery Evaluation Program, which is the brain trust for a lot of our social scientists. I myself am a social scientist, and my background is in science communications. So how scientists are able to communicate their information to the public, as well as how the public is able to understand and use that information. So to kind of pick up on what everyone has mentioned, I think a hurdle between end users and developers is really what Logan was touching upon, is that communication aspect of things, and making sure that the end users can clearly communicate what their needs are so that the developers can serve those needs. I think sometimes there's a disconnect between that. And so then the end user isn't able to get the information that they really need for the products or services that they're working on. So I would think that would be a great place to start to resolve some of that disconnect between end users and developers.
Thank you, Leticia. I appreciate that. And I'm hearing some common themes already, which is good. Last but not least is Castle Williamsburg.
Hi, everyone. Good afternoon. Castle Williamsburg. I am a contractor supporting NOAA's Weather Program Office. And in that role, I am on the research transition and portfolio analysis team as the lead. And like Leticia, I also have a background in social science. I'm a visual risk communicator by training with some atmospheric science degrees as well. But I think what's most fascinating to me is over the last 10 years or so, I've been in the research transition space of thinking about how do we transition meteorological research and development, specifically from like research to weather service operations. So this panel, I think, is really important and valuable in that space. If I had to provide an answer, I think it's going to be very similar to everyone else's comments, but I might take it a little bit higher level, which is, I think within the research and development process, I think we often forget that people are at the center of it. We're always really hyper-focused on what the outputs are, what the deliverables are, but we need to be more focused on how do we get there. And to me, that all starts with building relationships and trust between the developers and the end users. Because as Leticia mentioned, we're not going to feel comfortable sharing what our problems are if we don't trust those people, if we don't know what their intentions are. So it takes a lot of important work between the developers and the end users both coming together and having that dialogue, as Logan was kind of talking to. So I really think we do have some really nice commonalities here, and I can already see we're going to jive well throughout this panel.
I agree. Me too. Well, thank you, everyone. That was a great start. I think, based on everything that has already been said, maybe we can dive into this practical, actionable advice sort of at this point. If you'd like to answer my next few questions, please raise your hand. You can even do it visually. I could probably see it that way. So my first question for anyone who would like to is user comments, as we've kind of heard about today, can sometimes be not what you're looking for. Sometimes they can be kind of vague. For example, a user might say something like, the new interface is too confusing to me, but they don't maybe explain why. So what would your process be, or your team's process be, for translating that relatively vague feedback into an actionable task for your team? Okay,
I can give it a shot. Yeah.
Oh, Cody,
sorry.
then maybe Logan. Thank you.
I think we both did. Yes. Cody,
Perfect.
go first, please.
Okay. Let me lower my hand so I don't forget. Sometimes vague user it's challenging, but it can arise for a variety of reasons. In my experience, sometimes users fixate on really vague or simple concepts related to a tool or product because they don't understand the tool, product, or information. For example, someone might fixate on not liking a color scheme, and kind of refuse to delve in deeper into the information being provided if they're just overwhelmed by the complexity. Sometimes you just have to accept that you may not get particularly useful feedback from that user. Often you just simply need to try to use a variety of probing questions into what they find confusing, why they find it confusing. But sometimes you do just have to accept unusable feedback.
Thanks, Cody. I think, Logan, sorry about that. You can go. Thank you.
No, you were fine. That was to give me a moment to think about this a little bit more. So I'm going to take it one step further, and I guess one of my communication preferences or methods I like to use, I'm a bit of a storyteller, so I'm going to relate this something from my perspective, and then hopefully people can understand what I'm getting at. Something that happens for us as forecasting warning meteorologists sometimes is we'll be on the desk and, we issue the tornado warnings that you guys are familiar with, severe thunderstorm warnings or what have you, issue a tornado warning. We feel really good about that forecast, that estimate. Sure enough, tornado occurs, and we go out and we're the same ones who go and investigate that. And one of the things that we really we find valuable is talking to the people that were impacted. And we may talk to them and they'll be like, this happened, this happened, this happened. But something that happens with some degree of regularity is we'll reach some resistance where someone might say something along the lines of, well, this wasn't warned, or we didn't have a warning, or you guys didn't warn this properly, or what have you. And first and foremost, we're like quantitative scientists, and we take pride in our work. And the first thing you think is, I did have this warrant. I was right. And that's not really helpful though. If I tell them that, no, you're wrong, what have I gained from that? So I think to relate this back to the original question is how do you deal with feedback that can be vague, or even in this case, outright wrong, is to sort of ask the questions of why do they feel that's the way that things are? Maybe maybe you have something coded in your program or what have you, and you know that you have a way for the thing that they're criticizing to be done, whether that's a split panel or whether that's some sort of GUI thing that you've done, and you say, I have that in there already, you're just wrong, and you ignore that. The better question might simply be to inquire a little deeper and be like, okay, so you feel like you didn't have that tornado warning. What methods do you have to receive warnings? Maybe that's where the communication breakdown is happening. And to dig a little deeper into that feedback, and Cody mentioned those probing questions, And sometimes you can gather useful data points and insight into the user experience, even if what they're saying is patently objectively false. Even so feedback may not always be something that's apparent at first bash, like first glance, and sometimes you have to resist that tendency to want to defend yourself, especially if you feel like you might be being attacked and something might be wrong about your work. There might be a better approach that can help people out. Maybe they're the wrong ones in that situation, but so that's how I would say that can be leveraged, is to think about the people first.
Thanks, Logan. I'm hearing a lot of like dig deeper, probe a little bit, which is good. Castle, you're next.
Yeah, I'm going to echo that a little bit and take some pieces from both of their comments. But I think we kind of touched on this in the beginning, but I think vague feedback is often a symptom of the users not understanding what they actually need. And it's not always their role to tell you what they need. Sometimes it's the developer's job, I think, also to dig deeper. So I'll kind of double down on that. But I think in addition to like vocal feedback or like survey feedback, the other really great thing that I would suggest is like observational methods. So if they're saying, you know, this system is confusing to me, why don't you watch them use it and ask them to walk through what they're clicking, what they're doing. It's called Think Aloud interviews, and have them kind of walk you through the process and their workflow of helping you understand, like, oh, this button is in the wrong place, or, you know, it helps give you more specific feedback that can be at least beneficial. So I think in addition to some of these other mechanisms for feedback, actually sitting down, taking time to shadow the user or having them walk through something out loud can make a huge difference in understanding, you know, what their workflow looks like and how the new product or service you're testing fits into that or not.
No, that makes sense. Well, actually, Castle, you kind of led me. I'm going to go out of order with the question. Oh, Leticia, like my name, but with a beginning different. Please go.
Go ahead, because if there's a flow, I don't want to interrupt it, and I can probably chime in my thought in another place. So
okay. No, it made me think about when you just said a different question I thought of, which is like, how do you effectively involve engineers in the feedback before a solution is defined? Because we're talking about like digging in deeper, and we're talking about shadowing, and we're talking about like, how do you get the engineers involved before you already know how you want to fix it? Cody.
We've actually done this recently in the hazardous weather test bed with phased array radar data. A lot of the algorithm developers for that project don't know much about operational forecasting and warning operations. So we have found it useful, even just early on, to have them come in and observe an experiment in the hazardous weather test bed. It gives them a better understanding of how forecasters use the data, what types of products they're using when in their workflow, as well as like what types of decisions that they're making with operational and experimental products and tools. And it really helps them sort of build empathy and better understand what the forecasters are looking for, and can help them become better developers. So a lot of times we'll kind of phase them into the process where initially maybe they're just an observer, and, you know, the next round of the experiment, maybe they're actually asking questions. You know, sometimes just assigning roles can be really helpful, even if it's one of the most minor, but probably the most important role we can ever give someone in the test bed is turning on the voice recorder, because it's so easy to forget to turn that thing on. But if you don't capture what everyone says, it's really difficult to then analyze what people said. So just easing them in to being part of that data collection.
No, that's great. I like that a lot. Leticia.
Yeah, and this is perfect because it does touch on what I was going to say previously, because Cody just said it and Castle said it, and it's probably one of our favorite words, which is workflow. because the workflow can tell you so many answers to a lot of questions that you don't even know that you have. So for us, often when we're collecting data, we'll often just ask the end user, like, what do you do in your day? When you start, like, what's the first thing you do? And have them walk us through our day. And then that tells us how they're using the products, how they're using the data, and we can relay that information to the engineers. And sometimes the engineers, that's insightful for them. Our team just did a project with our air quality modelers here at Weather Service, and it provided insight into how a lot of air quality forecasters are using the data that for things that like they didn't even think about. And so that's where you can provide that insight, where on the modeling end, like it may not even be on the radar, but it's a really easy way to collect very useful feedback that can add to the development process.
These are awesome, and they make me like, I'm glad this is recorded because I need to go back and do these things. Michelle, your hand's up.
Yeah, just to add a little bit more onto one to kind of loop in the engineers. So with Met Plus, it's a software. And so we deal with software engineers very frequently. Most of our team is comprised of software engineers. So if you would ask them, they would say, bring us in immediately. So as soon as something kind of comes up, we usually try and bring them in as soon as possible, because early collaboration in the end means fewer code rewrites typically, because they're really the experts on the code. But also kind of speaking to the workflow, which has been a really common theme. Engineers love workflows. So, bringing them in early, but then also having them have that user engagement. So with Met Plus, we've often had some like focus groups or like these advanced training series where you get the folks actually using the output in the same room as the engineers. So then there's just a lot more understanding and empathy when you have to like use the data that you've created, and then they get an understanding. And so I'm also a big fan of getting the engineers and the scientists together because that often helps reveal either problems in the code or helps better understand what the end user wants. So then the outputs can match like what their scripts and things are. So I preferably prefer to get the engineers involved as soon as possible. And I think they prefer that too, at least in the Met Plus team.
That makes sense. Oh, Castle, your hand's up.
Yeah, I'll just echo that and say, one of the I think early engagement is critical, but I think we also have to be realistic of like engineers and developers have other things to do too. They can't like engage with end users all the time, as much as I would love that were true. So I think we need to think about this almost as like some sort of tiered engagement. Like we need to bring them in from day one to understand what some of the basic requirements and some of the basic like technical specifications are, so that you can start down the right path. It would be trying to like build a house without talking to an electrician. Like you get to the end and you'd have to redo the whole house because you didn't think about electricity. So I think bringing them in at early day one is so important and critical, so that, as Michelle mentioned, you don't have to do code rewrites. You don't have to pay a lot of money on the back end. But very similarly, you have to have the end user engaged from the beginning too. Otherwise, it won't fit into their workflow. So it's this constant balance of, how do we bring people together without overburdening people in their time for collaboration? Because I am a huge proponent of collaboration, but if we collaborated all the time, we wouldn't have time to do the work. So thinking about like logistically how to balance that is so important.
No, that's outrageously true, especially at EMC. Like, I'd love to meet with Michelle all day, but one, we can't, and two, that would be impossible. I think where I'd like to go from that is going back to the user and the communication, right? So before we talked about if it was maybe vague or even unusable feedback, but what about when users come to you with like a fully formed idea? Like they come with like, I need this, and they don't maybe tell you why. And maybe you hear that and you're like, well, maybe they would actually benefit more from this, and you already have an idea. So how do your teams or the people you work with determine the user's underlying need? Or is it more efficient to just build what they asked for, I guess, is my question. Cody.
I think it kind of depends on the context. So in the hazardous weather test bed, some of our experiments, last anywhere between 3 and 8 weeks. So, there's a new group of people rotating in every week. So that ends up being a lot of feedback to kind of sift through and really prioritize. How many people are asking for a specific thing? If it's, if one person is asking for one thing, that's going to be a lower priority. So it's trying to figure out what's easy to implement, what is sort of in most demand, from the variety of users that have looked at it, and trying to come up with ways to prioritize what to implement. And then also having to look at things like, what are we funded to implement, if that becomes a factor in it. So yeah, I think it's a multifaceted process to try to figure that out. If we accommodated every single request, it would be a never-ending process where we would be changing one thing and then turning it around and changing it back sometimes.
Absolutely. No, prioritization is huge because we can do a lot, but we can't do everything. And I agree completely. Logan, your hand's up.
Sure. I think and Cody mentioned this is entirely based on context. Sometimes someone just has a really good idea and you're just like, yes, obviously we should do that. Thank you for telling me. That's why we're soliciting your feedback, because now you've given it and it is great. But other times I think it could be like, wow, that is a pamphlet of ideas that you have there, and a full-time person for 3 years would have a time trying to get through that. And this goes back to my original point about sometimes the end user doesn't even really know what's feasible. Like, I think it could be easy to take that as being like, this person's a crazy person and I need to kind of like tamp this down, because almost when I worked in development, you almost always come across someone who's like, I have an idea. And it's like, that's great, but I only have so much time. So I think maybe instead of, you try to redirect that question in certain situations from like, what do you want me to do? And redirect it back to, what do you want to do? And maybe by asking that question, you can, again, develop some sort of fabric of understanding and be like, okay, well, it seems like the idea is that you want to be able to more quickly access this, or you need to incorporate this into some sort of routine or workflow. And here's maybe some other tools or ideas that we can accomplish that in. So trying to redirect the question a little bit without being, again, it's really easy, but without being defensive about it or off-putting. We have to really bridge this gap. It's really, really important. And I think it can be tough for folks in my position, operational folks, to feel comfortable asking these questions because we feel so out of our water sometimes, so out of our element. And then from the flip side, on the developer side, actually trying to go the extra step to understand a little bit more. So yeah, that's what I would have to say in that regard.
Thanks, Logan. No, it makes sense. And it goes back to what somebody said earlier about being comfortable even asking. And I think that's huge. I know that that's a big thing for me. Castle.
Yeah, I would just echo what people are saying and share that they're coming to you for a reason because you're an expert. And I think the thing we often forget is that end users are also experts and the developers are also experts. They're equally experts. And I think they're coming to you for a reason. And because of that, they should be open and flexible to, hey, you may have some really great ideas that could help benefit this problem that I'm facing. Otherwise, they could just, I don't know, give it to an AI or something to create it for them. So I think that there is this desire of this back and forth, in my opinion. It should be a partnership and not a transaction. So there should be some level of co-creation that's happening between the two entities. And I think sparing, like if it's a contract, for example, there may be specific things you can and can't do. Obviously, the context is important. But I think in a general sense, if they're coming to you with this problem and this question, then they should equally be willing to say, hey, we're willing to listen to your expertise too.
No, absolutely. I agree with that. I know we're almost at the half hour, so I guess Rusty in the room, I'd like to ask if anyone in the room has a question, potentially for this panel. So I'll give it a second.
We do have one person. John, please go ahead.
Yeah, thanks for the discussion. I represent the Navy. It's a more tighter focus group, and we have our own sort of feedback developer sort of processes. But NOAA is quite large, and so I was wondering, like, how do user feedback get distributed amongst NOAA, because it may touch on many different branches or not. And I have participated in NOAA like satellite data user groups at one time, and they funded people to come in specifically for a user group, and I thought that was a great process. I don't know if that's still funded for these different aspects, but I really am interested in how the feedback gets distributed and said, okay, is this a training issue? Is this a communication issue? Is this a research and development issue or equipment sensing type of issue? So I'd like to hear your thoughts on that. Thanks.
Cody.
I feel like I'm always jumping first. I think that, first of all, across NOAA, we have about 10 to 12 test beds and proving grounds that do a lot of pretty targeted interactions with users. I hesitate to call them experiments because I know from a social science standpoint, as my dog barks now, they are not experiments from a social science standpoint. So a lot of them are sort of hazard focused. There's a fire weather test bed. There's a hydrometeorological test bed. Hazardous weather test bed focuses on severe weather. We often collaborate with the satellite proving ground for the satellite evaluation. So a lot of that then becomes bound typically to funding from CASEL's office, the Weather Program Office, and then becomes very research project grant based I will now pass it off to CASEL.
No, I would just add that I think this is a place we could do better in NOAA is we have so many great end user opportunities like the test beds. The social science team does a lot of great focus groups. I think if I had a criticism, they get locked away in reports and then people don't get to see them. There's not a lot of collating end users. I think there could be, it'd be really great if there was like an end user database of like anytime a end user need pops up in any of these types of engagements, it's being collated into a single place. I think we could do really well at kind of better understanding where some of these things are, because one of the fears I have is that there's some duplication of going to talk to the same end users over and over and over because we don't have as much coordination as we do. So I think if there was an opportunity for improvement, it would be in that area.
That makes sense. I agree with that, even from a modeling standpoint. Somewhere people have so much feedback for us that we are not getting, and it's very hard. Logan.
Yeah, I'm almost going to repeat what CASEL said there, but this is just from an internal operational standpoint, just to sort of second that. I have participated in probably half dozen or more HWT, OPG, test bed projects, and I love it. It's one of my favorite things every year that we get to do sometimes, but there's also some biases that are inherently going to be brought into that. One of the things is because it's primarily volunteer based. So you're getting a selection bias problem. Are you going to continue to get the same exact radar expert that keeps applying for the same radar HWT over and over again? It's like, wow, Weather Service is really good at radar, apparently. No, it's just that one guy who's half the sample. And like CASEL was saying, we don't really discriminate really very well of like recording who said what or who did what. And understandably, we shouldn't necessarily publish like, oh, Logan Poole had this to say or what have you. But there should probably be some metric or databasing, a way to sort of reduce that bias and also to be able to share that data more. And I definitely think that we have resources across the Weather Service and across NOAA to where we could touch more folks and get more people involved. And I think that should be a real priority to get a really good solid sample of this feedback.
Oh, that's great. And I know this was NOAA centric, but if anyone had a non-Weather Service NOAA response to that, feel free. Okay, go
I'll let
for
the
it.
NOAA people handle that. No, I'm good.
Okay, you're good. All right. Well, that was a great question. Even if there are more audience ones, and I've been trying to like check Slido. I don't think we have any for our session, so that's fine. But that's good. So in our last 10-ish minutes here, I guess I'll ask my closing question and give the panelists like 2-ish minutes to answer it. So to close, I'd like you to leave us with a final thought. What is one key action and or even just mindset shift that all of us could maybe implement tomorrow to start bridging our communication gaps wherever we happen to work? Castle.
I'll go first so Cody doesn't have to. For me, I think I would say that I kind of led with this at the beginning, but I think we need to focus more on relationship building and trust building between end users and developers, and let the tool, the technology, whatever we're developing be kind of a byproduct of that engagement, instead of leaning into it and kind of starting with, what's the tool? What's the request we're fulfilling? What's the model change we're doing? That should be coming from and emerging from the great relationship and trust that you're showcasing and you're sharing. And the second thing that I will say is, I think we need to be a bit more agile in the way that we're thinking about end user engagement and development. I'm sure that word has been thrown around a lot this week, but I think we're moving in that direction. But I think we need to be more iterative in the way that we're thinking about development, instead of it being, hey, I delivered this thing and now I'm done. Bye. It should be, hey, we're delivering one version of this and we're excited to work with you and iterate on what the next version looks like. And I don't think, in my opinion, we do that as well in NOAA, but I think we're moving in that direction. But I think the end user engagement would really benefit from that iterative development and aspects.
I couldn't agree with that more, Cass. So I'm glad you talked about iterating, because that's what we need to, I think, improve on. Leticia.
Yeah, I would follow that up by saying, and I think the conversation we're having and just the conversations that have been going on at the workshop this week are a great example. But just to start the process, like step one is to get the feedback. And so once you started that ball rolling, like I think it creates a great opportunity for, on the development side, to be more informed, to start building those relationships, like Castle mentioned. And I can say from the work that our social science team has done, whenever we've collected feedback, at least I've never had the experience where the end user said, oh, I hated this experience, I don't want to give my feedback anymore. It's the exact opposite. They are excited. They want to provide more feedback. They're asking, okay, after I've done this, like, will there be like a follow-up session in 6 months or a year? Like, how do I sign up for that? And so the end users really want to provide the developers with their insight and their experiences, so that, as Castle was saying, we can increase that iteration between the two to really keep it an ongoing process to hopefully improve things on both ends. So I would say just like start that process, and although it can be time consuming, find a way, if possible, to keep it going and to keep that engagement consistent.
Makes sense. You got to start to have it. So I agree. Logan.
Yeah, this is, I think the fact that we're saying some similar things across the board, it shouldn't become as a terrible surprise, because I think some of these things are rather apparent as weaknesses within NOAA, and honestly within modeling at large. When you have an operational system at the end of it and users, this is something that is not a new question. I think one thing that is sort of missing is the world of Google Forms, if you will, where at the end of your class or what have you, it's like, put some questions in here, and then it just disappears into the ether, kind of like Castle was mentioning. It was like, all right, bye. And it's like, did that really do anything? Like, what happened with that? A little bit of like as a loop, a circle, like, thanks for this feedback. And specifically, this is one thing that has been actioned upon. Let people know that their feedback is meaningful. This is something we're going to do or consider, or we like this because of XYZ thing. And I think that makes your solicitation of feedback more valuable, and people feel like it's meaningful that what they're doing means something. So that helps a lot. And if we can just continue to iterate and loop through and give feedback to the person who's giving feedback, and then they'll give you more feedback, and then we can learn from each other that way. So I think that's the next step. It's easy to get up here on a camera or screen or whatever and just say, hey, these are nice things we need to do. But to actually see them in practice is really the next step. Can we actually begin to do these things that I think have outlined pretty well that need to be started? Where we're going to see that? I'm not certain, but I would like to think we will. So hopefully some of the folks watching will be the ones to kick that off outright.
Thank you, Logan. Michelle.
It's great being on a panel with truly eloquent people, because then I just have to say, yes, that sounds really great, and smile and nod. So just give a shout out to the rest of the panelists. No, just to kind of build on something that Leticia said, just communicating expectations, and Logan, you kind of alluded to that as well, is that I think, you can get overwhelmed with everything, but like, communicating, we're trying to gather feedback, and this is our process for then following through on what we're going to do with that feedback. And that's at least something I know on our end that we could do better and ensure that. We also tend to work a lot with the operational community, and I think sometimes we get pigeonholed into that way of thinking. And so just to remember that our user community is very broad, and to make sure that we're including all viewpoints and things like that. So,
Cody.
I think I agree with what everyone has said before me, but I'd also like to take it one step further. As we expand to user groups beyond the National Weather Service, emergency management comes to mind because it is a very overtasked community that has a lot of differences in how emergency operations centers are staffed. Emergency manager might actually be a fire chief, and someone might be volunteer. And I think one thing that in working with communities like that and broadcast meteorology and even members of the public is to make sure that, or to do better at making sure that it's not extractive. We need to be better about giving back to those communities for their time and dedication in helping us do our research and create better products and tools and models. So that's something that's been sort of more difficult to tackle.
No, I like that. So in the end, I think I heard a few things. Like, one, start, begin communicating, then iterate throughout the process, and then at the end, go back to the people who gave you feedback and give them something back, even if it's just saying, like, your idea turned into this. Thank you. Or beyond that, like you were saying, Cody. So I think I'm actually, this is great. I'm going to start doing these things. So I guess, we have 2 minutes left. If anyone would like to have a closing thought on the panel, we can do that. If not, I hope that everyone has had an excellent week at the workshop. I wish I was there. I'm obviously not. And, and I hope you have a great rest of the week too.
My only last comment would be simple, and that is that I've said this in other panels I participated in this year. This has been fantastic. It's the last thing I'll be talking about this time, so I want to say it before I go, is the vast majority of NOAA people, our address is our first.last@noaa.gov if you are within, and we're all just folks. And we've talked about starting, and sometimes that starts by emailing one of us or contacting us. And I don't want anyone to ever feel intimidated, and that goes either direction, whether you're trying to contact a user, whether you're trying to contact a developer, or anything in between. We have to talk to each other. And so if you would like to speak to me, anybody has any questions from things I've talked about an hour before, please do. And I'm certain, something I've learned by being in the NOAA environment, that everyone else pretty much feels the same way. We vast majority of us, if not everyone, are very happy to help. So do reach out and don't feel intimidated by that.
Thank you, Logan. That was a wonderful way to take us home. So we're at 45, and I think that is the end of this discussion and maybe the end of the day, potentially.
Yes.
For folks. So, all right. Good. Nailed it. Well, thank you, everyone. Thank you to all the panelists, and thank you to the folks in the room. We appreciate it.
And I just want to reiterate that thanks. I barely could contain my excitement while this panel discussion was happening. And I'm excited to continue the conversation with all of you and everybody else who can be brought into this conversation and figure out kind of where those trust breakdowns are happening and, you know, and figure out what mechanisms are best for, you know, providing this feedback and getting responses. And anyway, I'm very excited to work on this with you guys. And thank you everybody for sticking it out with us. I see a smattering of people still left in the room, and I'm just so grateful you guys stuck around. Thank you so much. Because there's not so many people remaining, we're gonna do 2 raffle drawings tomorrow. So we're gonna end it here. Thank you again. I hope everybody has a wonderful evening, and we'll see you tomorrow.